Hi, Brad. Morning.
Hi, Philip.
Good
How are you?
afternoon. Good evening to you.
Yeah.
Hi.
Good morning to you.
Hi, nice to see you.
You
So
too.
we'll start in 1 minute.
Okay.
So it's almost
I'll be ready.
8:30. Okay.
Yep. Okay. Excellent.
Okay, let's start. Dear friends of digital community, welcome. All of you who are here with us today at the opening event. I thank you for being here at this special time. My name is Philip Yuan Feng, from Shanghai, China. This year is indeed very special, not only because the global pandemic, but also for us, the 10th year of Digital Futures. Back in 2011, Tongji University and University of Southern California started this event, aiming to build a nonprofit global platform for research and education system, and addressing the role of digital in architecture and design. For the past 9 years, we hosted series of workshops, lectures, conference, exhibitions, and published a number of books as well. Thanks to all the instructors, as well as the students, organizers, sponsors with us for the past 9 years, and who actually contributed much of the event. We have evolved from a small group of people to a truly global community that can invite some of the most prominent educators in the field of architecture, and that can offer the students great opportunities that we can't imagine years before. We dreamed, we learned, we talked about the future in the past 9 years. But now we are facing an uncertain future. The uncertainty of pandemic has shown us its influence on our daily lives, but also the endless potential of digital technology in education. Many schools have sorted the online experience for most. The new environment had also reminded us about all the knowledge that comes with the digital world. They are in forms of paradigms, toolbox, and programs made by researchers, scholars, and even students around the world. Upload directly to the digital platforms, bypassing many traditional reviewing process. These new norms are making now the time to restructure our knowledge and education system. A fragmented, disparate pattern of knowledge generation is emerging. And the versatile digital platform and the shared open compatible with the traditional institutions, a new knowledge collective must be created, and from the idea emergence, digital future world. This year, we are hosting actually almost 80 workshops in 3 different time zones, attracting more than 10,000 worldwide applicants. None of this would be possible if it is not for the efforts of all the people involved into the event, including all of you who are watching right now. Here, I thank you, all of you, for making it possible for us to link the world with digital futures and to explore its endless possibilities. Today's conference will cover 2 parts: the paper presentations and the keynote speeches. The paper presentation actually was organized by the authors who submit their papers earlier and will be published by the book from Springer. In late January, we sent out emails and call for papers. Due to coronavirus pandemic, we had to postpone the deadline twice, and finally closed the event around 25th in May. This year, we have received 76 submissions from 15 countries. from 15 countries, 31 overseas institutes, 23 domestic institutions. So this is a conference today, Computational Design and Robotic Fabrication, which is actually part of our special event, DigitalFuture 2020. So the topic this year is machine intelligence. And Springer will publish the first book named Machine Intelligence, the proceedings of the conference. And another book will follow the proceedings book. We'll select around 15 long papers and publish the book also named Machine Intelligence. So this is the 76 paper submissions and around different kind of data from different countries, different institutions, and 23 from the domestic institutions. So as you can see here on the map, CDRF 2020 is inspiring and connecting us all over the world. Among 76 submissions, which 31 from mainland China and 45 from abroad, covering different very important and leading architecture institutions, both domestic and overseas. Comparing to 2019 submissions, we can see a rise in international submissions from different continents in the world, and maintaining the tradition of representing the most advanced research in the field of digital building design. This year, we can see from this analysis, the diagram, CDRF 2020 is witnessing an increasing focus on the AI, artificial intelligence in research, which is around 40% of the papers in this area. So that's the brief introduction of CDRF and computational design and the robotic fabrication conference. And then I would like to kick off the event. And our first keynote speaker today is Professor Bradley Cantrell, so Brad, who is an landscape architect and a scholar whose work focuses on the role of computation and media in environmental and ecological design. He has held academic appointments at Harvard GSD and Rhode Island School of Design, and also Louisiana State University Robert Reich School of Landscape Architecture. His work in Louisiana over the past decade points to a series of methodologies which develop modes of modeling, simulation, and embedded computation that express and engage the complexity of overlapping physical, cultural, and economic system. His speech today will feature on adaptive vocabularies and new ones. Now, let's welcome Brad. Bradley, please. I will stop sharing the screen. Yeah, please, sharing your screen.
Okay. Can we see that?
Yes.
Okay, great. Thank you, Philip, for the introduction. Thank you for the invitation. It's an honor to be able to speak to everybody here today about my work. I'd like to speak and outline my outlook on the discipline of landscape architecture, and more broadly how computation may shape ecology and the planet. So today I'd like to outline a view of the built environment that I believe is critical to develop as designers in the coming decades. The problems we face are larger than ever before, are embedded with infinite complexity, and are outside of our cultural understanding. Landscape architecture and the landscape itself can provide a sinuous connection between our lives. the architecture we inhabit, the urbanism that expresses our desire, and the environments that sustain our very existence. Most importantly, this landscape, the terra, the aqueous bodies, and the atmospheric envelopes must be reimagined, both regarding how we see and relate to it, but also in how we propose our future. We have positioned the discipline of landscape architecture particularly as a body of knowledge that can design across scales and produce controlled scenarios from the molecule to the territory. But we're still proposing a future based on the praxis that was defined by modernism, a quest for truths and subsequent propositions that are couched in different forms of certainty. So the contemporary environmental condition is one of ecological hybrids, an evolved state where constructed megaliths exist within noisy gradients of the pseudo-natural. These landscapes, hybridized territories, are the product of the exertion of civil engineering, environmental management, and the pressures of urbanization. Where does the discipline of landscape architecture stake its footing in the ecologically complex and technologically abstract realm of contemporary society? To confront the intractable issues of our time, it is necessary to unpack the technologies and subsequent interactions that operate at the scale of the territory. So the interface between the built environment and evolving biological and geological systems requires a blurring of previous strategies to address nascent forms of simulation, sensing, logistics, biological engineering, and technological interface, questioning the dichotomy of the constructed and the natural. It is necessary that landscape architecture takes the stance that designing the territory requires the application of reflexive and responsive technologies and methodologies to propose new infrastructure situated within ever-evolving feedback loops. So the interstitches of these new relationships become the medium in which the discipline may then examine new potentials for construction and maintenance as a starting point to propose new infrastructural landscapes. Once married with, so this is a quote from Kelly Shannon and Marcel Smets. Once married with architecture, mobility, and landscape, infrastructure can more meaningfully integrate territories, reduce marginalization and segregation, and stimulate new forms of interaction. It is at this point that it can then truly become landscape. So this hybridized ecology is a cyborg, positing that the role of landscape architecture is in designing and implementing technologies that promote active and real-time methods of environmental stewardship and management. These methodologies span a range of scales, from micro adjustments of chemical processes, to automated construction, to regional management and monitoring, to global remote sensing systems. Primarily, the concept of a cyborg ecology creates a recursive and/or iterative relationship between computation, biology, and landscape processes. So landscape architecture has long grappled with the material craft of landscape and its subsequent connection with larger territorial systems. These shifts in scale are primarily addressed through hints of connectivity, purported moments where the complexity of the territory is drawn into the scale of the human figure. There is little doubt that the rhetoric permeating the discipline states the effectiveness of the landscape architect as the planner of the territory, particularly as it relates to sociocultural issues, biophysical properties, and ecological fitness. What becomes harder to decipher is how that stated agency manifests itself on the ground, in actionable and nimble forms that live up to the discourse that is developed around process, indeterminacy, and flux. So the discipline aims to conceptualize and articulate the territory as an adaptive infrastructure, the landscape in a state of flux as it responds to changing environmental, programmatic, market, and sociocultural conditions. We can see this through a cynical lens in this quote from John May, where he says, "Our managerial posture demands that all of life be displaced to a condition beyond the natural and the artificial, to an ontological plane where such distinction no longer makes sense and can no longer interfere with the choreographing of matter." This is this quantification of ecological and environmental systems. But this approach places emphasis on the content. So the approach that I'm putting out places emphasis on the contingent, the provisional, and the conditional, and asks designers to amplify productive instabilities while inventing new types of landscape and form. Therefore, the landscape, physical and ephemeral, formal and indeterminate, is our starting point for the project of generating and maintaining complex environments. So as we talk about this, it's not a project to control our environment. It goes beyond the all-seeing eye of our remote sensing and geographic information systems. Jennifer Gabrus has a quote: "If the satellite view has largely been narrated as a project of making a global observation system and seeing Earth as a whole object, then the more distributed monitoring performed by environmental sensors points to the ways in which the Earth might be rendered not as one world, but as many." So within this, landscape has the ability to integrate the environmental, social, and scalar challenges that are at play in the larger territory. Furthermore, landscape architecture absorbs and hybridizes these multiple functions in ways that engineering, environmental science, or planning alone cannot. The medium of landscape also offers operational frameworks and modes of integration that emphasize dynamics, change, and adaptation, mechanisms that are in play in all ecosystems. It's essential to address landscape both as a medium to design and as a mechanism for testing and prototyping interventions that reshape the territory. So rather than understanding medium and mechanism as separate, it's necessary to emphasize hybridizations of systems and environmental dynamics. This would suggest working methodologies that privilege experimentation and iteration, playful and critical prototyping, pathways towards new responsive landscape-based approaches for territorial systems. So human societies have reshaped ecological patterns and processes across the Earth, both directly through land use and by facilitating the movement of species, as well as indirectly through pollution and climate change. Even in protected wilderness areas, it has become a challenge to sustain ecological patterns and processes without increasingly frequent and intensive management interventions, including control of invading species, management of endangered populations, and pollution remediation. Further, such interventions themselves may further alter ecological patterns and processes. The planet in the Anthropocene is a diverse and complex landscape, functioning at every scale, crystallized across a static framework of infrastructure, physical and logistical. Canals connecting disparate watersheds, pumps pushing water uphill to defy gravity, pollinators transported for crops, and thousands of kilometers of levees, irrigation technologies, and many other things that repattern entire regions. Our current environment is a literal cyborg of contemporary humanity. The infrastructural framework is bold. It's produced via applied capital to transform the hydrologic, climatic, and ecological regimes of the planet. Its success relies on predictability, models that define the future via abstraction and simplification. So the friction unraveling the planet we occupy is situated where the environmental dynamics of territories confront the stasis of an aging technological, political, and social infrastructure. So to promote a neo-projective language for territorial landscape intervention, it's necessary to understand the influence that infrastructures impress upon landscape systems. Historically, the implementation of landscape infrastructure has relied on a regime fixed by epistemological frameworks. These are verifiable truths that are seemingly self-evident, but most importantly, they're calculated, modeled, and verified as a basis for the proposal of megaliths, infrastructure that is constructed and operates at the scale of large territories. What is unknown in these situations is quickly excluded from the conversation or over-engineered in the need for safety and predictability. Stasis is the defining factor within this modernist framework. It's set, though, within a viscous and vigorous environment that demands change and erases histories. So to operate within this realm requires the embrace of new vocabularies, calculated failure, and forms of adaptation. These are design strategies that rely on adaptation via prototyping, framing the landscape as a laboratory to test the effects of systems at scale. To explore these facets, I'm going to describe a body of work that begins to capture these attributes. In my own work, some of the oldest projects are the most comprehensive, but also the most naive. The more recent projects interrogate specific themes that are present in the older work, in some ways explaining the intuition that was driving these earlier guesses. So I'm going to speak about several projects. Some are a bit more abstract, but are very much about defining these new vocabularies and exploring these concepts of failure and adaptation. So the first one is this idea of failure. So failure in general requires a subject to fail. Without the subject, we are simply discussing processes. This work comes from a series of drawings collaborating with Emma Mendel for the Drawing Codes Traveling Exhibition and the Night Gallery for the 2019 Chicago Architecture Biennial. Drawing Codes was a product of work by Andrew Cudlis and Adam Marcus, and the Night Gallery is by Future Firm in Chicago. What we see is the timeline of human categorized environmental failures over the past 30,000 years. This has been a continual process of humanity expanding its technological prowess while developing rules, instructions, and frameworks for how complex environmental phenomena should interact. These are catastrophic events, but they are also a legitimate part of the evolution of humanity. Our ability to further abstract our complex world and develop solutions to the problems we create has led to a cascading series of failures that are reshaping the planet. The time these failures exist is within the Anthropocene, a human-induced geologic epoch that is the product of our static infrastructural frameworks, sites resource extraction, and ever-expanding forms of settlement coming into contact with a biological and geological medium that is both dynamic and indeterminate. So reading from our statement for the Drawing Codes competition, failure is at the heart of landscape. Environments inherently complex, multivalent relationships in constant flux with indeterminate beginnings and endings. As designers, the dominant paradigm avoids failure, attempting to predict externalities through ever more complex modes of simulation. Complexity beguiles prediction, making it impossible to predict whether or not one unprecedented event is more likely to occur over another. However, it is through the embrace of failure that we develop systems that more readily recover from disturbance, systems that lack fragility and have the ability to respond to unknown outcomes. This requires a paradigm shift. How do we operate in a world that understands it cannot predict a chaotic future? An environment that embraces complexity but rejects predictability. So the application of failure is formed through continual testing, applying stress and digesting the outcome, the product of accumulation and eradication, revisited through irregular schedules, through our own feigned technical competence and our sparks of response. It's a method that has little explanation without post-rationalization, requiring new eyes to determine its history and purpose, like an anthropologist sifting through cultural artifacts. So in this series of drawings we did, we called failure, we attempt to represent the fragility of a single representation. No moment is whole. Each action cannot exist as an entity or contain meaning, formed to the traces of the others, but can be re-related in any order, misaligned, contorted, inverted, or erased. And in this, we dubbed this an anti-method or anti-drawing, coded through the process that we created internally. So in this sense, it's this idea of emergence and this exploration of failure within emergence to form an evolved form of representation. So complexity in landscape pushes back on our obsession of attempting to find a non-existent order. So this is some kind of writing we've done around this kind of concept of failure and a series of drawing processes and code that we developed to kind of explore these kind of unknowns or random interactions. The second thing I will bring up here is a competition entry, and this is really about beginning to change our vocabulary. I worked on this project with Emma Mendel as well and Fionn Byrne, and we use this as a way to redefine the vocabulary around islands. So rather than drawing the island, we used fungi and mold and chemical reactions to define multiple states. In this project, we ask ourselves, how do we know when a plant has died? And as a human, we will expire our last breath as our neural activity comes to a halt and the heart discontinues the steady beating it began as we were born into the world. One would think there is no better metronome of vitality than the heart. So in this, we began to redefine this concept of life and death and begin to then use that as a new way to explore the vocabulary around island. So I'm going to read a little bit more from the statement. As this restless muscle finally relents, death takes over. While certainly you understand life and death as a process, you'll have no trouble distinguishing one from another. But the kingdom of fungi demonstrates a most odd hybrid of alive and dead. Having no excretory organs, each cell in a fungus must deal with its own waste. With growth, they build upon non-living material in vacuoles or cell walls. This slow accumulation of death is contradictory to one of our most important dualisms. No last breaths will punctuate the border between subjectivities of alive and dead. So our first redefinition in this project was that of time, the ever-changing relationship between the island and our perception of it as a defined entity. The second definition that we began to question was the one of measure. The boundary length of an island increases with precision of measurement. And this was all about fidelity. Based on the scale it is observed, depending on the scale at which you draw the island, the measurement is infinite. And then the third was scale. The continuous boundary of an island is contingent on scale. Within the island are other islands, spores, porous boundaries, all impossible to define. So ultimately, the project arrives at an expansion of our use of vocabulary. And in this, we make the statement, to speak differently allows us to think differently. And this is really about expanding the language of islands and edges into a broader lexicon. Therefore, what the fungi we use to represent the project teaches us is that our representation of the world is limited, divisive, and subjective. Our sense organs act to constantly cleave things from an undifferentiated medium. Our powers of perception fumble to see the unmediated space and time and energy through which we exist. Here in this medium, there are no islands, no binaries, no edges, no objects, no beholders. It's really the way we perceive and describe the natural world, which becomes extremely important as we begin to think about forms of management and the design of ecological systems. So from that, then I'd like to put this quote out for everybody. And this is from Levi Bryant. To be in a world is to be decentralized, to lack all mastery, and to be a participant in an assemblage, network, or composition that exceeds society, culture, and oneself. In this sense, thinking of conceptually about how we begin to flatten the hierarchies that we've developed as human beings in our relationship with the environment. So to have agency in the territory requires tools and strategies that construct an epistemology that is adaptive, an ability to create prototypes that exist throughout the life of a landscape, a feedback loop, and ways to belie hyper-efficiency or control. To create an adaptive epistemology, and so an evolving idea of knowledge, for design, it's necessary to not only adjust our theoretical frameworks, but to also develop new tools for representation, experimentation, and prototyping. This would require us to begin to create laboratories that focus less on empirical data and instead highlight the methods and interventions required to choreograph dynamic landscape systems. These choreographies focus on resistance, producing interventions that disrupt or catalyze ecological systems to produce landscapes that are robust, relying on the concept of anti-fragility, infrastructures and landscapes that produce a heuristic, evolving alongside one another, testing weaknesses and learning to repair, patch, and grow. How might we approach design's agency in an adaptive epistemology? Through a new set of design tools, possibly? A suite of responsive interfaces, interventions, and infrastructures that sculpt, inflect, and choreograph the complexities of ecological systems to develop knowledge that is rooted, but also adaptive. While there's several groups researching these tools, a body of work can be found in my own research over the past decade that originally formed during my time researching infrastructural adaptation in the Mississippi River Delta after the devastating effects of Hurricane Katrina in August of 2005. This work attempts to merge the computational prowess of numerical modeling with the tangible tools of physical modeling developed in North America by the Army Corps of Engineers. So to further explore this research, it's helpful to frame the issue of coastal adaptation. If we think about it, approximately 40% of people across the globe are living within 100 kilometers of coastal and riverine environments. This means that 3/4 of the world's megacities and critical infrastructure are situated next to the ocean and will be required to adapt to fluctuating sea levels over the next century. This will be a monumental task for humanity and will require new methods of adaptation, retreat, and construction that are currently outside the scope of our current capabilities. Therefore, it will be important to reimagine how the coast is reformed to provide for the complexity that has been slowly eroded. So this body of research was realized in the formation of the Responsive Environments and Artifacts Labs, co-directed with Professor Alan Sayegh at the Harvard Graduate School of Design. The REAL Lab has conducted research that examines the potential of responsive technologies across a variety of scales, focusing on systems primarily at the territorial scale and the manipulation of indeterminate land building using real-time sensing, robotics, and adaptive management techniques. This body of work has followed me to the University of Virginia, where I'm currently working, and I'm developing collaborations with architecture and environmental science to establish what we call the Open Systems Lab, a university center dedicated to design technologies. So some of the first funded research projects are underway, looking at physical modeling methods in collaboration with Ajay Lime in environmental science, and further collaborations to develop methods of heterogeneous forms of algorithmic cultivation. The first modeling projects at the REAL Lab utilized a geomorphology modeling table, originally designed in collaboration with Steve Goh at EM River to simulate dynamic riverine and coastal environments. This became the site in which designers at the school and researchers began to develop approaches to fluctuating hydrological systems. The model utilizes 4 sensing systems using ultrasonic range finding sensors, real-time photogrammetry, image analysis, and capacitance sensors to record sediment behavior, surface morphology, and water flow. The geomorphology model is imagined as its own space with dynamic phenomena that is unique to its conditions. This allows the model to be free of attempting to simulate a specific physical landscape or reality. With that being said, there are baseline conditions derived from prototypical geomorphological tropes, such as delta building, meandering rivers, backwater swamps, and tidal zones, among others. The modeling space creates a tangible environment that can generate a huge range of conditions. These conditions are created using a synthetic sediment of varying sizes and densities, pumps to create stream flow and groundwater flow, and an adjustable bed that can set lateral and longitudinal slope as well as depth. These variables can be altered to set the initial conditions and also controlled over time. The controls on the table allow the researchers to program hydrographs for both stream flow and groundwater flow, creating flow input profiles that are repeatable. The media feeders can create measured mixes of sediment that are inserted into the water flow, and there is also an injector that can introduce dye plumes into the flow, helping to visualize water movements. The varied synthetic sediment sizes and densities self-organize based on water velocities, resembling a range of particulate matter from an abstraction of large gravel, or yellow, which would be in yellow, to a fine silt, which is in red. It's actually not on this slide. In coordination with the modeling elements, the modeling space also has a sensing system that allows for the researchers to gather data on surface morphology, flow rates, sediment moisture, and image analysis. Using ultrasonic sensors that measure distance, the system can move the sensors across the table to record precise spot elevations as well as continuous sections. using a Microsoft Connect. It's also used to record a continuously updated point cloud of the surface. Combining these, it's possible to derive a precise real-time model of the surface at multiple levels of detail. The controls and sensors allow the model to deliver a broad range of fluvial landscape scenarios with consistent seeding parameters. The overlay of sensing technologies allows for the acquisition of data to experiment with methods of visualization, analysis, and interaction. The model is more complex than static models, but it's important to acknowledge that it's also an abstraction that generalizes fluvial landscapes. And these are just some images from some of the software we developed in order to visualize the data that was being recorded from the table. So this research, it advances a form of, it's a project that holds great promise for how we engage large-scale environmental change, engaging highly dynamic systems and utilizing their energy to compose new terrains, which provides a mechanism for massive change with minimal input. The feedback between sensing systems and landscape modification forms a construction methodology that is tunable and challenges methods of complex simulation and static infrastructure. Using the real-time digital models, the researchers are then creating devices that respond to the changes in the physical model, such as robotic sediment gates, repositionable sieves, and flow disruptors. The intent of this exploration is to develop prototypes and a design language that enables designers to create novel hydrologic landscapes that are tied to sense phenomena and forecasting models. The current scope of the work provides a proof of concept for an emerging tool set to engage the world at this scale. The tool set relies on real-time sensing, but it's also coupled with methods that are formed around adaptive management to produce closer relationships between landscape analysis and subsequent methods of construction. Conceptually, this proposes a method that relies on designing operations that intervene locally but aggregate to produce territorial change. Most importantly, this is a form of landscape choreography that continually learns from itself by processing the results of its actions before choosing the next intervention. It's a continuous call and response between biological systems and an active infrastructure. So to produce these interventions, research has taken different approaches. As I mentioned before, this is really about like using this model and the data generated from it to create responsive prototypes. And this is, then about managing the product of those interactions. This is a project by Tyler Moore and Andrew Boyd called that is really examining how indeterminate landscapes might be represented and managed. So an important step in this work has been to develop a range of motion within the infrastructural interventions and to then document their influence. Using image analysis to record subsequent iterations, this documentation illustrates a formal design language addressing indeterminacy. Producing topographic plans that speak to movement and probabilities of change. The illustrations highlight a landscape form that expresses areas of stasis and flux, forming a gradient of interaction between the two. Furthermore, the work of Leif Estrada utilized the lab to explore how the Los Angeles River Channel may be deconstructed and reconstituted as a composed and managed riverbed with a highly developed urban fabric. So categorizing the materials of the deconstructed Los Angeles River, the work proposes the reorganization of the demolished channel using the energy of high water moments in the river. The approach utilized a series of individually controlled insertions into the sediment that redirect the graded material from the demolished channel. So assuming that each material has its own performance and its interaction with the hydrology, it's then choreographed to produce a range of riverine landscapes. The new riverbed is the product of interactions that guide outcomes. Most importantly, these outcomes are controlled within a range, and their aggregation is a consequence of the current hydrology while projecting a series of future goals. So these distribution patterns are analyzed and calibrated to produce these novel habitats for a diverse series of species, including humans. So, essentially deconstructing the river system and then using these high water moments to repattern the downstream condition. And within that, using the kind of indeterminate outcomes to guide them towards these ecological systems. These are dynamic and evolving systems, each with their own temporal dimensions and physical expressions. You can see in this image a choreographed redistribution of sediment and materials as the infrastructure moves up the river channel, deconstructing and redepositing in each annual flood cycle. So, within this, ideally the work in the lab really examines the idea of tools, right? And so it goes beyond kind of forms of documentation that we use in landscape architecture. The work produced helps to enhance the tool set of the architect and landscape architect and develop design approaches that utilize this ever-expanding command of computation. Proposes a method of intervention that collapses representation, analysis, documentation, and the construction process. This requires a tactical approach to landscape formation, relying on the design of operations that rest within local observation, sensing, and as I mentioned before, long-term forecasting. And so this is, this kind of tool set is one that I've been, and others have been exploring recently as a way to begin to think about how we might approach these highly complex riverine systems. So in this, it's the feedback between sensing systems, machine intelligence, and landscape modification that creates a construction methodology that is tunable and challenges ideas about simulation. The goal is to move beyond our known representations and design methods and develop the tools necessary to address these current global conditions. From this idea, we can identify 4 methods for establishing an adaptive epistemology that engages the material landscape. The first is this idea of micro-modifications, bottom-up processes such as eutrophication and soil catalyzation, made up of slight localized alterations, resistances, and shifts across multiple operations. The modifications are tuned for a range of scales and read as gradients within the larger landscape. So this is kind of 4 kind of ideas about engagement. First one being this idea of micro-modifications. The second is the celebration of novel relationships created and monitored based on evolving methods of simulation and machine learning. These relationships curate new ecologies based on performative pairings and evolutionary trajectories. This method creates relations that format, predict, reorder, or nudge systems in unknown directions. While these may be system-wide changes, it is assumed that they would be emergent, functioning as predictors of the unknown, tested and altered to suit our current conditions. The next is this idea of what I would put out as called temporal exploitation. It's the manipulation of systems across both the micro and macro timescales to respond in the moment to long-term goals. So this method views time on a continuum where each modification references historical data while simultaneously speculating on future trajectories. It's also this, this ability to essentially begin to slightly speed up or slow down different types of landscape systems. And this is a kind of a concept that's embedded in landscape architecture that I believe is extremely important in this idea of ecological management, and particularly through this idea of through computation. And then the last one here is this idea of phase manipulation. It refers to the intentional intersection between entropic processes and actuation to shift these trajectories. So this manipulation is expressed through small shifts rather than complete state changes within systems. For example, the alteration of water velocity or the liquefaction of soil substrates. So from this, we can see one attempt to develop new tools for design, tools that form a new relationship between landscape process and construction methods. And so I think so hopefully there's like a bit of a trajectory there in terms of tools and the new processes that they enable in terms of how we interact with landscape systems. Just looking at my time. Okay. So that body of research is very much about tools, and there's a kind of range of things going on in that realm. As I mentioned, there's a lot of other folks working in similar ways. But in another body of research that I've begun to develop, and this is work with my colleague Earl Ellis, an ecologist, and Laura Jane Martin, an environmental historian. We explore the potential for fully automated management systems within the environment to create and sustain new forms of wild places. We use this term wild places without ongoing direct human intervention. And we talk about this in a paper we published in Trends in Ecology and Evolution. This paper is called Designing Autonomy, if anyone's interested. So from this, I'll read a little bit and then kind of talk about some examples. So recent breakthroughs in artificial intelligence have produced systems capable of solving complex problems through algorithms in which the rules of behavior are not derived through programming, but through evolutionary processes of machine learning. This is probably obvious to everyone on this stream. Most of us know the story of AlphaGo and the deep learning approach that it used. It's learning from games played with itself to defeat the world's top-ranked human player in Go. It's a game long believed to be so complex as to be intractable to computing. At many points, what's most interesting about this as an example, at many points, AlphaGo deployed innovative strategies. Thus, the prospect of intelligent systems capable of acting autonomously in real time to sustain the autonomy of non-human species and ecological processes without direct human intervention appears increasingly possible. Indeed, machine learning methods are increasingly used to develop species distribution models that inform conservation decisions, identify and monitor unique species, analyze existing data sets, and then among many other applications. Importantly, conservation biologists and managers are also employing deep learning systems and other technologies to eliminate, counter, or mitigate anthropogenic influences on species and ecological processes. So essentially using forms of machine learning in order to kind of separate the kind of human or anthropogenic and natural system divide, right? And to set up this kind of artificial barrier between those interactions. So for us, to explore the potential of automated systems for sustaining wild places, we began by reviewing the concepts of wildness and autonomy. We then introduced a framework for describing different levels of automation, and we linked these to levels of environmental management. The highest levels of automated environmental management were then explored through the speculative design of an automated infrastructure, and we call this a wildness creator. This creates and maintains what we're saying are wild places independently of humans. As with self-driving cars, these automated technological systems for environmental management are rife with practical challenges and ethical dilemmas. Indeed, fully automated systems may ultimately prove both impractical and unethical. However, the prospect of fully automated environmental management raises important questions that designers, ecologists, and conservation biologists must address in their efforts to enhance non-human autonomy in increasingly human-managed ecosystems. I put the question out there, and I think it's one that should come up right away. Can wildness even be created by human beings? And when we use this term wildness, we're really talking about systems that are perceived or are outside of human influence or control. And I think there's a whole range of things to debate within what I just said, but I'm trying to simplify this for the point of this discussion. So the idea of creating wildness is not new. In the 1920s, for example, and this is just one example, American ecologists developed the idea of creative conservation. And Harshberger concluded that ecologists may reproduce nature so closely by the use of native plants that our fellow humans are deceived and believe that they look upon a wild growth when it is in fact artificial. A few years later, ecologist Edith Roberts and landscape architect Elsa Raymond described how to garden so as to leave the woods absolutely natural and seemingly untouched. Indeed, for nearly a century, landscape architects and restoration ecologists have sought to intervene in landscapes in such a way that mimics wild nature or facilitates its autonomous recovery. And there's a host of projects out there, and this is, once again, in no way exhaustive at all, and just to give you some examples, but there's a host of projects already shaping ecosystems through semi-automated strategies that enhance the autonomy of non-humans. And I use the word enhance, but they actually also do the opposite of enhance other species. So wildness is an unusual design challenge that is fraught with contradictions that are technical and formal, as well as cultural and philosophical. The design of wild places has usually aimed to preserve the historical character of regions, establish the picturesque, and to curate human experiences harking back to a period before modernism. However, to design is inherently a human act, an influence in itself. To design a space free from human influence therefore requires a distanced authorship, favoring process, curation, and choreography. Such design from a distance would need to allow ecological systems and wild populations to co-evolve through their sustained interactions, sustained by an infrastructure operating beyond human control or interference to continuously promote non-human autonomy and counter human influences. So the point we try to make in this is that we are already at a place where the natural environment is often a cultural construct of humanity, and the perception of the kind of control or lack of control of those environments is a large part of the way we understand the world around us. In many ways, we are moving towards a space where computation is playing a greater role in the management of those complex environments, and the product of that management is moving towards a realm where we don't quite understand the decisions being made by the infrastructural or the management infrastructures. What that produces then are landscapes that are the product of machine interaction and the biology or the geology itself, and that environment is inherently perceived as wild, particularly if we don't quite understand the management protocols or what exactly is occurring. An example of this is the hotspot, and this is I won't say this is a direct example because the work and the research that I'm talking about goes much farther than this. But the idea of the hotspot, this is the crown of thorns starfish bot, and this has been deployed in the Great Barrier Reef off the coast of Australia. And the hotspot is an interesting example that is essentially moving across the Great Barrier Reef and using image analysis to basically find crown of thorns starfish. It's then when it finds one of the crown of thorns starfish, it uses basically a probe and injects it with a bile solution to kill it. The crown of thorns starfish is an invasive species, or considered an invasive species that's basically eating the coral reef. Interestingly, the crown of thorns starfish is there because there's extra agricultural runoff from the deltas, but at the same time, what we end up with then is a management system where we have an autonomous drone moving through the ocean and using image analysis to find these species and actually as a predator putting them down so that they don't continue to eat the coral reef. So we have a predator who's basically is a human management protocol. Right now, obviously, it's using a series of instructions that are easily understandable, and we can understand the kind of consequence of that. But I think we can all imagine very quickly how different decision-making processes might completely change the choices a robotic management system like this might take. So if we talked about this as a larger system, and we think of, we already have forms of semi-autonomous ecological management, you can imagine then the idea of this creation of wild, what we could call wild or what seem to be unmanaged landscape systems. If these kind of if these managers were unseen and we weren't kind of in direct, our knowledge of its actions weren't complete. As with current efforts to naturalize restoration decisions, the prospect of wildness, creating wildness that is perceived, comes from this idea of the machine as gardener. It concedes decision-making to non-humans, the machine intelligence, rather than confronting humans with difficult, complex, and political decisions in environmental governance. So you can imagine in some ways that you can almost offload environmental decisions to a system like this. This work has been important to develop as it outlines a future for our relationship with the environment. That is a direct trajectory offered by our current forms of automation and guided by our further implementation of different types of machine intelligence. This speaks to a couple things. As I mentioned before, this kind of design of operations, it's important to begin to really frame the importance of protocols and the design of the interactions that govern systems. These are some two quotes by Galloway and Thacker, but this idea of protocol is twofold. It is both an apparatus that facilitates different networks and a logic that governs how things are done within that apparatus. It's important, it's not simply about the creation of optimized systems, and there's a concept of resistance that's also important. So this idea of protocological control fosters the creation and regulation of life itself. In other words, once again, I'm quoting here, in other words, the set of procedures for monitoring, regulating, and modulating networks as living networks is geared at the most fundamental level toward the production of life in its biological, social, and political capacities. So the target is not simply protocol, rather, to be more precise, the target of resistance is the way in which protocol inflects and sculpts life itself. So in this idea of resistance becomes important. How do we begin to use protocol as a form of resistance? And how does that then begin to sculpt and reflect these natural systems? Am I doing okay on time, Philip? Just another few minutes? Sorry, I can't hear you. Maybe you're. I have one more project to talk about, and then we can maybe do questions. Does that work? So finally, I'd like to end on a multidisciplinary project. So this is the one at the very beginning of the talk. I mentioned that this is one of the older projects I've done, but it had a lot of these same kind of ideas in it that you can see have been kind of extracted and explored through these much smaller projects. This is a project with the Louisiana State University Coastal Sustainability Studio and a collaboration with Elizabeth Ann Williams, Jeff Carney, and Matthew Seibert. It's a year-long funded project and is recognized by several awards. So to jump right into the kind of definition of the project, embedded within the sands and silts of shifting coastal surfaces, multi-scalar relationships across urban cores and their outskirts render vibrant socio-ecological landscapes, incorporating gradients of population, industry, investment, and regulation that stretch of the shore between Houston, Texas, and Mobile, Alabama. This presents one of the most vulnerable mega regions throughout the entirety of the United States. And within this urban economic expanse, the Tri-City Delta landscape between New Orleans, Baton Rouge, and Houma Thibodaux has evolved to maintain significant cultural and industrial value. The central wetland of Louisiana is embedded within an expansive web of resources. And this project, which we called Synthetic Mudscapes, speculates on the potential of alternatives where human occupation effectively strengthens environmental resilience in the face of sea level rise, subsidence, coastal erosion, and increased storm frequency. So in order to defend infrastructure, economy, and settlement within the region, It was essential to reestablish a rapidly disappearing landscape by constructing new land to alleviate increasing risk. Links between urban environments and economic drivers have constrained the dynamic deltaic soils for generations, now threatening to undermine the ecological fitness of the entire region. In order to found a resilient, layered mitigation strategy, 3 distinct land building practices provide an arc for transforming these systems. So these were 3 ways of rebuilding land and on sites in the Delta. So at the Isle de Jean-Charles Crescent, dredge material and drill cutting debris are deposited and then continually deepen transport lanes for an expanding oil fields. It's a high diversity and concentrated seeding is dispersed to sustain land growth. The other is along the outlet of the Mississippi River levee system. This is near the Myrtle Grove diversion, south of New Orleans. Releases sediment and sifted landfill material transported from the river basin, and it's really accelerating natural land building processes. And you can see this kind of underlying form that begins to take. And the third is really about nutrients being, and their kind of entrance into Lake Pontchartrain, and redirecting those to help regrow coastal ecologies. And I know we're running out of time, so I'll be quick here. But this is very much then about beginning to use this kind of actuation of sensing and monitoring, and kind of the continual building of knowledge about a landscape system. So, really what we began to imagine was this kind of underlying model that would begin to be built from the environmental data that was being input into it. This was, once again, about 7 or 8 years ago. And so in this, we were thinking that this would be this kind of ongoing, almost library of environmental data that begins to help us manage each of these landscape conditions. Within that then, with this diagram, it's really then about kind of moving up and down this idea about management and investment, and how we begin to think about how parts of land are maintained as open water, how they become active as accumulating sediment, might then become healthy wetlands or established land that could begin to form as kind of infrastructure or areas for settlement. And if it's essentially moving up and down this kind of diagram based on political or economic moments in time. So in this then, really thinking about how these 3 sites are kind of emergent from their own kind of physical conditions, but also sitting under the umbrella of kind of economic and political pressures. So I'm going to kind of close down from this, and maybe there'll be some questions. But as I mentioned before, what I'm trying to begin to develop in my own work, and I think many others are as well, is thinking about how we begin to kind of alter our design methodologies, alter our engagements with the physical world in order to really dive into this concept of the intractable problems that we're facing, the complexity of those issues, and the kind of fault of our previous deployment of infrastructure and other large-scale systems. So thank you all for this opportunity. It's a real pleasure to present this to you, and I look forward to continuing the conversation with everyone.
Okay, thank you. Thank you so much, Brad. It's a fantastic keynote speech. I think I can see around in Bilibili around 7,000 people listening this your lecture. I don't know how many in YouTube, but I think it's a 2 channel. A lot of students and researchers right now, they put forward a lot of questions. I want to briefly say something about my impression. I think it's right now it's a quite cross-discipline research area. What we are doing actually very similar to what they were doing. We are doing some cyber wind tunnel to testing different kind of high-density, high-rise building in Shanghai, this kind of environment. It's very similar to what your make research in the hydromorphic or hydrographic system you set up. I think it's kind of an extension of the human body. You have more tools to simulate and make more feedback from the test and from the test process. And actually you can predict what you want to set up in the design process to predict some future. It's very interesting for the question, can the wildness be simulated by designers or by computers? I think it's kind of challenge to the intelligence of the tools you set up. The protocols you input into the system is really important. Right now, it looks like it's really related to the geometry system, the water speed, and the different kind of the material, the soil material, giving different kind of feedback to the system. So some of the students, I think one question is really interesting in the Bilibili group. They're asking the parameters of protocols you input. Is there any human activities or the animal's performance will influence your system? So they're asking, right now it looks like all the physical parameters which influence the system. Is there any more complexity of your system could be set up by what's your simulation process?
Yeah. So I think it's the right question to be asking, and I think much of the research doesn't quite go all the way in that direction, so I would point that out as a weakness of some of the work. There's much of the ways we've focused on this is by really thinking about what are the landscape conditions that can be formed that then support different types of life. And so is that kind of biological life in forms of plant material or different species, or is it about human settlement or kind of human activity? So rather than thinking about them as simulating what happens then in those spaces, it's more about how do we choreograph these landscape systems in order to produce the conditions where the next stage could be for the occupation by other species of some kind. So the research isn't trying to hasn't tried to simulate how those activities then play an influence back on the system, which I think is critical. It just hasn't gotten there yet. But yes, I think that's an important thing to begin to imagine and begin to develop protocols for.
Yeah. Okay. I think we should control the schedule. So thank you so much for that.
My pleasure.
It was a fantastic lecture to opening the whole event. It's great thanks to your support.
Yeah.
So I'm looking forward to inviting in the future, if you have time, and some special opportunities, come to Shanghai and make some physical real lecture to us. I'm very interested in your research and the way you set up. It's like a collaboration between human being and machine. So it's kind of a cyber future we mentioned. It's kind of collaborative between the machine protocols, algorithms, and human being. So that is something about the future, not only in the landscape discipline, landscape architect discipline, but also architecture discipline as well. So thank you so much for everything you give us today. It's a great lecture. Thank you so much.
Thank you. I appreciate the opportunity. Thank you. Look forward to being in Shanghai sometime soon.
Yeah, in the future.
Yeah. Thanks.
Thank you. So also there are some questions, but you can check, but probably we don't have time today. So the next session, I would like to invite Professor Huang Weixing, who is the session chair for the conference this morning. I want to briefly introduce Professor Huang Weixing, who is Professor Huang Weixing here? Okay.
Yeah. Good morning, everyone.
Hi. Professor Huang is associate professor teaching right now in Tsinghua University, and he actually play leading roles in not only China but also in the whole Asian. He is very importantly play a very important leadership in CADRA, and actually helped to organize a lot of special academic event in past few years. And this great honor to appreciate your support for CDRF conference today. So I would like to give time to Professor Huang Weixing You could give a 10 minutes introduction to the whole section and your work. So please, you can share your screen.
Oh, yeah.
Okay.
Thank you, Philip. Yeah, I'll try to share my PowerPoint and see if you can see my PowerPoint playing.
Yes. Okay.
Yeah, thank you very much. Yeah, it's my great honor to be a session chair of the CDRF conference this year. And thank you very much, Philip, for the introduction. Actually, it's my honor to be here. And it's a very good opportunity that I have the chance to introduce some of our work, the work in my lab with my students. And the topic of my introduction to our work, human-computer integrated spatial cognition. Actually, in the digital architecture design area, we have a lot of interesting areas to work in. Sorry, so I don't know if you see it's like my PowerPoint or it's the.
Right now, you should. I think it's better.
It's
not the real
some
PowerPoint.
problem with the.
Yeah. You should start. Yes.
Sharing the screen. So this is the. Is it okay now?
Okay.
袁老师现在是在播放的状态吧？
现在可以了，现在可以了。
是的，播放。
好的。刚才可能设置有点问题。Sorry for the setting of the screen. Yeah. So in my lab, we have several different research directions related to the design and construction, and also the evaluation of the constructed environment. First, in the digital design area, we are trying to do some design generation and cognition research. And in the construction area, we developed a system called weaving structure, which is a bending active frame-form grid shell construction system. And in the evaluation the process of built environment, we try to do spatial temporal data analysis in environmental behavior study. First, I would introduce a bit of the weaving structure, the bending active spatial grid system, grid shell system for freeform construction. Actually, freeform construction is a kind of a topic being explored by many scholars around the world for the past decade. And our idea is we're inspired by the traditional handicraft, the woven handicraft in Asian and in many other part of the world. But for this kind of woven handicraft, there are some limitations. It only applied to simple geometries, and it is difficult to be applied in construction of large scale and complex geometry. So our idea, we propose this weaving structure system. Actually, it is a bending active system, so it can be used for form finding by the continuous elastic rod. And also we developed a generative algorithm to adapt to all kinds of geometries to generate the woven grid. So it's a kind of adaptive system that can be used for many different geometries. So based on this system, we can construct complex minimum surface geometries and some dome geometries, and also this famous clean bottle, which is a very complex, kind of typical complex geometry. All of these are the models, but we try to build a large scale pavilions later. This is the geometrical principle of the weaving structure system. We try to make it like a evenly distributed weaving rods, and also we want to minimize the geodesic curvature of the rods. So for the figures below, the right one will be the ideal waving structure grid, but the left and the middle is not not so good. And with our algorithm, this is the first full-scale pavilion we built. It's like tunnel called waving spatial and time and spatial waving. Of course, for large-scale construction, we need to deal with the structural problem. So this is the simulation and comparison of the constructed model with our calculation. This is a very challenging project. We built a Mobius strip, which is with the diameter of 10 meters and height of 4 meters. This is very challenging because the Mobius strip is not an ideal structure prototype, but we use our elastic system to realize this complex geometry. And also, we try to incorporate this system with lighting. So this is the simple sphere we built in Tsinghua campus, and you can see it's 4 meter diameter, and it's very popular among the young students. Last year, we attended the ISS Innovative Lightweight Structure competition held in Barcelona, and we got a special mention award. And the comment is special mention for its construction tenacity and artistic expression. This work is a gyroid minimal surface with a diameter of 4 meters, but we only construct this geometry with GFRP rods of 4 millimeter diameter, and the total length of the rods is 1,200 meters, and the weight of the structure is 40 kilogram. We were awarded by the Ministry of Housing and Urban Rural Development of China, People's Republic of China, which is a very good award. And the most recent work, this is it's a kind of a lighting installation. We collaborate with the art school of Tsinghua University. It was located in Shanghai, in the central Shanghai, the Yuyuan Garden. Unfortunately, it is not there now, but you can see some videos of the work. So the whole structure was constructed by our waving structure system, and the weight of the structure is only 400 kilogram. So about the waving structure system, it's actually a digital fabrication system, but we don't use any numerical controlled machines, but use all uniform industrialized product, and all the joints are all standard, but it can be adaptive to different freeform construction. It is also a structure and architecture integrated system, which can be used for large-scale lightweight construction. And also it is environmental friendly because it's bending active, so all the joints and rods can be reused in different constructions. I will speed up a little bit. I will also, this is the second research interest. We use spatial temporal data analysis for people's behavior in architecture space. This is the traditional environmental behavior research that people try to collect data from on-site observation and investigation. And this is what we developed and we try to use through Wi-Fi, ultra-wideband sensors, and through video analysis. Some visualization of the data. And through the data analysis, we can show the spatial temporal changing of people's distribution. And we can also do analysis of the relationship of different areas in the shopping mall, which is quite interesting. Because actually, for some of the areas, they don't have positive correlation, but rather negative correlation. And we also did this kind of analysis in National Park Huangshan in China, and we can, through the data analysis, we can predict the people's flow for a certain day in the Huangshan area. And we also did analysis of the Hongqiao Airport T2 terminal through tens of billions of Wi-Fi records, and found some interesting correlation of people's behavior related to the schedule of the flights. And our third research interest is the design, generation, and cognition. And actually, I think it's a hardcore part of the digital architecture. And this is our early research that we try to do process analysis of interactive design, meaning the behavior of people when doing interaction with algorithms inside computer, and to try to review the process of how an design idea is evolved. Last 2 years ago, we published a paper using GAN, actually pix-to-pix HD, to generate and to recognize the floor plan of apartment. This paper was published on Acadia, and it shows the potential of the GAN and the CNN in understanding floor plan and in generation of floor plan. It's great to see that our work was further developed by some other scholars, such like the Stanislas Chilo in Harvard University. He developed this ArchiGAN system, which is widely recognized by people. In his website, it is mentioned that our work is the first to use the GAN in floor plan generation, and is very inspiring for his work. We also did style transfer research. This is the Tsinghua campus model on the left, and we generated through a CycleGAN algorithm to show a series of actually an animation. Every frame was generated by CycleGAN, but it turns out to be an animation of the virtual reality kind of virtual reality environment. Some of our recent progress, this called Embed GAN, and it is done by a master student in our lab, and he will present in the afternoon session. So my concept of our research is trying to help the researchers, architects, and the users to have better use and understanding of the architecture space, which is meaning that we try to use this human-computer integrated system to help people in understanding, in creation, and in appreciation. And here are some introduction of our session. The works of people that will be presented in this morning session. We have 8 very interesting and high quality research that will be presented in this morning session. First, we will have an interactive design interactive drawing system that will be inspiring in the early design stage, that will be presented by Kylie Stanfield from UC Berkeley. The second research is from Harvard University, which uses GAN for generation of urban planning. The third research is about analysis method for third place, which bring us a set of methods for measuring the third and visualizing the third place properties. The fourth research is very interesting. It tried to try to develop a 3D architecture space generation system with high precision and which can also combine two different design ideas. The fifth research is a interactive system, interactive screen and programs that can interact with people. And it also uses plenty of machine learning and natural language processing technologies. The sixth paper is about a sensing, integrated sensing toolkit, which can be a mobile urban sensing method which can collect dynamic and continuous data from the urban environment. The seventh paper is about a machine learning system that can be used in generation of structure form in architecture design, which also use GAN and CNN. And our last presentation will be a beam enhanced augmented reality system for construction, which is brought to us by shop architects, which is a very powerful and practical method. And after all of these presentations, we are going to have a kind of a 30 minutes panel discussion, and we will also invite all our presenters back to the stage and have some discussion and answer questions from the audience. So that's all for the my introduction of the panel, and so let's invite our first presenter, Kylie Stanford, Professor Kylie Stanford, to present your research. Please share your screen.
Hi. I need a visual indication that I can be heard. Can you guys hear me?
Yes,
okay?
Yeah, we can hear you very clearly.
Fantastic. And I'm going to be sharing my screen here on another computer. Let's see if this works. Oh dear, just one moment. I'm sorry. It looks like I've been logged out on my, there we go. So I'll be sharing my screen on a second computer. Let's see if that works. One last verification. You guys can see my screen? Just a thumbs up?
Yes, we can.
Fantastic. Thank you. Great. So hi, good morning, good afternoon, good evening. My name is Kyle Steinfeld. I'm an associate professor at University of California at Berkeley. A couple quick notes. All my slides for today are posted online at the URL that you see on your screen. And I also posted that in the chat window for anyone who would like to follow along. So there we go. So like many others today, I'll be talking about machine learning. I think it's a topic which is on our minds here in digital design. It's on our minds because this is a new approach to digital design, and no one's quite sure what changes this new technology will bring. No one's quite sure how to do with it. No one's quite sure what challenges and opportunities it might present. I just wanted to just kind of start with a position that I take while I'm interested in the opportunities that this technology holds for slightly improving or radically improving our existing tools. This body of research represents another interest, which is more about what entirely new forms of tools machine learning might enable us to engage with in digital design that perhaps fill in the gaps of things that have been kind of missing from digital design thus far. My talk today is going to center on the description of a single tool that we've developed. The tool is called Sketch2Pix. It's an interactive application for architectural sketching, augmented by automated image-to-image translation. So this is an augmented architectural drawing tool. So this is intended to support early stage design sketching, sketching by hand, but kind of augmented with the computer. That is integrates kind of automated image-to-image translation. So while in the paper, I detail the technologies, the workflows, the interfaces that enable novice creative authors to train and to wield custom-made image-to-image translation models in support of machine-augmented sketching. While I detail all of that in the paper, here I'm only going to cover that material in overview. And from the perspective of a user of the tool. Forgive me, I'm going to be recording the talk. I forgot to hit play. So I'm going to begin with a brief discussion of our motivation for the project, along with a description of some basic terms and the central mechanisms of the tool that are intended to support creative sketching. And at the end of the talk, if there's time, I'm actually going to attempt a live demo. So wish me luck on that. Okay, so first, a brief introduction. There we go. So we might observe that the intersection of recent advances in machine learning and architectural design tools remains a largely undefined territory. While it's clear that AI-based design tools present fresh challenges to the way that we understand and use software in the service of designing and building, the nature of these challenges and the character of the related opportunities are still uncertain. This project represents one step towards demonstrating an opportunity that we've identified and in bringing machine learning to bear on better supporting modes of reasoning that are central to creative design. So while broadly speaking, existing paradigms for design tools have been shown to effectively support what we might understand to be deductive reasoning, we assert that a new paradigm of design tool based on machine learning will be uniquely situated to address heretofore unsupported modes of reasoning about design, such as imagistic and inductive thinking. So this difference is clear from the intrinsic mechanisms of the tools involved if we look at them more carefully. So for example, while 3D modeling proceeds by composing geometric operations in sequence, and parametric modeling operates proceeds by assembling elaborate chains of logic in sequence, machine learning models operate entirely differently. They operate by matching patterns drawn from prior data. And as such, they imply a completely different mode of authorship for the designers that use them. So just as we'd expect an author to reason differently when wielding a tool of induction versus a tool of deduction, so for example, a charcoal pencil as opposed to a calculator, we would similarly expect entirely new cultures of design to emerge in response to this sort of paradigm shift in the nature of software. And our project anticipates exactly this. So the tool described here in this project is intended to be thoroughly inductive. We intend to support sketching. And the inductive nature of the tool is clear insofar as we first invite a designer who is using the tool, to define what we term an indexical relationship between a hand-drawn mark, a mark that they make with their hand, and the qualities of the image that mark is mapped to. And only after that indexical relationship is established do we ask the user to kind of find the quote-unquote reason for the images in the composition of a drawing. And this is largely how sketching operates. It's completely different than making a 3D model. This is how the artist Scott. In this way, the project seeks to anticipate new cultures of drawing practice that relies in relationship to this tool, and of course other tools that also take a similar approach. And from this, we hope to uncover new modalities of authorship latent and in this still emerging paradigm of computer-assisted design. A couple of terms to help guide us. In context of this tool, in the parlance established by the project, we understand a trained neural network that is ready for sketching. We term that a brush, right? So that's a neural network that's like trained up and situated and like ready for us to kind of draw together with. Similarly, we term the activation of a brush in the service of performing an image translation, either a transaction or an inference. And this is language that's drawn from computer science. A brief discussion, overview of the central mechanisms at work in this brush. So embedded in the brush itself is the central mechanism of augmented drawing activity. This is envisioned as a conversation, and you see an animation here of me using the brush. It's envisioned as a conversation, and it's expressed as a kind of graphic call and response. So first, a human author composes a drawing, makes a mark that may or may not adhere to some anticipated graphic convention. Next, this call image is passed to a neural net, which is trained to offer a response image, which is passed back to the sketching environment to be displayed to the author. If the results are not satisfactory, then the process can be repeated by modifying the original drawing. Changes can be made, or the author could choose to move on to a new portion of the sketch. So due to certain technical limitations of the current system, we're constrained to transacting only on images that are smaller than the typical size of most architectural sketches. And so for this reason, the transaction typically represents only a portion or a segment of a larger drawing. So what you see here, lots of transactions that kind of aggregate together to form a larger sort of sketch. So I'm pressing that button many, many times. Okay, so that's the basic sort of mechanism of the project. A quick thank you to the students at UC Berkeley. So the research was closely related to an upper division undergraduate research studio offered in the spring of 2020. Here's my list of students. They're an extraordinarily inspiring and resilient bunch. So now I'd like to talk about, in a very quick overview, the specific tools, methods, and workflows that constitute the Sketch-to-Pix augmented drawing tool. And since most of the technical details are already covered in the paper, I'm just going to speak solely to the experience of the user. So I'm imagining that you're a person who would like to make their own augmented drawing partner. And if that's so, then these 4 steps are required. So first, we establish a kind of training data set. And it's important to note that the user is responsible for that. I don't provide brushes, kind of inbuilt the way Photoshop does. It's up to the user to define these things for themselves. That's a part of the authorial act, is to define the training set for the brush. So for us, data sets are derived from a combination of 3D scanning to get a digital model and texture modeling. And there are some scripts associated with that. Second is the training and validation of a neural network. This is the kind of very techie stuff that we want to mainly hide from novice users. It's done through a GPU cloud computing environment, and it's supported again by a collection of sort of user-friendly scripts. Third is the deploying of this trained model to allow communication with whatever graphic sketching environment is being used, and for us that's Photoshop. And then fourth is the configuration and the customization of the sketching environment to best facilitate a conversation with an AI partner. So I'll take these kind of very quickly, one at a time. The most critical step, really, in crafting a Sketch-to-Pix brush is the conceptualization and the establishment of a data set on which to train, something that might be kind of overlooked. So here, these are kind of toy examples that we developed, as samples. So here, the central operation of a brush is established through the 3D modeling and texture modeling of a digital model. So embedded in this 3D model is already the kind of mapping between a graphic call by a human author and the desired image, quote, response of the neural network. So here we can see that at work. This is our sample bowling pin. On the left are samples of our training set. So we render the 3D digital model with colors and textures, and we map that onto another kind of rendering, which is meant to kind of simulate a human sketch. It's a line that describes edges and a kind of gray fill. And that's enough for the Pix-to-Pix model to pick up on the right kind of relationship. On the right here, you see me sketching with a brush that was trained in this way. So the reason for using a 3D model data set is because we need a data set that is sufficiently large to train upon, which is quite big. And so by taking many views of the 3D model, we can achieve that. So step 2 is the training and validating of a neural network. And again, we do this on a kind of cloud computing environment. And this is because most novice designers lack direct access to the computing resources and the expertise necessary to complete this training in a reasonable amount of time. So we provided resources for this. And so these are novice undergraduate students of design that are able to kind of click through something like a Google Colab notebook well enough to train their own brushes sort of by themselves. Third, there's the deploying of this model once trained to an environment in which it can communicate with a kind of graphic sketching environment. So something that kind of facilitates the connection between these two things. And while in the recent past, such a step would present considerable difficulty and quite a bit of software development to achieve, and would be impossible for a novice user, recently there's been introduced a kind of pieces of software or really services that provide model hosting and distribution. And that has significantly eased this burden and lowered barriers of entry in important ways. So given a service such as this, we're using Runway ML. This is a relatively trivial process from the user's perspective. Finally, there's the interactive sketching component of the work, where the model is deployed to the hosting and distribution service, and we need to define the mechanisms of interacting with this model, which might now be regarded as a kind of functional drawing assistant at this point. So the details of this collaborative drawing activity are largely guided by the features of the interface developed for the given graphic sketching environment. And a large amount of development time was spent sort of noodling around, trying to get Adobe Photoshop to interact well with this hosted model, to get the kind of human-computer interface of that right. I would just note here that how to best structure a successful interaction with an AI assistant, that's actually a topic of like current research in HCI circles. And it's important to our fields as well. So from this perspective, we take the position of strongly valuing the iterative development of small-scale graphics in the service of larger compositions. This is because in our view, the ease of iteration is essential to facilitating the feeling of a conversation with an AI partner. I see that I have about a minute left, so I'm going to try a very, very quick live demonstration if I can. So here's Runway that's currently running on my computer. This is where a model is hosted. Right now I have a model being served up that was trained on images and forms of plaster blobs. And over here I have Photoshop. I have to minimize that. And in the Photoshop environment, I'm sketching with my mouse, so please forgive my bad drawings. I can draw here on a layer and fill that in with this predefined kind of gray color to give the computer a hint as to what I want. And then I push this button in the upper right called Abracadabra. And if I glance over at Runway, you'll see that it should be receiving. It is not receiving. It's not running. I forgot to start it. I'm starting it now. So it will receive the message from Photoshop. Let's try that again, and then send back a reply. Abracadabra once more. Go talk to Runway. It happened. Voila! Sketching, interactive sketching with Photoshop and machine learning models. Let's just change it and push Abracadabra again and watch it from this side. So there, it's tried to put the colors and textures of a kind of plaster model in my Photoshop document. Fantastic. So very quickly to wrap up. So sketching. This is an activity that we see as a special case of inductive design thinking. Two quick observations. One is a reminder of the central role of iteration in design. I don't think I have to highlight that again. But second is an indication of the sorts of challenges that lie ahead in the shift from geometric and logical modeling activities to those that are required by machine learning or CAD software based on machine learning. We see such a challenge in the role that the 3D models that were here in the service of training. And we're looking at student authored sketches here. So here there's a shift in the representational role that these models play from a kind of directly representational role where the model stands in for a building that we envision to a kind of loosely indexical role where the model defines the relationships and patterns to be learned by a neural network, which prefers information such as colors and patterns over forms and organizations. We expect, so this is one example of a kind of challenge where we expect to find many, many more such differences between traditional forms of computer-aided design and the emerging forms that are based on machine learning. And that wraps it up. Thank you very much.
Thank you, Kelly. It's very interesting research. I can see that it's very intuitive, and also the method of interaction is very convenient. And also you use the Photoshop as an interface. It's very I think it's very smart idea to use all the tools inside Photoshop for interaction. Also, the process can also be integrated with the creative design process. Thank you very much. But actually, I would like to. We wish to have some questions, but we're a little bit behind the schedule. So I think maybe we can leave the questions until the discussion, roundtable discussion session.
Right on. That sounds good. Thanks.
Yeah, thank you very much. Thank you very much. And let's proceed to the next presentation. Actually, for each presentation, we have 50 minutes. So if the authors and the presenter can finish within like 12 minutes, we can have some simple questions. Yeah. So our next presentation comes from Harvard University, Tian Runjia, I think it's the Chinese pronunciation, sorry. Suggestive site plan with conditional gain and urban GIS data.
Yeah. Thank you, Professor Huang. Dear professors, guest speakers, and Digital Future Team 2020 and audience of CDRF 2020. Good morning, good afternoon, good evening. I'm Runjia Tian, current Master in Design Studies student at Harvard University Graduate School of Design. Today, I'm honored to join the International Festival for Computational Design and Robotic Fabrication and sharing ideas and inspirations and present my recent research. Suggestive site planning with conditional gain and urban GIS data. So first, site planning. Site planning has been a crucial stage in the design process of architecture, landscape architecture, and urban design. In 1984, Kim Lynch formalized the idea of site planning as the art of arranging buildings and other structures on the land in harmony with each other. Therefore, the primary goal for site planning refers to the generation and organizational process of site layout. A foundational step for site planning is the design of building layout across the site. There have been various attempts through the past years in the AEC industry to automate the site planning process. However, most approaches takes algorithm-based approach, as this process is hard to automate due to its multimodal nature. It takes in multiple constraints, such as the street orientation, program, density, plantation, and most importantly, the geometric shape of the street block. Next page, yeah. And with the advancement of geographical information system, which is a framework for gathering, managing, and analyzing geospatial data, and the abundance of open source GIS database, there has been like great improvement for building site planning related machine learning models. However, canonicization, standardization, and augmentation are required for feature engineering, since the existing GIS data are not ready for deep learning purposes. On related works, in 2014, Ian Goodfellow proposed the structure of a generative adversarial network. In the paper, he proposed the use of two multi-layer perceptrons, a generator and a discriminator, to generate data and classify as true or false based on the training data. The training is concluded until the two network reaches an equilibrium. This had triggered a boom of generative models based on the GAN structure in recent years' researches. In November 2014, researchers proposed conditional GAN to generate descriptive text which are not part of the training labels. And more recently, in 2018, Philip Isola and other researchers proposed the pix-to-pix, well-recognized image-to-image transformation with their model based on the conditional GAN in 2018. The condition, which is an image with identical size, is concatenated with the Gaussian noise at the input to the generator, and concatenated again to the generated output as a discriminator input. Since then, the pix-to-pix model offers great accessibility for designers and has been proved effective in multiple scenarios, including texture filling for sketches and generating architecture plan layouts. In 2019, Harvard graduate Stanis proposed ArchiGAN. It generates deep stack for apartment building design in his thesis. The work of Stanis laid foundation for practical generation of building footprints based on the parcel shape. However, his thesis is limited to apartment plan generation and does not incorporate into the complicated situation of urban and landscape features for site planning. So with the abundance of GIS data, the existing urban environment proves a practical data set for modeling and automation this design process with statistical learning approach. The researcher proposed a prototypical and extensive framework to generate building footprints as master plans references for architects, landscape architects, and urban designers by learning from the existing built environment with artificial neural network. The overall project pipeline of the creative design tool can be divided into 3 parts. The first part is the early exploratory data analysis, including data acquisition and wrangling. The second part, including the building artificial neural network and training in TensorFlow framework. And the third part is the visualization in 3D modeling software environment. We take rhinoceros and rhino and grasshopper, for example, in this showcase. Specifically, a dataset containing necessary information is collected from open source GIS data from the city of Boston and wrangled with geospatial analysis libraries in Python. And the pixel-based conditional gain is used in this process to learn the mapping from a block boundary to a urban fabric pattern that contains color-coded programs information. And the result is visualized in Rhino for generating set plans interactively in real time. So the data acquisition, the data for training the generative model is obtained from the OpenGIS portal. And we aggregate 19,000 building data, 8,000 street block data, and 200,000 street block data from the Open Data portal. And each object in the dataset has a GeoJSON geometry that indicates the absolute geographical location for the object, which we use for further spatial drawing and merging. And the data wrangling consists of 2 parts, spatial joining and feature engineering. The spatial joining is accomplished in ArcGIS Pro environment to speed up the geospatial data merging algorithm. And the researcher also split the dataset by parcel data so that we could back the building to the closest street parcel that contains the building geometry so that we can use for further generation. And the data wrangling consists, data wrangling is processed in Python and Anaconda. So after this step, the buildings with the same parcel is stored in the same tabular data frame object while maintaining the statistical numeric features such as elevation, building height, and the land price, and more importantly, the program. Feature engineering is accomplished in Anaconda to calculate important design metrics such as coverage rate, plantation rate, and floor area ratio, which could be used for further work. Color coding and rasterization. After the feature engineering, we can easily perform spatial queries, such as spatial joins, and overlays geospatial features on top of each other according to selection metrics. The joint matrix is stored in Shapley geometry format, and we'll work with the geometry files, parse and aggregate in this step as our cornerstone. This research used the program metric as a showcase for the research, and similar approaches could be applied in similar ways to other features such as height, price, and plantation. For the program, each building in the set is color coded with a particular RGB value according to the categorical program feature in the dataset, and the color map maximizes the differences between various categories. To prepare a dataset ready for the pixel-pix training, we need to prepare a dataset composed of training image and predicted image. Again, for building reliable conditional gain network. Taking in the outline representation of the site boundary, the GAN model generates suggested building layouts. It's essentially a segmentation task. So a pair of pixel-wise multi-class cross-entropy loss is added to compare the ground truth and the set plan. And meanwhile, a discriminator takes in the generated image and predicts whether it's true or false. In training and validation, the model is trained in TensorFlow 2.1 framework with NVIDIA GPU acceleration. And the training data consists of 4,400 pairs of block boundaries and ground truth set plans, and 400 validation data. And here are some of the immediate results of the training process. Yes, you can see the Yeah, at first the building tends to be like in the same block. We'll begin to show different programs as the training progress. And next page. Yeah, and using the similar tools as Dennis did in 2019, they also developed like a similar interface based on the p5.js framework that could be used as a design assistance tools for generating the set plan based on the given boundary. And this is a very prototypical early results. And more advanced and mature results will be shown in the later page in 3D environments. So to visualize the results in a better way, we use Flux Python server to connect the TensorFlow model and Rhinoceros Grasshopper, so that the results could directly be visualized in 3D environment. And the various colors encoded in the same way as the training data, so that you could see that the neural network is predicting the building of a variable program according to the building block data. And the author also compares the performances of various input boundaries, and it seems that the boundaries with the quadratic boundaries are have the optimal performance. This is partially according to the analysis. This may be due to the fact that most city blocks in Boston are on the quadrilateral shape, and in future work, this aspect might be further enhanced with data augmentation and data rebalancing. And currently, the head of the building data is unified to the average of the data set. And future work will improve this feature with regression networks such as multi-layer perceptrons, or adding different stacks of generative models on top of the existing model. And some extended use of the model, including city style transfer. So the generator essentially maps the specific urban fabric data pattern to a city in our case. So to extend the model, we could apply the generative model to a different city and compare the results of the predicted result to the existing urban environment. In this test case, we develop a city style transfer interface that takes the urban parcel's input and output the urban fabric. Thus we'll be able to test how the urban fabric of one city could be overlapped and juxtaposed onto another city. And there are still aspects of this model that could be further improved. And one aspect is to add more features to the data, such as elevation data and other numeric data, such as coverage rate and floor area ratio, because we all have this data in the data frame. And other optimization of measures, including optimization of the network structures, for example, using variation autoencoders for increasing the diversity of the generated model. And this could be very useful for a nonlinear dimensionality reduction tool for encoding the multimodal feature into the model. And about the anticipated impact of the project, the project might have impact for urban planners and urban designers, especially during the stage of concept design and massing studies. And the generated data could be further combined with property value to display economic impact of urban design project. And the project also could impact real estate industry, such as fast prototyping design iterations at the early stage of real estate financing project that involves complex set planning. And ultimately, the project will improve public engagement in urban planning and design, encouraging participants in public project decision by displaying potential impact of the project to the existing urban neighborhood and community. And in the end, I would like to express my sincere gratitude for Professor Kelly Mueller, Dr. Arnaud Dev from MIT, and Ms. Caroline Scatbo from SpaceMaker for supporting my research. And thank you for watching. That's all. Thank you.
Thank you, Tian. It's a very interesting presentation. We still have 1 minute, so if any, I would like to ask if any presenters from our meeting room have any questions to the presentation of Renjia Tian. Any question? Okay, I have one question. Actually, you used the GAN for the generation of urban planning for a kind of certain block of a city, but for each block of the city, it is not isolated from the urban context, but the Pix emphasize the boundary geometry, the shape of the block, and so do you have any consideration of the information from the surrounding urban context, or do you have any kind of idea in your future study how to integrate this kind of information in your system?
Yeah, that's a really great question. Yeah, because during my research progress, I also think that this could be a problem for using the pix-to-pix form like isolated mode. But I think with the recent progress of graph convolutional neural network, we could maybe encode more information of the context instead of like fixing on this one image to image translation. So yeah, in the future work, so in the optimization part, I also included the improvement of network structure that could potentially impact the performance of model or take more engineering into consideration. Yeah.
Yeah, thank you.
Thank you, Professor.
Thank you. It's very interesting. And let's go to our next presentation. It's from NJ Studio from USA, Namjun Lee. The topic of the presentation, the title of the paper is Understanding and Analyzing the Characteristics of the Third Place in Urban Design Methodology for Discrete and Continuous Data in Environmental Design. Please share your screen.
Sorry, Professor Huang. The third presenter, Namjun Lee, he misunderstood the time, so he become the last presenter in this session, and the next presenter could be forward. Is that okay? And we have
sure. Let's shift to the sequence. So our next presentation will come from the University of Pennsylvania, from Han Zhang and Ye Huang, machine learning aided 2D to 3D architecture form finding at high resolution. Please share your screen.
Hello, can you hear me?
Yes.
All right. So hello, everyone. My name is Han, and I'm honored here to give you guys a presentation of our work. So our work is basically we're trying to do the form finding at a high resolution from the 2D to 3D. So our main goal is like we're trying to do the form finding from the architectural styles, from style A and style B. We're trying to find out what's going to be happen from architectural style A, like take this, for example, the seating opera, and to the next one, the style B, the Gothic church. So what will going to happen in their intermediate state? And then we're trying to find out this state to have some innovative design. And we're trying to do this from 2D to 3D, because basically this is going to make our project gather a much higher resolution. So compared to the related work, all of these three works are the similar projects that they try to do the form finding from like the object 1 to object B. But the difference is we try to do the form finding directly happen on the 3-dimensional model. So this is like they got the 3D point cloud or the 3D voxels, but their resolution, or let's say their dimension, is extremely limited. So for our project, we got a much higher resolution. Like for this one, our results got the 1024 by 1024 by 64 resolutions. So compared to the previous one, we got like at least 256 times larger compared to the previous one. And our method is like we try to do this from 2D to 3D. So you guys can see on the right, this on the right is our 2D results. So on our 2D layout, we got like more than 8K pixels. And how are we gonna do this? So this is our main process. Firstly, we try to slicing the 3D model by a series of the 2D image stocks, and then try to lay out them on the 2D graph, and then try to train them on the machine learning algorithms, and then decompose them and compose them to finally get our final 3D form. So we typically use the StyleGAN system to train our model. The reason why we choose this is like the StyleGAN is really talented on to generating some similar big images or style mixing images, and also the truncation trick images. So you guys can see on the bottom, this is an example of the truncation trick images. So this feature will give the continuously shift from style A to style B. Like this one is from the urban style to the forest style. And we think we can utilize this method to help us to do the form finding. Firstly, the 2D-dimensional model, and then to combine them and compose them on the 3D. So this is our layer slicing method. Our method is a little bit different compared to the traditional architectural section drawings. This, like, each of the layers will only contain their own information rather than just compared to the traditional section drawings. They will have their background, they have all of the section drawings features. But here, like for this example and this example, they only got the information on their own layers. And this is our 3D model input. So we typically choose the sex inputs. We want to make our input, like each of them will gonna be unique and will significantly different from the others. They all have their own unique types and styles. And we also add one more step to reverse the compiling to make sure that the model scale is right. Because while we're just doing this layer slice method, our model is always not on the same scale. So after we training the whole system, the geometry gonna be really weird. So we add the steps to make sure each of the model will on their own right scales and positions. So this is our process snapshot. We try to train this on the 2D graph of the StyleGAN. And we then finally find out that we did not have to train the whole epochs that suggested by the StyleGAN group. Because basically our goal is to try to train the whole system from 0 to 1 by 1 pixels to pixels, which means like we can see on the top row, this is in the middle process of the training, and the bottom row is the final one. So we think if we just try to reach from the top to the bottom, and this is going to be okay, and this will save us quite a lot of times, because if we just train the whole systems to as suggested by the StyleGAN group, then the whole training time will gonna be it will depend on your hardware devices, but it will take at least 6 days. But for our choice, this will gonna only take like 2 or 1.5 days. So this is our final results. Our results, like we trying to find out the intermediate state of the styles from A to B, and you can see there are quite lots of relatively success examples from style A to style B, and we try to think how can we utilize the models in between, like this one or this one, to get some innovative architectural designs that they're gonna combine the two features, the two styles from these two famous buildings. And we also got like a more complex process of this network, because basically our network is trained on let's see the previous one. Our results is only got the 64 layers, and we think maybe we're gonna find a way to get more layers of this architecture model. So during this multi-level process, we got the first step is like we tried to slicing this model with 2 series of images. The first one is 1024 by 64 pixels images, and the next one is 1024 by 1024. The reason why we do this is because we want to make the TD layout 4 times larger compared to the previous one. So our layers will not be 64 but 256, 254, 256. But for this situation, each of the single layers information is only gathered 64 by 64. So this is totally not enough. So after the training process, we try to use the Y-2 plus. This one, this is the image enlarger AI algorithm. So this will make the images 8 times larger compared to the previous one. But this one will also got the limits. Like we can tell this is 64 by 64. And while we try to enlarge this one to the image C, the whole geometry is not so clear because this results requires more details, but the details within the images is lost. So what we try to do is like we want to have the second method to help to gain the details back. So we try to get this large and this enlarged image is at the same resolution as this one, but this one, this 1024 one has much more details compared to the previous one. So we try to train them through the pixel to pixel and try to find out the logic from the less pixels, from less details to the more details, and then we turn it back to make this result and to generate the details back through this network. And this is our multi-network process. The A is the 64 by 64, the B is the 1024 by 1024. And while we just enlarge this one to 1024 images, we try to train this one and get the pixel-to-pixel model, and then turn it back to get the model return. But this method also got their limitations, like because we have been through quite a lot of networks, and during the whole process, there are gonna be really a lot of the noises inside. So we think this method is not mature, but we think this method is interesting, so we put it here. And we think we're gonna try to improve the whole process and make there is less noise and the better results. So this is our project. Thanks.
Thank you very much. I think it's a very intuitive research to challenge the generation of 3D models because the 2D, a lot of researchers has done a lot of works on 2D, but the 3D performance is still limited. So you are trying to challenge the limitation, this kind of a very difficult problem. And I think the performance is quite good. And yeah, let me ask if any questions from our audience in this meeting room for the research of John. Okay, I have one question. You try to do the slices or the sections of the 3D model and try to generate through these sections, generate the 3D model through these sections. So do you have any experience or preference of the direction of the slices? For example, if it is not left to right, is front to back, or it is from bottom to top, what will happen? Or if you have any suggestions or any anticipations of this change?
So basically, while we're doing this project, we try to do multiple ways. Like we tried from the bottom to the top, we tried from the left to right. And then we find out that the best results is come from the section cut, not like the plan cut. Because then we think it's a reason that there gotta be quite a lot of information and details within the section cut compared to the plan cut. And I think the section cut is much more easy to understand by us and also by computer rather than the plan count. So then all of our project is based on the section one, not the plan one.
Yeah, thank you.
Right, thank you.
Yeah, thank you. Thank you very much. Yeah, we still have a time for one more question, if any questions from our audience.
Probably I have one question. As we all know, the pixel to pixel is, I think in the style GAN or the other GAN algorithm, it's really need a really big training database. So is there any benefits of to use your methodology, actually not only the orientation of this kind of sectional cutting direction, but also I think the resolution really matters, right? Is there any special optimization process you deploy in the process to reduce the training database or make it more efficient, more smart ways or intelligent ways to the pixel-to-pixel methodology? So is there, I mean, the special process of your tools, is there any simplification to the training time or the training database?
I think this question is related to our parameters configurations, like what is the batch size and how we try to configure all of the training process. While we try this quite a lot of times, we think the best solution is like trying to train this on the relatively not little but not that much the database. Like we try to train this on the 2000 and the 8000 and also more than 20,000, and we think maybe the data size is like nearly 2K or 4K is enough. Because while we got this too much, and the whole training process is gonna be really time consuming. So while we do this like a few hundred of the data, and the results it sucks. So we think maybe the 2K or 3K input is the best choice, I think.
Thank you, John. Thank you very much. And I think yeah, let's proceed to the next presentation. It's from the Woodbury University from the United States, from Anna Harunzo and Nikita Pashenkov. The topic is collection to creation, playful interpreting the classic with contemporary tools. The authors cannot attend the conference, but they recorded their presentation. Our assistant will help to play the recorded presentation. Please.
Called Collection to Creation, playfully interpreting the classics with contemporary tools. This is a project that Nikita and I developed within a pedagogical environment at Woodbury University for an event at the Getty Museum called College Night, where we were invited by the museum to create a piece that focused on human emotions, and in some way find ways to relate it to the museum's art collection. So I will be detailing more of the background of the overall process that happened at the university, and how we managed to combine different classes, and how we worked with the students on ideating and creating, and then deploying an installation that merged the use of artificial intelligence with the creation, with interactivity with users, and the creation of a lot of different content based of the users that that experienced the installation, and also how we found a way to link it to the actual museum's collection. So the piece is called WYSIWYG. It's what I see is what you get, and the idea is that we created a piece that is actually looking at the users, and depending on what this piece sees, it changes, and the content dynamically changes depending on the information that the piece is seeing, and also it creates a series of text descriptions describing the piece using AI and using a database that the students created from the Getty's collection. So as I mentioned before, this project was developed within an academic environment at Woodbury University as part of the Applied Computer Science Media Arts program. Which is a hybrid degree in art and technology, but highly technical as well. So our program was invited by the Getty Museum to decide to create an interactive and experiential installation for this college night event. So some of the constraint that we were faced with was, one, how can we find ways to address human emotions? How can we link it to the museum's collection? And then how can we fit it within the classes that were already being taught in the spring of 2019? So we found that we had two classes that worked best, were the media environments class that works on designing experiential projects at a human scale environment, and then with our artificial intelligence class, we could use this is an opportunity to address artificial intelligence in an applied environment, which is part of the core missions of our program, working in applied environments. So as I mentioned before, we proposed the design of development of an installation that creates live interactive visuals and accompanied by machine learning titles and text descriptions generated from the user's interactions, or what the installation was actually looking at and seeing. These are some images of the outcome of the exhibition and displayed at the Getty Museum, and how, as you can see, the machine is like grabbing the silhouettes. The installation is grabbing the silhouettes of the users and creating different graphics that were all designed and created by the students, and actually then creates a description of what this piece is with a title in the description. All of this is happening dynamically. And each time with different users, depending on their age, their gender, their emotions, the colors and the graphics displayed would be different. So I'm going to go into describing the installation itself. And so the installation consisted in 3 large screens that were connected with each other, and we had a Kinect camera on the top that we were able to extract the human silhouettes and other data from it, and then we had another camera that was working with computer vision algorithms to grab the information from the other information from the users. This is some diagrams of the piece itself, assistance diagram of how the hardware was working, and through the camera that was using computer vision data, using deep learning models, we were able to obtain the number of people, approximate ages, facial expressions, estimated genders. So some moments at the Getty Museum where we're setting up the installation. You can see some of snippets of the code that we're working with. And so the visual content that we created consisted there were 4 different elements. One, the silhouettes of the user that really helped the users identify themselves and find, and it created like a really strong bond in forms of interactivity, since it really appealed to the users to suddenly see themselves reflected as a mirror. And another part would be the scenes that were actually created, the real-time graphical scenes and animations. Those were generated by the students, and they all had different color palettes that would be applied to them depending on the facial expressions that the user were doing. So, and we would usually never find the same graphics during the full exhibition and multiple interactions with the piece. Never one frame that the piece was displaying was the same overall. The overall project was always changing and evolving. These are some inspirations that the students used to start creating their graphics and real-time generated content, and the color palettes that I mentioned before. What we did is we assigned different color palettes to a different emotion. And as soon as that facial expression that corresponded with that emotion was recognized, then these color palettes would be applied to the piece. As you can see, we have, joy, sad, anger, fear. These are a collection of examples of different interactions, and with different text descriptions, as you see that are generated dynamically. As you see, all the graphics are completely different depending on the users or that are in front of the piece. The students were also interested in I realize I'm running out of time, so I'm just going to skip through this extra part, and I would like to focus pretty fast on some of the language models that we use for all the title and text generation. So as I mentioned before, so I've mentioned quite briefly, usually art pieces are accompanied by text descriptions, and all of the art pieces of the Getty Museum are accompanied by a text description as well, and a title. So what we wanted to do, since all these graphics were generated dynamically, we wanted to dynamically generate a new title and a new description each time some users approach. And this was our main part, that was how we addressed the constraint of linking our installation to the Getty's collection. So what we did is we visited the Getty Museum multiple times, and we had some presentations from the Getty education specialist. And what we did is we focused on looking at and screening all art pieces that portrayed humans in it. And all the students went through the whole Getty collection, and they started at grabbing all of these parameters from each one of these pieces. So the title, the artist, the date, the description, and the number of people, the gender, their age, their emotions, and the image of it. That's how we created this database. So using this database, and for example, here's one of the Bexel and one of the pieces that we used from the Getty. That shows a really strong expression. And this is images of the database that the students created. And so we use this language model that was actually released in February, GP2, 2 months before the deployment of the installation. And it's a language model that is able to reproduce text with and create text from a limited amount of with a prompt, as you see here is an example system prompt, and what like the amount of large text, coherent text that it can generate by a small prompt. So the idea what we fed into this algorithm would be like 2 people, happy, 26-year-old, and then going through the whole. After we fed it the whole database from that the students created based on the Getty's museum art collection, it would generate a different prompt, a different text description. The examples of the different prompts and titles that were generated depending on the users that were interacting with the screen. one thing that was interesting was that most of the descriptions and titles have to do with religious themes or mythology, and that has to do with most of the collection of the Getty belongs to medieval times and has a lot of religious themes. So in order for further iterations of this project, we believe that working with a larger database that is closer to what the databases that are used for these type of algorithms, it would really help to get a larger variety within the text and the titles that were generated for the pieces. One of the really important aspects of the project was the user experience. We believe that it was very successful, and the students and the professors, we worked really hard on designing an iteration and the timing of the piece that would work really in a really fluent way and familiar way with the users of the piece. So the users would enter, and the piece would have different stages that would guide the users from the beginning to the end of the experience. And here's some of the credits of all the students that worked in the project. And we believe this project was highly successful in many ways. One of them that the level of interaction with the users was really high. We had multiple pretty large audience experience the piece throughout the event and engage with the piece a lot. And also, it was the piece fulfilled pedagogically a lot of the learning outcomes of the classes, and the students had also an opportunity to work with a worldwide, well-renowned art institution, which was really fulfilling for them. And so one of the most important parts of how we from this project is trying to find ways to connect the existing art collection with our project, and are addressing all these learning outcomes at the same time. And we believe that we managed to do this very successfully in a really fulfilling way, and working with the latest technologies, and also getting to work with artificial intelligence and creating a piece that was constantly alive and constantly changing over time and depending on the users that were using it. We have a GitHub repository that you can visit with all the information from the piece, and you can download it and install. All the code is there. And if you have any questions, feel free to reach out to us. We are Anna.
So I think the presentation has finished, and although the author is not here to interact with our audience, I believe with all this advancement in the development in the hardware and the algorithms and all our research, this kind of interactive environment will be more and more popular and will be a very important direction in our research. Okay, let's proceed to our next presentation from Princeton University, from Maida Laugono Moni Texa and Ellie Bonzaid, Sensing the Environment Neighborhood Mobile Urban Sensing Technology for High Spatial Resolution Urban Environment Mapping. Please share your screen. We cannot hear you. Please open your microphone.
Is it working now? Hello?
Yes.
Yes. Okay. Okay, let me move this here. So well, first of all, hello everybody. It's a pleasure to be part of this amazing event. So I'll be presenting our paper, as you mentioned, on sensing the environmental neighborhoods. I'm Maider Jaguno Municha, and this was done in collaboration with Professor Eli Buse at Princeton University. We are becoming increasingly aware, especially in the recent few years, that concentration level, the air contaminant concentration levels in cities vary at very fine spatial resolutions. For example, if you take a street canyon, there can be a 6 times a higher concentration in a corner versus another corner of the very same street. We've also very recently learned that environmental neighborhoods, that is the areas that affect the environmental quality at a given point in a city, range between 200 and maximum 1,000 meters. So these are very fine scales that, for example, if we look at New York City and we see what are the Environmental Protection Agency official regulatory stations in the city, we see that they are very scattered. So with this spatial resolution of environmental data acquisition, we cannot really understand what is happening in the city. And so we cannot reach conclusions that are going to be useful for architecture and urban planning processes. So what we've been working on is on the development of mobile urban sensing technology, which we called MAST, to capture environmental data to high spatiotemporal resolutions, to see what is happening, what I was referring to at that neighborhood scale, to see what's happening at the street and the neighborhood scale. And MAST are customized sensing kits that can be coupled to any vehicle, any mobile platform, as those that I'm showing in the image, can be any buses, any trucks, any trams. And they contain sensors for humidity, temperature, particulate matter, CO2, NO2, ozone, carbon monoxide. And we also couple an infrared camera. And of course, all the data is going to be geotagged through a GPS. And through cellular connectivity, we send the data over to an online server, which we then access through mobile applications and web applications. So prior iterations of this work, the first installation was done in 2017 in the city of Seoul as part of the Seoul Architecture and Urbanism Biennale. The sensing kits, a prior version of the sensing kits were coupled to the inner bus network in the city center of Seoul, and we're mapping the air quality for approximately a month during the summer of 2017. Also in New York City in 2018, in this case coupled to onto private vehicles, we mapped part of the city. And so we question now in the last year and a half, we've been looking into really understanding what are the challenges looking forward for mobile and urban sensing technologies. And the main issue is that there is no really design criteria established for low-cost mobile sensing technologies to affordably and accurately characterize environmental gradients at the neighborhood scale. So we've been looking into the design approaches to define these strategies for the sensing kit that is focusing, for example, on the resilience over adverse weather conditions, that is preventing the sensing kit from overheating and protecting it from heavy rainfall. So taking into account the provision of sufficient air exchanges to enable fast response data acquisition. This is very critical because even if we use fast response sensors, unless the sensing kit itself, the mechanical design of the sensing kit doesn't enable this fast responsiveness, then we are not going to be able to capture the neighborhood scale air quality gradients. Also, affordability is very important to us to enable an scalable project. And another important issue is the power and deployment autonomy, so that we could really develop opportunistic sensing, so that the mass sensing kits could be coupled to any mobile platform with no dedicated experimental campaign design. So this is the last version of the mass sensing kit that we are using now. I'm highlighting here the sensing chamber. So there is an area inside the box that is exposed directly to the incoming airflow. This is the band that you see with the number 1. And all the sensing heads are facing this area, which is directly exposed to the main airflow. If you think about it, this kind of the vehicle is moving in this direction. Then there is an inner chamber that is contained within this kind of plexi walls inside the sensing box, where all the kind of main electronics are located, and this area is most protected from the weather, from the rain, so that we make sure that water doesn't get inside. And then ranging from number 3 to number 8, all the sensors would go CO2, the inlet of the particulate matter sensor, the temperature and humidity sensor, NO2, ozone, and carbon monoxide sensor for number 8. And then we have the solar panel, so that the box is autonomous, so that it is not relying on any other power supply. There is a ventilation gap under the solar panel, because we found that in previous versions these were touching, but there was an overheating problem. And by doing so, we enabled the ventilation between the solar panel and the sensing kit. And then the waterproof cap with the waterproof locks, and the perforated envelope that has an over 30% perforation to enable sufficient air exchange inside, and the magnetic legs for an easy deployment on any vehicle. And again, there's a ventilation gap under the box to prevent it from overheating. So we developed box studies. The reason for this, again, is to guarantee that there is sufficient air exchanges to make sure that we can really capture the data at fine spatial resolutions. So what you see on the left is just like the setup within the Princeton University instructional wind tunnel. And on the top row on the right, you see a setup where, in this case, the fog emitter was situated right under the sensing chamber, so that sensing chamber is full of smoke. And then we turn on the wind tunnel and we see how fast that fog, sorry, not smoke, is evacuated. And on the bottom row, on the other hand, we see that the nozzles with the fog are outside the box. And in this case, we are looking into how quickly that sensing chamber is full with smoke. And then we turn on the wind tunnel and we see how fast that smoke is taken out. So just a short video of this second nozzle version. You see how the nozzles are, it jumped quickly, must be a zoom thing, but basically we were looking at how fast that sensing chamber is full of smoke. Now the wind tunnel is gonna turn on, and you see how fast that's clear. That was tested with and without sensors, with different incoming wind velocities, but basically in the wind tunnel, pretty much the wind velocity was 1 meter per second. And of course, if you think about mobile vehicles, that's going to be much more. So the air exchanges are going to be much faster than what we are seeing here. So we consider that these were definitely sufficient for the scales that we wanted to capture. The mass sensing kits were calibrated against reference EPA air quality stations. In this case, this one you see on the left, located at Rutgers University campus, and also in the Environmental Fluid Dynamics Laboratory at Princeton University, and also through cross calibration, so comparing one box against another box. That's well, before I change to the next slide. And here in the table, you can see that we were using readily available sensors. Again, fast response readily available sensors. We are looking at the sampling frequency of the sensors and the equipment we used for calibration. And after, of course, the calibration was performed, then the acquisition data was recalibrated to make sure that it was okay. So this is a campaign we did right before the case study I'm going to show in a second, that we use to test the cross calibration. Again, all of what I'm going to show today is in Princeton University. So the boxes were placed one next to each other over a private vehicle, and as you can see in the plots, the data was compared to see whether what kind of to see kind of the behavior of the boxes in parallel for cross calibration purposes. Right after we finished the lab, the EPA against EPA station and cross calibration campaign, we deployed the sensing boxes on the Princeton University mailing and printing service logistic vans during the summer of 2019 for the duration of, again, approximately a month. And in every measuring day, a daily average of 3 to 4 hour data was collected. And in every occasion, the van pretty much followed a similar route, more or less twice every day. And in every route, it spent more or less about an hour, and most of the runs were after 3 p.m. in the afternoon. So it was kind of a consistent time frame in the sensing process. In this, also, we made sure by this time frame that we were capturing the peak hours in the traffic. So in the left, you just see like a simple deployment over one of the vans, and to the right, you see the gradients we observe for example, for one specific day for temperature, CO2, PM10 and PM2.5. In most of the cases, not only for this given day, probably, or some of you may be familiar with Princeton, in Route 1, where, consistently where, yes, the concentration levels were observed to be highest. Through a 3-dimensional visualization of the CO2 data collected in one of the measuring trips, we also try to look at the data through correlating it and trying to correlate it with the urban fabric to really start thinking about how the city morphology and street layout can be affecting more intuitively or more qualitatively the concentration gradients. Just another view of the same model. And also, as I mentioned earlier at the beginning of the presentation, we made the data available within campus through web applications by visualizing it as scatter plots or interpolation plots. This is the web application, and also we developed a mobile application that displayed the data as a map views and as first-person views. In this case, we are looking at the map view that is showing for every intersection in the city, the AQI, and also as an interpolation map. And the second version was the first-person approach, where you can, I'm gonna just play the video maybe here since I'm running out of time. Where right now I'm looking at the map view, but in a second it's gonna go to the first-person view, where you see these bubbles in the application with the air quality data, AQI data, temperature or humidity data for the different intersections within your field of use through an augmented reality approach. So thank you with that. I'm gonna stop sharing.
Thank you, Mader. I think it's a very good research, and you developed an efficient and affordable system, and through a lot of systematic and systematic tests, it's proved to be accurate and good performance. And I think we can have one short question, if any question from our audience.
Hi, hey there. Welcome to the conference. Yeah, it's great presentation because last year Mader came to teach here in the workshop, and I'm a little bit familiar to the whole system. I think it's a very important visualization platform. You can put it on not only on the drones, but also on top of the taxi or the cars to collecting the information in the city. So I'm really interested in the resolution you mentioned, the high resolution of the spatial parameters you can collect through different kind of tools. So the question goes to the platform. What's the difference between the drones or the cars? Because different speed, different height of the platform, which can help the MUST to collecting different kind of protocols. So my question goes to, is there any difference? You put all your sensors on different platform. Is there any resolution difference or the parameter difference feedback from different platforms?
Well, one of the reasons, and I'm going to go back to the resolution point, but one of the reasons is that the approach is targeting towards opportunistic sensing. I mentioned the word earlier. So you can put it in any vehicle and you don't have to worry about it. So it can be, in this way, a vehicle that delivers mail, or a vehicle that a garbage truck, whatever it is, and the sensors are sitting there. While if you put it maybe in a drone, it's usually a more, unless the sensing packages become very small and they can be part of an Amazon drone, say. But as they are right now, they have to be like a targeted sensing approach. So if you want to inspect a given site, then drones may be an interesting approach because you get a 3-dimensional mapping of an area. But you have to be invested on doing that experimental campaign. And in terms of resolution, there you can get a 3-dimensional resolution, while humans stand on the pedestrian level. So one kind of pragmatic, it's maybe more efficient in that way, the kind of the vehicle-oriented or pedestrian level-oriented approach, given that humans are mostly operating at that level, right? But again, if you really want to understand the spatial gradients 3-dimensionally, drones would be a targeted sensing option that is very, very valuable, and they're going to be on the rise for sure. Yeah. Thank you for the question, Philip. Yeah.
Thank you.
Thank you. And, any other questions? Professor Kelly, do you have any question? No. Yep. Okay, great. Yeah, thank you very much, Major. And let's proceed to the next presentation. We're kind of behind the schedule, so let's proceed to the next presentation from University of Pennsylvania. The title is Types of AI Machine Learning Assisted 3D Modeling Design. The authors has also recorded the presentation, and after the presentation, the first author will be answering the questions from the audience. So I will ask our assistant to start.
Hello everyone, my name is Chuan Liu. I'm currently an undergraduate student in Zhejiang University of Technology. My research topic is mainly about machine learning and application in architectural design. I'm glad to be here to present our current research paper, Type of AI. Convolutional neural network is a class of deep neural network that are most commonly used to analyze virtual images. This figure shows the image that analyzes how an input image is perceived by CNN. Firstly, the computer reads the image as pixels and represents it as a matrix, which will then be perceived by the convolutional layer. The layer uses a set of learnable filters that can move across the width and height of the input file and compute the dot product to give the activation map. Then the file is passed to the next layer. The pooling layer substantially reduces the number of parameters and calculations in the network and controls the overfitting by gradually reducing the size of the network. The last layer is the fully connection layer, in which the neurons are fully connected to all activation of the previous layer so that their activation can be calculated by matrix multiplication followed by offset. In general, CNN uses a relatively light preprocessing than other image classification algorithms. This means that the network learns manually design filter in traditional algorithms. This independence from by our knowledge and human effort in filter design is a major advantage. In this research, we apply style transfer, which is based on the CNN structure as an assistant for the 3D modeling design. CNN-based style transfer is a type of algorithm for processing digital image or video using the local visual style of another image. The style transfer processes a summary input image and a simple style image. The input image is fed through the CNN and the network activation is sampled at each convolution layer. The content image is then obtained at the resulting output sample. The style image is then fed through the same CNN and the network activation is sampled. The goal of style transfer is to synthesize the output image that shows the content of a content image to which a style image style is applied. To fully understand style transfer, histogram, an online style transfer tool is used to generate images. A pair of images is selected as the content image and the style image for the experiment. Then switch the role of the image to another for another set of experiments. It's evident that the output image presents the geometry of a content image and the style of the style image. Despite the remarkable results of style transfer, design techniques are only used to design images to be generated at a 2D level, such as graphic design. In order to broaden the scope of use, it's necessary to design 3D levels in order to apply the generated result for architectural design. Since style transfer processes images on 2D scale, the 3D models need to be converted into 2D images at first. I select my cellular design, which is diverse in entire space, so that a variety of floor plans of different heights can be extracted. By adjusting the position of section plans in SketchUp, a series of floor plans are gained according to the height increment of the building. Then the 10 floor plans are converted into images that only carry the information of every floor plan. Black and white colors are used to distinguish the interior and exterior space. In general, by translating 3D volume into 2D image, content for the input image is obtained as the basic element of style transfer neural network. Later on, the style image will be imported into the network with the content images to start the generating process. After the content image is obtained, a style image should be imported so that the generating phase can be activated. For style image, it should contain a clear outline and a distinctive color contrast. Thus, a framework of chart structure is set as the style image. Before importing style image and content image into the network, several input parameters need to be confirmed. These parameters including style weights, content weight, and TV weights. There will be different effects presented by the output image by adjustment of every input parameter separately. With the awareness, a content image is imported into the neural network while adjusting a single parameter regularly to receive a series of output images. After the 3-set experiment, we noticed that style weight is the input parameter that brings the most ideal generating results. The figure above shows the images that exported as the output images while adjusting the value of only style weight. From the images, the difference is obvious between every single image, and the surprising found is the regular pattern of the set of images. With the increase of the value on style weight, the part of generated texture in the black area, which is represented in entire space, is more evident, as well as taking up more percentage of the black area. Those phenomena are not shown in other 2 sets of experiment with the adjustment of TV weight and content weight. That style weight is selected as the input parameter for the design. With the conclusion above, firstly, TV weight and content weight is given a specific value in the design. For style weight, a range from 500 to 5,000 is given to the content image since the range shows the most ideal case for the content of new generating images. For instance, style weight value of the first floor plan is 500 and that of second floor plan is 1,000. With the set of rules, values are distributed for every content image so that the content of output images are well regulated and persuasive as well. After the processing phase of style transfer, output images are obtained for further design. At this stage, 2D images need to be converted into geometry to fit in the architectural language. Random Zero, which is geometry-based modeling software, is applied to accomplish the conversion. After the import phase is completed, the geometry-like polyline is used for geometric generation. There are several rules at the adding phase. The first to delay the area that is useless for the coming design. The area in white color, which represents the exterior part of the floor plan, is defined a unitary space of the design. After eliminating the white area in every image, there is another set of rules for further addition. Since generated texture in the black area present as intersect line segment from the top perspective, the polyline making tool is utilized to translate the texture into geometry. By connecting all the line segments together with polylines, a geometry version of the image is completed. The rest of the output images will be added according to the same set of rules until all the geometric layers are obtained. By the same rule mentioned at the previous page, the rest of the content image are translated into the 2D geometry forms. The 3D model will be accomplished after all the geometric layers are stuck together according to the original sequence of floor plans. To make the model applicable for architectural design, patterns should be added between the layers so that the load condition of the structure is reasonable. Grasshopper, a plugin based on Rhino 0, is applied to explore the best way of connection from an agro-Mac perspective to eliminate the possibility of connecting uncertainty. To better illustrate how the vertical connection was generated, I select two adjacent layers and use a particular part which marked on the floor plans to show the process of generation. After the script is completed, information of two certain areas imported into Grasshopper. Then there are two input parameters which decide the number and two angle of lines need to be modified for generating the vertical geometry. The input parameter which decides the line's numbers being modified first, since the determined value of the parameter is prerequisite for further adjustment like tilt angle. A number slider which domains from 0 to 1 is implied to adjust the number of lines between the layers. In the experiment, the domain is divided into 5 groups of subdomains, which are 0 to 0.2, 0.2 to 0.4, etc. Then the median is selected from every subdomain to be the value of the input parameter for each side of experiment. After the number of geometry is fixed, a panel is set for the domain of the tilt angle to determine which domain is more suitable. Another 5 side of experiments are conducted according to the same rule of the former experiment. To translate the geometry into architectural language, piping, a design tool in Rhino 0, is used to convert geometry into a 3D format. By adjusting the radius of both horizontal and vertical geometry, the optimal format is generated, and this figure shows the image of two section planes. One is from the right and the other one is from the front. The views are selected according to the structural complexity, which present the distribution and relationship of vertical geometry between layers. The panorama shows the image that depicts the relationship between the building and its surroundings. The original building is evolved into several variants, which are achieved by stretch, compression, and superimposition of the original format. This step helps to expedite the design process, which translates the original building into a series of new formats so as to fit in different circumstances of the city. Generally speaking, 2D geometry is successfully converted into 3D format that is available for architectural design. Since 2D images are the basis of 2D geometry, style transfer, a neural network to generate 2D images is of great significance for the whole design. This brings to an envisagement that if style transfer can be employed as a post-human approach to architecture, it is possible to generate new style in light of two input images that are of distinctive design style of two architects. It would be more interesting if the new style can be applied in architectural language so that style transfer could be processed into a creating level. Future application in architectural design with style transfer involving the creation of architectural images as well as vectorized data. Apart from application in architecture, it is the perspective of being utilized in fields like graphic design and animation design. Thus, it's highly possible that style transfer neural network will be an indispensable tool for designer at the creating stage in the coming future. And that's all. Thank you.
Thanks for the presentation. And the first answer Chuan Liu is in our meeting room and ready for answering questions from the audience. Please, if Professor Yuan, do you have any questions?
Yeah, it's very interesting research. Actually, it's a very difficult part because the deployment of style GAN is to transfer the 2D to 3D. Different people, different team making different kind of tasks, but I think it's meaningful here to implement this kind of transformation through 2-dimension to 3-dimension. The question goes to actually, right now it looks like very stylistic from image transfer to generate the model from 2-dimension model to 3-dimension model. So are there any other parameters we can input, maybe based on the structure or based on not just on the stylistic images? Are there any other parameters could be embedded into the process of the transformation?
Hi. Oh, yes, there is another parameters for the experiment, such as the TV weight and the style weight. But the style weight is the most important parameter in the when adjusting the all the parameters in the experiment in GAN. And in Reynolds, there's another two parameters to adjust, like the several cells to adjust the tilt angle and the numbers of the pillar, just which are connected to the adjacent layers of the building. And these two parameters are very important in this, but the most important is the style weight in the GAN system. Thank you.
Thank you, Chuan. Yeah. Do we have other questions from the audience? Okay. Thank you for the presentation. Very interesting research. And now,
thank you.
Yeah, let's proceed to the next presentation from Shop Architect USA. On-site beam enabled augmented reality for construction. From Adam Chernick, Christoph Moos, Steve London, Tim Lee, David Menard, and John Seron. Sorry for the pronunciation. Yeah, no can problem. Start.
Can you guys hear me?
Yeah.
Great. Awesome. Thank you guys so much. I'm really excited to be here. I'm actually representing our team today. I'm Adam Chernick from Shop Architects. I am the director of interactive visualization. So we lead a small team that builds AR and VR applications, and I'll explain a little bit more about that right now. So very happy to be here. Thank you guys so much for the opportunity. So a little bit about Shop really quick. We do a lot of different buildings around the world, but that's not really what we're here to talk about today. What we're here to talk about today is a piece of technology that we use on this project. This is the 9 DeKalb Tower in Brooklyn, New York. It's going to be the tallest tower in Brooklyn, and it's currently under construction. And so what our team does, just a little bit about our team, is we connect design, data, and the physical environment. And we do that using a whole bunch of different tools to a whole bunch of different mediums, whether that is a tablet, headset for virtual or augmented reality, or a web application. And so to speak specifically about the paper on hand, and the problem is it's documentation, it's construction. Construction is an incredibly complex process. And this is what we're trying to solve today. Not solve, but facilitate a better process. Construction documents in their current state are easy to misinterpret. They're slow to navigate, and they're slow to gain a spatial understanding. And it takes a lot of experience to really understand and interpret these drawing sets. And there's a lot of related work to the work that we're doing here. There are some software that are specifically for construction management. Procore and FieldWire are great software for that. Insight VR lets you collaborate immersively and be able to collaborate on BIM issues. And then Bluebeam is kind of a document viewer. And so all of these different tools are trying to, solve parts of this problem in a different way. But we'll dive in a little bit further right now. So here's kind of our solution, and I'll read our abstract really, really quickly. So we describe a prototype system of communicating building information and models directly to on-site general contractors and subcontractors. The system developed by shop architects consists of a workflow of pre-processing information within Revit, post-processing information outside of Revit, combining data flows inside of a custom application built on top of Unity Reflect, and finally delivering the information through a mobile application on-site with an intuitive user interface. And this system incorporates augmented reality in combination with a dashboard of documentation views categorized by building element. And so this is kind of how the data moves through into our application from Revit. So we'll kind of break that down a little bit more. Our pre-processing step here, we have a custom Revit API plugin that we are actually creating custom metadata within Revit and creating custom parameters within Revit in order to pre-populate this data into our BIM model to make this initially BIM data-rich model even a little bit richer in information, to give us some data that actually is not able to be accessed out of the box with Revit. And then once we have that data, we actually do this post-processing step. We have some editor scripts in Unity that come and, based on some of that data exported from Revit, it automates the creation of a hierarchy system within our Unity scenes here. And then we go and we are able to access that BIM data. And the ability to access that BIM data is thanks to Unity Reflect, actually brings in our geometry and our BIM data in an optimized fashion. And that's a really important aspect to this process. So here's the application. So, augmented reality for construction, what are we trying to do here, right? We're overlaying our BIM models and data on top of the construction site so that we can interact with our BIM models in a one-to-one scale, immersive way. And so we have this iPad. This is specifically looking at localization here. We're using QR code image trackers to be able to localize our model into the correct location onto the construction site. Once we have our BIM model localized onto the construction site, what we're trying to do is basically extend this construction document set. We want to make it easier for anyone on the field, a GC or a subcontractor who's going to build these buildings, make it easier for them to obtain necessary information and gain spatial understanding very, very quickly. And so, we need ties to these initial construction document sets. There's this language that general contractors and subcontractors understand. And this language is, based on iconography. There are these section cut detail callouts and elevation callouts. And so how do we represent that in augmented reality is we actually put an object in the physical world. So this is a physical, an augmented section cut symbol that now we're able to interact with. This section cut lives on top of the real world as an extension of the CD set. So this section cut 1A360 is actually at the correct location as it is in that CD set itself. So it's a one-to-one correlation. And then we can see that section cut in one-to-one in AR is, again, a direct representation of that same section cut in this construction document set. So when we click this construction this section cut, now we actually have a one-to-one scale augmented reality model on top of our construction site that's not just dumb geometry, it's also data rich and interactive. And so we'll see that when we select a specific component, we actually obtain all of that pre-processing data that we had done before. We are able to actually access what drawings are associated to that specific piece of geometry, to that specific column or that specific ceiling there on the right. And so what that allows is now we're able to select a wall and pull up a drawing instantly, instead of having to flip through these potentially hundreds or thousands of pages of documents. Now we're actually able to select that piece of geometry, and that geometry actually knows what is associated to that geometry. And that was not previously there. Here's just another demo where we select a wall and you can see all of the associated drawings. We also brought in the thumbnail versions so that you can visually be able to grab the correct drawing quickly. It's all about decreasing the amount of time it takes to understand and build a building. And then here's kind of that entire video of the process from A to Z. Is we localize that model. We have these section cut elements. We have these call out elements living on top of the physical environment. And then, you can walk around. This is positioned into place. And we actually have multiple QR code image trackers around the site that we can relocalize to snap the digital environment on top of the physical environment at multiple locations to make sure that it maintains that accuracy. And then looking into future development, there's a lot of things that we want to do with this application. One really important thing that we would like to do is tie this application into some other construction management software, such as the Procore API or BIM 360 or Autodesk Forge. That would allow us to really gain additional data and metrics from our already BIM-rich models, as well as directly gain information from our construction administration teams, which we think is really important. Another thing is increasing scalability. Right now, this project is just a proof of concept level. We're trying to get it to a minimum viable product so that we can actually do additional more user testing on site. We've done some very limited user testing, but we really need to continue to push this user testing so that we can find issues and make it more useful for the boots on the ground. We need to optimize the software a lot. These drawing sets are massive. And we need to automate more of this process. The entire process from A to Z is, continuing to become more and more automated, but it's still, there are some manual pieces in there that we need to continue to work on. Another thing that's very important is exploring other localization techniques. Right now, this is using image tracking and then relocalizing based on separate images. We've also done some research into spatial anchors so that we would not need any image trackers. The device would just be able to look around and be able to, contextualize itself and understand spatially where the digital environment needs to live. So those are a few of the future development paths that we're going to take. And I'm going to kind of cut it off short here to get some questions going and hear if anybody has any questions for us. So we really appreciate it. Again, we're excited to be here and talk about this technology that we're working really, really hard on. So thank you guys so much.
Thank you, Adam. It's a very practical and useful tools. And actually, you already have one question in our chatting records.
Okay.
Can you see that?
Sharing my screen.
Yeah. Can you read the
the
questions?
The question is, when doing the cool AR thing, how do y'all know that the QR code trackers are in the right place on site? So that is a predefined location. So we have a user-defined location or multiple user-defined locations before we build the application. And then when we go on site, we know where those specific locations are, and then we know that it's localized correct. Yeah, thank you for the question. That was a good one.
Thank you. Thank you. And other questions from our audience, from our meeting room? Another question in the chatting.
Another one.
Yeah.
Have you ever considered other ways of determination rather than QR code? Is that the best solution? Yeah, exactly. So that's kind of what we were talking about with these localization techniques. So spatial anchors is a big one. There's a thing called Azure spatial anchors, and there's a few other similar methods that basically take a point cloud, not a scan, but it uses some SLAM technology to understand spatially an environment, and then it's able to actually match that environment. So if I'm standing at a specific location on a construction site, I can look up, it knows exactly where I'm standing, and then I can drop the digital model correctly on site. And so that's one that we have been looking at, but the technology is very early still with that stuff, but we're excited about it. Are there any other questions?
I have one question. Actually, I'm not such a BIM guy. I don't do BIM research or BIM practice. But actually, the concept of BIM comes out like 15 years ago, and the idea of using this kind of augmented reality or virtual reality in presenting BIM model on site, on the construction site, has come like 10 years ago. And but I believe your work is really advanced among all these works. But my question is, why it's not so much applied in practice yet, or you still need to do the development after 10 years of this concept?
That's a good question. I think my answer to that would be, it's still so early in the technology from the augmented reality side. Problems like localization are incredibly difficult problems to solve. A lot of smart people around the world are trying to solve that issue specifically, but it has to make people's lives easier than they were before, right? That's what adoption the software needs to save somebody time. If it makes their life just as easy as it was prior, they're not going to adopt the technology, right? We need to save time and we need to save money. And I think once we do that, adoption will follow. So I think that we're just not quite there yet.
Yeah, the Autodesk, do they also develop this kind of technology? Because it's kind of it's kind of key for the Revit and their system to be applied.
Mm-hmm.
So they are also doing this, but it's not so successful yet, right?
Yeah, exactly. I think that it's going to be very interesting to see what these larger companies do, and kind of how they push those verticals and those ventures, specifically in on-site augmented reality. I know that they are definitely doing a lot of experimenting with it, but they haven't, released any of that functionality publicly so that any architecture firm can go and use their, on-site AR one-to-one tool. I guess I'm trying to understand your question exactly. Why haven't they released those products? Is that your question?
Yeah. What's
I'm not sure.
the problem there? Yeah.
Yeah, I think it's just on the augmented reality side, on making sure that making sure that the digital environment is accurate enough
I see.
to the physical environment, because there is some risk associated with that if the digital model is off, or anyway, maybe it's something
Oh
like
yeah,
that.
That's
a great
very
question. Thank you so much.
Difficult problem. Yeah, thank you very much, Adam. Yeah, so we still have one more presentation from the NG studio from ESRI USA, and let's invite Nanju Lee to present the work understanding and analyzing the characteristics of the third place in urban design, a methodology for discrete and continuous data in environmental design.
Sure. Can you see my screen?
Yeah.
First of all, thank you so much to having me here and this opportunity to present my work. And my name is Namju Lee. I'm founder of NG Studio, which is specialized in computation and design and visualization. And I also work as software engineer at Ashley, which is GIS company. My presentation's topic is about understanding and analyze the characteristic of a third place in urban design, particularly focusing on the methodology for discrete data and continuous data in environmental design. With the rapid development of data-driven technology, many opportunities have arisen to understand and characterize urban context. This project tries to address the methodology to understand a place in an urban setting through the lens of third place and mobility based on the walkable distance. To capture the process third place data fetched from the Google Place, and based on the given location, the project discuss two different types of data structure to process discrete and continuous data and representation of the third place. In a specific location of a city could be characterized by representative query. It's identified chart as a representative of understanding a designated area could compare with other chart in different place. This methodology allows us to distinguish the constitution of third place based on distance among place, enabling us to develop design strategy to differentiate or accord the site based on mobility. The third place refers to the social environment between two users around a surrounding place, like a home as a first place and workplace as a second place. These places are settings such as cafe, club, park, library, and restaurant, and so on, where you spend our daily life except for the first and second place. This diversity and density of the third place could become a parameter and characterize a place. Energy is also essential resources in modern society. Every major city is on the earth and consume diverse types of energy. And as you can see on the image on the left side, is the major energy concentrations for the transportation things. And on the image on the right side, and the urban population is more significant than rural areas, and the population increased the consumption of energy for transportation. However, the energy use for transportation per person in low density is higher than urbanized city with high density, because citizens need to use transportation to access their third place in their daily life. So this is the third place visualization by Google Map data. So as you can see, we can clearly see some patterns, some group of the third place population in Cambridge and Boston area. So in order to produce this kind of third place data, so I utilized the two different types of data structure majorly. The first one is the pixel data structure, which is like a two-dimensional data matrix, consists of individual pixels that could have diverse data internally. As a parent of each pixel, in a hierarchy, the pixel structure govern and they control the compute, the emerging the new data by talking with the neighbor, the data set. So what I mean by that is basically the position data, in general, they have like a particular discrete data. So sometimes we need to interpolate this particular position data, their neighborhood, to make them a better, the compute for the data. This is the other example of the multiple layer of the 2D pixel. So let's say we have multiple types of the data, and then we can, the layout based on the layer, and then we can make some special processing to talk and merge and flatten the multiple layer into one simple, like a 2D-dimensional data set, which is representing the city or district. So as a different technique, a graph data structure also utilized in that project. The graph structure is a sort of a mathematical object that consists of the node and edge, and is widely used to represent relation data structure. The street network of the urban street or a highway or a subway map are example of objects. Those are very closely resemble their physical form. So in order to calculate the actual distance or some cost, we need to convert like the continuous data into the graph data. So as a second data process, I utilize the graph things. And also, as you can see, the graph has a very particular characteristic in terms of the travels. So some data, a node could have like a one-way trip, or the other ones could have a round trip. And the individual node has some their data properties, so we can basically calculate the one single source of truth as a weight by computing multiple hierarchy based on the each weight. So this is the query. There's a lot of query, so maybe it become like a noise. So I reduce some of the query reduction. So as you can see, there's a lot of sort of place, but we can like categorize into 6 areas so that we can get the more precise and clear the compute process. So in order to execute this kind of the methodology, so I picked the 4 different types of area in Cambridge area. So which is the Cambridge is a very unique area, but the 4 designated place has a very differentiate each other. So basically, for example, the Harvard Square has a lot of tourists and students, and MIT Building 7, which is sort of isolated. So a lot of students is there, and Kansas Station or Bellevue Center has their own like a biotech and some big giant company there. So this is a sort of the methodology demo. As I can say, we try to analyze sort of place data based on the distances. So I parameterize the distance between 5, 10, 15, and 20 minutes to workable place, and then what kind of sort of place is accessible or not. So the sort of place is actually the point data, and then we basically pre-process the point data as like a pixel, because the one place actually affect their neighbor, right? So we try to mimic this kind of ecosystem, and then at the end of the process, we the network analysis is consume their own area and then compute based on the distance, as I said, like 5, 10, 15 minutes. So this is the other example how I convert a discrete data to the continuous data. So there's one particular area could have different types of data sets. So for example, like slopeness or number of sort of places or restaurant or coffee shop and things like that. So we actually give some kind of weight, and then the weight is atop their neighbor as like a propagation system, so that we can get like a continuous smooth the data around their neighborhood. So this is the sort of last the methodology that I use for this project, the paper. So as you can see, we can designate a particular area and then it's snapped to the closest node and then travel the older network and then print out the sort of place based on the 6 category that we already processed. So as you can see on the right side, we can see the number thing. So this is the result. Let me close this window. So there's the number of the solid place within the 6 category based on the 3 different the measure system, like a 5, 10, or 15 minutes. So if we actually overlay each other on top of each other, so we can see some like a pattern and some like you know, the shape of the star shape. Yeah, and also the down there. So we again the discrete data couldn't represent only one particular area. So we need to think about like the more you know the place with their neighbor. So this is the like a heat map representation of the star plot, as you can see. And also, there's a 2 way of looking at this star diagram, I guess. First one is we can see you know, the number of the solid place, and the other way around is the shape itself. Shape itself has a very unique characteristic. As you can see, the Melbourne City here is for the 5 minutes, this workable place, it has a very rapid, like a facility and the health things. But as the distance is getting bigger and bigger, so maybe the people living there, they need to drive, or otherwise they need to walk like more than 10 minutes, things like that. So I have a simple like a wrapping video. I don't know how can I reduce the soundtrack, but I can, let me, I think it's okay. So as I said, I have a solid place data. This is the entire solid place data, so we can see some pattern. And then I do some color reduction because there are so many noise. So we need to get the some particular algorithm to process the solid place data. And then we have some network analysis. This is not just about the distance based, it's more about like a weight based the cost system. And overlay. So this is the examples. So we can quality the solid place based on the different the distance, like a 5 or 10 or 15 minutes workable distance, as I said. This is the example how one particular point affects their neighbor based on the law. So we can, so for example, like a crime data is not affected on particular areas. The crime data is actually living in their own district or area. So we need to calculate the urban data. So this is the example of how we represent the solid place data as a sort of like a star plot. So as I said, this is the result. I mean, with this kind of result, the shape itself is also very unique. And also, as I said, the shape is a sort of different types of representation of that particular area that you select. So actually, as a conclusion, understanding the density of the solid place based on walkable distance could reveal the characteristic of city, which allow designers to develop the decision-making process by comparing with different location or the past of the same location. That's it. Thank you.
Thank you very much for the presentation. And do we have any questions from our meeting room?
I posted a question.
Yeah, please.
Sorry, I posted a question there in the chat, but I'd be happy to state it verbally. Hey, Namju. So I guess my question has to do with, so first I should say it was a great presentation and some really lovely visualizations of your subject matter. I guess my question has to do with the kind of start of the data visualization process, where you decide what constitutes a third place and what does not. And I guess I find myself questioning, especially in this time that we find ourselves in, I haven't really left my house for a third place in months. So I kind of started by thinking, like, are we still going to have third places in the post-pandemic era? Or how is this going to make us kind of rethink what constitutes a third place and what does not? And that more broadly, then I kind of took a step back. More broadly speaking, it seems like what constitutes a third place is culturally and temporally specific. Like what I consider to be a third place now in the middle of a pandemic is different than what I did a year ago, and it's probably different than I will consider to be a third place a year from now. By the same token, these are culturally specific categories. What a person in Cambridge would consider to be a third place in their life would be very different than someone in Seoul, for example. So I wonder how your visualizations might begin to reveal these kinds of differences over time or over kind of different cultures.
Correct. Thank you for asking this question. So the assumption of this the project is we actually rely on the Google third place data, so which is actually not represented, the real third place context in the city. And also, as you can say, like we have a different culture, and then based on this sort of rapid pandemic, I think we need to define what is the third place. I think before starting, I guess. But according to the book, the third place that I refer in this paper is it's more about like in between place, like workplace and the house. So where we can meet and then hang out and communicate, just like Zoom meeting. Also, it's a sort of we can consider this is a sort of place happening things. So I feel like I don't know whether I'm fully understanding your question or not, but I feel like the third place is sort of it's really hard to define. To actually make the third place as a tangible data that we can actually allocate on the map in a geographical way. So yeah, I mean the data is I think it's really important in this project, and then I think I need to more think about like the definition of the third place, and then how even if we couldn't get the right third place data, I think there's a lot of way to measure or collect the third place data indirectly things. So yeah. Any other question?
Yeah. Maybe, yeah. Actually, we're kind of behind schedule, so we don't have time for another question. But we're going to have another panel discussion session for all our 8 presenters, and so we're behind the schedule. So we're going to shrink the time from 30 minutes to 20 minutes. And but before that, I think there are still some questions left for our presenters that was asked by our audience outside the meeting room and inside. And I think maybe it's also very interesting to share some of the questions in right now. So there are some questions asking about for our first presenter, Professor Kelly Stenfeld. And I would read out the question that you can answer again, because you already answered in the chatting room, but you can answer it again to share all the information to our audience outside the meeting room. The first question is, as you mentioned in your presentation, the audience was wondering, for each model type, do you need to train separately by its categories?
Right, thank you for that. So basically, yes, we do. I haven't really considered what it would be like to do otherwise, and the reason for that is that we really placed a lot of emphasis on facilitating users in training their own quote unquote brushes for their own purposes. So an individual user would, begin, by deciding on what they wanted their drawing assistant to do, or how they wanted it to help them draw, train a brush surrounding that, given a training set, and then wield it. So in the end, because we were working with a group of 16 or so students, we ended up with more than 200 brushes, I believe, that were just trained for very, very specific purposes. So yes, the one training set per brush.
Thank you. The second question is, since the parameters of neural networks are determined by the training dataset, how exactly can we diversify the outputs?
Yeah, I have to admit I got a little stuck on that one, and I would love to hear more from whoever asked it. I don't know who it was. I have to say I'm not trained as a machine learning engineer. I'm just an architect who likes to play around with these things. So I don't think I quite understand the question well enough to respond smartly. So I don't know if the person who asked it is on the call, or maybe they were remote, but I don't know.
Okay, let's leave it as a question for all. Okay. Yeah, and you have still a third question: how the Sketch to Pix and Photoshop interact?
Right. Thank you. Just a kind of clarification of a detail that I didn't get to in the talk. So Runway ML is a existing piece of software / platform that can host models. And so once we train a brush, it lives, quote unquote, on Runway ML. It's hosted there, which means it can receive API calls. So different pieces of software can send images to Runway ML, and that runs the model and then receives the response and then transports it back to whatever context made the call. And so with that in place, we didn't do that, right? So that's just Runway. With that in place, we posted our models to Runway, and then we actually developed a plugin for Photoshop, which could talk to Runway via API calls. And there's a plugin development language that we used for that on the Photoshop side. So really the only development that was necessary was the Photoshop plugin side of things to get the two to connect. So Runway is the glue.
Thank you. Thank you. That's the 3 questions for you. And we still have one more question for Adam. Adam Chernik. To Adam, one question on the AR device. When you actually build on-site, it seems not practical to always hold an iPad. Do you consider to use another device, other devices?
Definitely. Can you guys hear me? Okay.
Yeah.
Yes.
Yeah. We can hear you. We can hear you.
Great. Yeah, definitely. Right now we're using mobile devices because they're very distributable. We're running betas on Apple's App Store and on Android Google Play Store, so that we can distribute them and get user testing. But definitely in the future, when augmented reality headsets get better and have a wider field of view, we would like to move in that direction.
Okay, thank you.
Thank you for the question.
Yeah. So that's all the left questions, and so let's start our panel discussion. Please, all the presenters, turn on your video, and we can have a group discussion right now. And also, please, Professor Yuan, participate in our discussion. And actually, I think it's a very very good session. I mean, I learned a lot from you. All of you are using very advanced algorithms, or trying to develop very practical and powerful tools in design or construction practice. And actually, I feel like that the digital design research evolves very rapidly, and nowadays we see a lot of in GAN and the neural network researches, and also a lot of very practical, very detailed and practical tools developed. And so my question is, although these tools are very powerful, do you encounter any difficulties, or what do you think is key to the development of our research area, like digital design, digital like analysis or construction, all these problems? What's the frontier, and what's the difficulty that maybe we were facing or you are trying to solve in the future research? And also, I think this is also questions also related to a question from our one of our audience. I will read out. This is a question towards all speakers. Could you describe in more detail how do you envision the marriage of machine learning and architectural design in the future? Is it going to be a tool that promotes inclusivity, or will it become a barrier for designers who are not digitally literate? Yeah, so that's my question. I think all our presenters can share your opinion with our audience, like one by one. And if you're ready, you can start.
I can go first because no one.
Yeah, please.
Yeah, so I'm not a machine learning expertise, but I had several projects with the machine learning things. But my understanding of the machine learning in the design practice is it's not like the developing the special network, but more about like understanding what the network does and then how to prepare data set to take advantage of the network system correctly. So, there's a lot of like a specialized network, like pix-to-pix, or like a, ranking system, or, there's a lot of networks, computer science and statistical people develop their own sort of methodology. But as a designer, so I think we need to understand what we really want, just rather than take advantage of the technology because it's just simply fancy or like a nice. But in terms of as my professions, we dealing with a lot of urban data and geographical data. So in this particular data set, for example, sometimes I don't know. As I said, I'm limited experience, but sometimes the deep learning is it's like shows like a little less performance compared to simple linear regression or polynomial regression. With the deep understanding of the pre-data process. As I said, the data processor need to understand what the network gonna consume the data. So let's say to make my long story short, I guess as a designer for design practice toward the machine learning understanding is more about like understanding network and then prepare the right data structure or right data image or whatever. And then we need to clarify what is the input, what is the output. And then this kind of input and output goes to other design process or decision making process things. So I think this is just my understanding of looking at the machine learning in design with the limited experience.
Thank you.
Can I make a comment?
Yes, please.
Yeah, I think this is really a great question about like the inclusion of machine learning and advanced in design. In response to what Najim just said, I think one motivation for me to use machine learning in design is the word understanding, or the word that a lot of like data scientists use in the data science projects as interpretability. So I think from the perspective of designer, I think somehow design is usually captured as a black box process, and I think machine learning is kind of like providing a way around for people to understand like the neural basis of design, which is like a biological, somehow like could be metaphorically understand it as a biological neuroscience process, which we do not yet uncover. But machine learning provides like a simulation modality to this kind of like black box. So yeah, this is my perspective using machine learning to increase how we understand the design ourselves. It's actually through machine that we can like can understand ourselves, like understand human. So yeah, that's my opinion. Thank you.
Thank you.
I was wondering if you could repeat the question, I guess, as framed to, you know, what our more practical application is, isn't actually touching on machine learning. I guess you could skip me on this one, or
yeah. My question is, although we have developed, we're using very sophisticated and very good performance tools, there are still some challenges for the development of design and construction and analysis or investigation in the future. So what do you think will be the challenge in the future, or what are you going to do? What are you going to, you think is key for your future explorations?
Yeah, absolutely. I guess I'm going to interpret that as, you know, what are some of the biggest blockers for us in development of some of our software? And I would say, you know, some of that is hardware restrictions and some of that is software restrictions. I think that, you know, the technology is growing so quickly. It's incredibly exciting to see. But there are still many limitations, especially on some of these, you know, headsets. It was a very good question previously about why are we using mobile devices on a construction site when, you know, a head-mounted display might be a better opportunity there. And, you know, really that has to do with cost and distribution. We can't give a head-mounted display to every single general contractor and subcontractor on a construction site. When all of them, you know, many of them already have tablets that they're using, they can reuse that, repurpose that device in a new way to increase efficiency on a construction site. You know, so it's really both a software and a hardware problem, in my opinion.
Thank you. Yeah, I think it's somehow the practical problem is really difficult to deal with, actually, even with this advanced neural network and machine learning tools. But some of the practical problems are most difficult to solve. And yeah, it's based on a lot of optimization and also very good understanding and how to structuring the problem.
I don't know if I mean, I hope I'm not hearing that people think that drawing bowling pins and strawberries is not practical in some way. But I could take up the question. I'll take it back to machine learning, I suppose. There was really two parts. Like, what are the immediate challenges, and then is there a kind of will there be a barrier? How will machine learning tools relate to novice users who are not deeply embedded in those processes? So I'll take that one at a time. So one, like the immediate challenges, I think it's notable that there was more than one project that we saw in this session that struggled with the kind of 2D to 3D translation. And a lot of that has to do, and I mean, I should say struggled mightily. I think I really enjoyed the projects, and I think that they were quite strong. I think it more speaks to a position that we're all in as design technologists in architecture who are experimenting with a new technology that we don't have direct access to. None of us are machine learning engineers, right? I assume. I'm not. So I don't have direct access. I'm in my own way a novice for these things as well. And the simple fact is they were designed for other purposes. I mean, these are technologies that come out of computer vision. And so they are made to operate on formats that are amenable to computer vision problems, images, and image sequences. And architects don't generally work with that particular format. And so I think what's needed overall is an investment in two things that would further the state of the art in architectural applications concerning machine learning. One is underlying algorithms that deal with a broader range of representations that are more akin to what we do as architects. So vector representations and 3D representations such as 3D graphs and meshes and that kind of stuff. And there's been some work in that regard, but it's not completely accessible to folks like us yet. And then second, we need better data sets, like kind of fundamental data sets, benchmark data sets, the way that they have in computer science. There's no standard representation for a building. The representations that we use as architects is multivariate. There's many, right? There's plans and there's 3D models of different formats and there's programmatic descriptions and blah, blah, blah. I mean, we don't have any kind of standards in that way. And I think that developing those standards collectively would go a long way to furthering the state of the art. So those are the two big challenges I see ahead of us. And I would love to work together with anyone who wants to help tackle those things. The second part of the question about access, I don't know. I mean, this is how things go in the world, right? I mean, like, this is not the first time that a transformative technology has been introduced to design culture. And there are people who are deeply embedded in it, or relatively, like for our group, and there are those who are less so. And, you know, it will go how it goes. I think that those who are less deeply embedded will have less access to customizing things and changing things around for themselves. They'll have less power in this scenario. And those who have deeper access will have more power to change things as they like. But with that power comes in, like, it's a trade-off, because as you become more deeply invested in these things, you also kind of buy in to the fundamental assumptions of any given structure, right? You become an expert, and that means like you do things the way the expert does them. And so on the one hand, I think it's not going to be any different than any other thing in that regard. On the other hand, I have as I said in my talk, I have high hopes for machine learning as a technology of the tacit, which is not something which is a fundamental failing of digital design media as it's currently conceptualized, from 3D models to parametric design to BIM. These are all technologies of the explicit, right? And as a designer, it's very uncomfortable to have to be so explicit on everything all the time. I want to draw bowling pins and strawberries, right? As an early stage, like kind of frou-frou designer, right? Not like as, you know, a serious person who builds things, but like I want to experiment. Like, creativity thrives on the tacit, and designers need that. And I think that there's a possibility for CAD tools based on machine learning to begin to address this missing piece of what we yearn for as designers, which is something unspoken, design by example, design through tacit suggestions rather than explicit statements. So I have a lot of hope in that regard. And that might play into the person's question about a novice user. A novice person can just say what they want through example rather than writing a script or whatever, right? So I don't know. I'm of two minds of the second question.
I think it's very, very intuitive. Thank you.
I have a question. So Kai mentioned the second section. You also talk about like, you know, standardize the data set that we can benchmark to train the networks, basically. But I'm just curious, like, my understanding of, you know, the machine learning for the computer science side, basically they try to predict the future based on the past, because they need to sort of you know, very standardize the aim, you know, increase the accuracy, things like that. But I think, do you think if in case that we have this kind of standardized data set, how the machine learning things, you know, dedicate the design area rather than fitting one particular, you know, thing? So I think this is my question. What do you think about, you know, the standardized data for benchmark for training for the network in design area? So do you really need to like sort of have a, you know, medium or optimal design set, or, you know, the network or training things? Because we are dealing with like something we need to design, you know, designing some things that we never experienced before, right? So in this case, maybe the train set maybe become blocker. So this is my question.
I love that so much. Thank you. That's awesome. So that I might quote you, so I'm going to say it again. You said that because of these, well, it's a different thing in computer science, because what they want to do is predict the future based on the past. And Lord, did they get into some trouble with that, right? I mean, like, it's so dangerous because of all the bias. There's a problem with bias, right? But that's not our position as designers at all, is it, right? I would say as designers, we want to play with the past to construct the future. And that's a completely different thing. And so you're right, like those benchmark data sets, they're not for the things that the computer scientists would use them for. They're for something else. They're for us to play with. But I think we still need them. Thank you. I'm seriously going to quote you on that. Thank you.
Answering the question. Thank you, Kai.
Yeah, I think I want to say something. It's a great panel. All your papers, I think it's very interesting testing the new boundary of architectural discipline. The most important things from the keynote, I also asked him a question. He's talking about the wildness. He wants to simulate the wildness by computer or by certain kind of installations. So the question, if we were talking about the AI, I think it's kind of expanding not only the design skills, but also the authorship from the designers. It's kind of extension of the skills of thinking. But actually, if, as a designer from design perspective, the whole design process actually is really difficult to replace totally by the AI or the machine learning, these kind of tools. But probably some kind of certain motivation or certain target could be probably solving smartly by the data collection or the training the data, or actually by cleaning the data. I think that is very interesting to make certain kind of simulation, optimization, and iteration. This kind of process is construct a certain kind of a thinking methodology, actually, which is not only a data process, but also goes to some material process, including the construction process. From my experience, actually, we implement a lot of scenarios by robotics in the construction process. We also use machine learning to training different kind of details. For example, we take videos from the carpenter to do some special work on the timber. After 500 different kind of record videos, we can use machine learning, training the special angle and the special strength to cut the wood. So this kind of process is kind of learning some skills from the past, from the craftsmanship, kind of cyber craftsmanship, which can replace a human being. So that is something maybe part of the work we can actually replace the past. Maybe we can learn from the past, or can produce different kind of new possibility to the future. But actually that is, the labor cannot replace the thinking process. Maybe can replace the labors, but not replace the creativity by the designers. So I think the most interesting question is artificial. Maybe in the next few days, we have 3 or 4 different talks, and the topic will focus on artificial intelligence design. Matthias de Campo, Neil Leach, they invited different people, make different kind of discussion, because in the last 2 or 3 months, I was invited to be the critics in different kind of studios. I think it's a hot topic right now in the implementation of artificial intelligence. But the most important, I think, right now is kind of a stylistic process by the style GAN, or by the pix-to-pix, this kind of training process. Different kind of scenarios, maybe not only in the architect skill, but also in the scenario of urban planning. It is interesting, but my feeling right now is more like a stylistic training process. The way is focused on the outlooking or the image-based process, but actually the architecture is really complicated. It's a complicated system, including the structure, including the environment feedback. So I'm looking forward to maybe in the future, artificial intelligence may be just by some very small toolbox. It's kind of toolbox culture, which is can help us to in the very complicated process to implement different kind of tools to solve different kind of problems. So that's why this year, Digital Future, we set up a special award which focus on the scripting. I think the future generation, like you guys, some of the students here, if you can invent certain type of tools, certain kind of plugin, that could be the new authorship to designers. So designers in the future maybe not design certain object, but the designer could be someone to design certain kind of tools and can teach different people, can be implemented in different scenarios. So that is really interesting from the PhD student and some professors here. I think you are really doing some contribution to the discipline. Thank you.
Thank you.
I think maybe we should keep the schedule because
yes. We may have some authors do not say anything yet, but if you have anything, please, anything to say? Okay, thank you very much, and I am very honored to be here to be the session chair of this fantastic session with all these 8 fantastic presentations. They're very inspiring and delivered a lot of information and a lot of opinions, which are with very deep insight into our profession in design, in construction, and in analysis investigations. And also the discussion is, I think I try to push you to say something you're thinking of, you're looking into, and which is not the answer yet, but maybe key to the future development of our area. I do think that architecture is a very interesting area because it's very different from common problems that like the computer scientists are trying to deal with, because our problems are more dynamic, more interesting, more like in much more freedom than what they can think. I think it's a lot of freedom and also the dynamic and complexity in our profession. So I do think that architecture and related areas are very good playground for researchers in digital methods, and I do really looking forward to very fantastic and innovative tools and methods and papers from you. Thank you very much, and hope you have a good lunch and see you in the afternoon.
Thank you.
Thank you very much.
Thank you.
袁老师还有什么要宣布的没有？ I would like to ask if our assistant to have something to announce.
Yeah, we will start our next conference session in this afternoon. We'll start from 1 p.m. So it means 20 minutes later.
Yeah. Yeah.
So are you interested? You can stay in the Zoom conference and you can ask some questions to the presenters in this afternoon.
Yeah. Thank you.
Thank you.
See you in the afternoon.
李彪老师好，前半场有点拖堂了，所以我们刚刚结束了1刻钟啊，可能我们可以稍微晚个几分钟开始。
啊，没关系，没关系。
那个能给我设一个联系主持人吗？
等一下，袁老师，我要找主持人给你设置一下。
啊。
已经设置好了，袁老师。
好。我们可能稍微晚个5分钟，因为很多人在吃饭。稍微我们晚个5分钟开始。请问那个转播有没有转屏幕？
我去哔哩哔哩看一下啊。
转播暂时没有转屏幕，转播等会议开始之后转。
立刻你可以看到我的那个什么吗？屏幕吗？
我可以看到，老师您需要现在开始转播吗？
等一下吗？稍等一下，稍等一下啊。
好的。
你先切过去吧，屏幕。李哥哥，你屏幕切过去吧。
已经在切了。
慧珊在吗？
在的。
你的 YouTube 已经切好了吧？
嗯。
李哥哥，你好了，说一声啊。
好了，老师。
李彪老师，请您露一个脸吧，我们开始了就。Okay. Dear friends of Digital Future community, let's coming back and kick off the second session. So in the afternoon, it's a great honor for us to invite Professor Li Biao, who is from Southeast University, to give us a keynote speech. Professor Li Biao is the Deputy Director of National Architecture Digital Technology Teaching Committee, the Deputy Director of Computational Design Committee of ASC, Architectural Society of China. And he is the Director of Digital Construction Committee of ASC. He is mostly engaged in the research and teaching of theories and methods related to digital technology for architectural design. Professor Li Biao has published more than 40 papers on various academic journals and conferences at home and abroad. His speech today will briefly on teaching and research exploration of digital design. So let's welcome Professor Li Biao.
Can you hear, Professor Philip?
Yeah, we can hear you. Please share your screen, please.
Okay. Okay.
Okay.
I thought it should in Chinese, but I just know it's in English. So maybe, but it's okay. My slides, most of my slides is in English. Thanks a lot for Professor Yuan for introduction, and thanks a lot for invitation from Tongji University. My name is Li Biao from Southeast University, and I'm leader of Institute of Architecture Algorithms and Applications. My topic today is any problem? My topic today is about teaching and researching exploration of digital technique. It's most of cases was finished by our institute during the past years. Okay, let's start. Okay, as we know, architects always rely on drawing to translate design information. Yet from the design to construction process, any data are usually missing during the actual construction, meaning detail cannot be precisely controlled. It's during the old time, I think, in the area of lack of computer technique. So any problem with my slides? I think it's okay.
It's okay, no problem.
Okay. Okay. In era of lack of computer technique, so such kind of unique design designed by Gaudi, and it's during the year like the computer technique. Normally it means a significant consumption of manpower and also time cost. So, but during the past 20 years, we know many architects, more and more architects are engaged in creating public tools suitable for architecture design, rather than satisfy just use a computer for only drawing, and treat computer as a algorithmic machine. So it's just the past 20 years, and this change mainly occurred in two parts. One is about the method of design, which means use algorithmic design tools, or even explore the algorithm for design. And the second is closely related to construction methods, such as use various type of CNC machines, and maybe the method are linked together. I mean, the methodology of design and CNC, such kind of CNC machines, they can be linked by a kind of system called a digital chain. And also, meanwhile, a few architects try to find tools that may be called a kind of super function, which show on my slides. What kind of super function? It means it can combine the rational element of analysis, logic, and so on, and also as well as emotional parts of creative or arts on the right side in my slides. So okay, any problem with my computer? And the architectural design process is often described as a block box, which present in the middle. So it's involved in mathematical algorithms or methods of optimization, and the import string on the left side contains various variables, such as different kinds of architecture rules that control the design results, and then transform the design and control facts into the parametrics that the computer program may understand. After run the program black box in the middle and output different kind of achievements from the right side. Maybe the result, the achievement, maybe a kind of technical drawing or CNC code, or even architecture itself. So it's a change during the past 20 years, I think. And for architecture design, normally it contains many control facts, such as functional or building or space, and context environment, context environment or form and construction, and so on. It's normally I show you in the left side, and but it's a pity that many problems in architecture are defined just as a EO structure problem. It's from the way of maybe from the angle of computer. I mean, from of course, as architects, we know many such kind of architecture concept. But from the way of computer, from the angle of the computer, it looks it's EO structure problem, which means sometimes we can't define very precise what we need to do. So it's so we need a kind of common prototypes leads to extract it as method, such as the surface division in the middle. I mean, in the middle my size, or topological, or and then translate into computer algorithms, and species data structure, such as half edges or pass found or collision and detection and so on. So we need to have our original architecture facts, and we need to extract a prototype of what we should translate, and then we do by coding algorithm on the right. So as a college, university teacher, we should consider how to integrate computer technique with traditional architecture method. So that's a very important things. So during the past maybe 15 years. In my university, Southeast University, we set such kind of how to say not so series or systems, but we just do it and try to set any courses which cover the undergraduate teaching and doctor research. We set several kinds. Just do it. So part of the student can attend our courses. Here is maybe any videos I can show below. For the lower undergraduate student, we can set we call a generative art. Which means how to say attract a student to be interested in program courses, because most student in the school of our architecture, they don't know, they don't like how to say racial things. such as mathematics or coding things. It's very boring for them. So how to attract them to be to think? It's interesting to set such kind of generative art. So how to translate the art to how to say to interest things by coding? Maybe I can show the result of the students' work. It was finished last year. So it lasts 4 weeks, and most students they don't know computer program things. So it lasts for the teaching of program. It lasts 3 weeks, and in the last week the student need to find any topic they like. So any student can do many how to say such kind of complex pattern things. So okay, it's such kind of things. Okay. So I just okay. So it's about no problem now. Okay. Any problem? Philip Yuan, any problem?
I think the video have some problem, but the acoustic is okay. The sound, we can hear the sound, but cannot see the video.
Okay.
Maybe the files is too big. The last, but this one is fine right now.
Okay, I don't know. It's a problem of technique. So for the I continue for the higher students. I mean in grade 4 and grade 5, a student can deal with any problem. How to say involved the architectural method. For example, use coding for architectural function, or thinking about the context of environment, and so on. So here is a video. I don't know whether the video can work. No problem?
Yes, this one is okay.
Okay. So it's a course in grade 4. A student coding and use coding find the shape of the pavilion and use KUKA robot to many different kinds of components, and then assemble together. Normally it's for grade 4 for the because the students, the architecture students, they like do models, they like assemble, things, they like such kind of pavilion. But on the other hand, they need to learn a little bit more about computer program. The pavilion was how to say was done by students, and after the course, the students know how to control Coca robot and something, and also the computer program. And then a lot of courses in grade 4 is about generative design, which means the student need to use such kind of tool, computer program for finish how to say design, architecture design. We will show any cases here, and so it's about the student. It's a kind of bubble, and use a defined area. Yeah. And the student knows how to deal with the algorithms about pathfinder and digital star, or the Voronoi, like which means we use a data structure of half ages. It's not so complex. It's very simple, and but the student need to know any algorithms, any data structure, and to get the result achievement. So. Not so complex. And during the student in master and PhD study, they were engaged in one topic. It may be digital fabrication things, or a topic of how to say architecture. For example, here is we finished Taihu Stone. It's near Shanghai and Jiangsu, but use a different way. Use how to say a different method and different material to finish it. Yeah. For master student, normally they do the real project. They must finish the real project. Okay, and also meanwhile they need to finish a kind of research. For example, here is a research for how to say to set the plots, the layout, the texture of a city. Let's imagine it's a block of a city, and then we predefined any plots in the block, and you can define the area of the plots, and then you can set the texture looks like field behind, and then algorithm, the coding can generate the texture like how to say according to field behind. And yeah, this is cases of how to say city texture, and with the blue lines it's a kind of disturbing element, and then every plot will optimize accordingly. So it's all this is just an exercise for our education course. and our generative design methods are mainly based on two parts of rules. Aspect of rule-based and data-based, and how to integrate computer algorithm into architecture effects. For example, the architecture function, architecture space, form, and context, or structure and construction things. Okay, this is a early case. It's finished 5 years ago, and it involved how to transform the functional relationship of building into optimization and process of computer. So let's imagine we can set the relationship of a house on the top left. And then the bubble chart, we call the bubble chart, it defines the relations between a house, and also they share the staircases in location, and define the functions of second floors. And then we set a program, and here is the first floor and second floor. They will adapt automatic, and in the bottom it's the visualize for three dimension. It's okay. It's not so complex, and the top left will show adding parametrics for achievements. It means we extract the problem for architecture function, and then we can define the area of building. We can define the relations between architecture elements, and then computer program can do many such kind of achievements, and every result is different. So all these achievements was generated quickly, but based on the same topology on the top left. So it means you finish the tool, you import the how to define the relations of rooms, and you define the area of rooms, every rooms, and you can get many achievements by programming. I like these cases very much. And here's another cases project about architecture, space, and function. It analyzes the combining of courtyard in we call Huizhou residential house, such as the feature is about space ratio of courtyard or building space or culture symbols. Because we know in the house, the residential house in Huizhou, they have a very typical style. So we did such kind of tool on the right, and you can define the shape of the plots, and you drag the red line of the plots, and then you will get a suitable layout of courtyard. So on the left, we present many such kind of achievements. It means we also can analysis the residential house in other cities, and then you can do it because we are architects. We know how to analysis the feature of the house. So we on the other hand, we can program. We can do how to extract the features, how to make it to digital in a digital way. So it's very free. Okay, and after we finished the tools, you can play around. You can play the result of the program, and you can text the computer. Computing power of the computer and get the a virtual Huizhou settlement, which means maybe you don't need the boundary of you can see the right video. We can get the endless the boundaries settlement. So it's just play to how to say to text the powerful of the computer. Okay, here is the case. Is another case is about the form. We also can. It was finished. It's nearly 10 years ago. It was finished by my colleague Hua Hao, Professor Hua Hao. And it can extract the any element of architecture and calculate the feature of floors or walls and so on, and then extract any elements of building, and we can combine this element and get the new result. Let's see what happened. You can define the link on the left. For example, A to B, B and C, C to the third floor for D and E. It's just a simple topo of the space, the link, the staircase, and then you can learn how to form the building. You can see. Yeah, it's you can set another link, and then you will get a different building. So this case is very funny. And on the left, it's just a user model, user achievement randomly just throw it on the floor. And on the right, we can get different kinds of new achievement based on the many cases we analysis by program, and then extract any features, and the computer can do design for us. Not bad. And another, how to say, we call it the first case we use data-based for generative design. And this project was complete maybe it's 4 years ago as a teaching and researching cooperating with university in Roma. So the principle of the project is very simple. It's just how to say getting the basic data on the OpenStreetMap, and also the functions of the buildings. For example, the POI data, and then search for the building group similar to the design site in the whole city of Roma. And then you can sorting it. The numbers of for example, the numbers of floors and the styles and area, and you can sort. We will show the video.
video 没有看到。没有看到。
So
video 还没有。
problem in
好了，来了。
OK，
有点滞后稍微。
OK。It's a pity. So this stake is searching on the whole Roma for the suitable building groups. So this is a key part of our digital tools. So we will get many achievements. How to say, according to predefined sites. It means you can define the shape. You can define the shape of the sites. Okay, this is the case finished by my post students. Okay. Any problem with my computer? Okay. We also need to think about the structure and construction of building. This case was just finished several months ago, and it was done by my master student. The case is how to say? I think it's a series of studies. How to say? Armed at finding the type of building structure. How to say? Defined by structure. So this is just a case of using or employing finity element researching. How to say? It's a concept. It's a method of in structure. So it's finished just several months ago, and then we can use this tool for finding how to say finding the shape. I think Professor Philip did many such kind of things, use finity element. But the course was finished by coding. So we can play with the algorithm and try whether it's good or not. And then we also can use. Here is a case of use coding. It's a real project, and employs a computer algorithm for finding shape and optimize structure. It's a case, and one is about structure. Another is about how to make it out. I mean, meaning it's about CNC meaning, and we need to predefined. How to say? It's a little bit complex to explain. The shape of the beam and we don't want to have how to say we need a beam, such kind of beam, not just the total things. So so the beam can screw around the surface. So it's a kind of play. It's kind of how to say how to make it clear. I mean the vectors, which direction of the pavilion of every vectors. So so all components was done in Nanjing and then transformed to Sichuan, Chengdu. So there are many things need to be think about. For example, the size of truck, or the size of CNC machines, and how many, how to say, whether the truck can go through all the nearly half of China, and yeah, many things need to be considered. And is a model of our pavilion, and this is the final result. Yeah, it's this is a photo, and maybe let's see whether the video can work. I don't know whether the video can show.
No, the video is not coming out, right? No.
Okay, forget it. So one picture is okay.
Okay, it's coming.
Yeah. I just shut down. Sorry. No problem.
But maybe several minutes slowly than your presentation. It's
okay.
Need time to just.
Let's move to another database topic. I think many professors in the morning has talking about deep learning or AI. Seems in our group, several students are doing this field, and also Professor Li, he will have a group in this how to say this time, and it's also about deep learning, how to use the principle of deep learning for architecture design. And here is a case, very simple case about deep learning things we did just now. Normally it has several steps for deep learning. I think the deep learning, how to say, the principle and the technique is not so how to say complex. It's because as we know, many how to say models has set by others, and then the key problem is how to translate how to say the architectural element into the LED work. Here is a case we just try to do it. It was finished by my student Zhang Baizhou, and his work several days ago. And just how to say, we also get the data from OpenStreetMap. We use PDF file, and then how to say extract all universities campus information, and then clean invalid the data how to say, this is just one word, but a lot of work, how to say, during program. And then obtain several types of the data from multiple angle and extract a data feature. Of that is cluster analysis and output visualize result. And then the fifth steps according to the how to say characteristic of integration, and the proposal and for recommendation and match. It's similar as the cases the case I just introduced for Roma, but it's we search on the we search the data on whole the global yeah. So we try a kind of you know how to say. So the problem is how to define and normalize the existing building site. So as we do for the import, you import data to the network, a neural network. You need to normalize any data. So we just try to use this method for normalizing the shape of the building. Just use a fixed number of point and the angle of each point to the center. The angles, for example, here, how many dots around, and then we just use this kind of method for normalize import data. And then here is any result we searched, and we want to map. We want to map use how to say the searching on the global and find the best fit situation to inform your target design site. So it's a kind of the system can recommend the achievements based on the global data. So here is the cluster diagram. Maybe I have oh, here I open the Any problem with my computer? No problem. So and we use the pixel to pixel taxi to technique to cluster the how to say the school campus like this. And then we use the system for recommending any achievement based on the right the sites. It's similar, and here the result is the campus of university in China. You can see in China campus in the right, always we have X in the compounds, but in the Europe we don't find X. Here we can find X. I don't know. This is Anyang. This is Asia, China. We also have such kind of X. Always have such kind of X. It's very funny. And we also can find how to say, this is on normal campus, and this is a similar campus in Dani University, and here is a similar result. And okay, this is my, how to say, I just present any of our achievements, and here's the last short move. We hope it can work. Yeah. So that's all for my lecture. Thank you very much.
Okay, thank you. Can you hear me? Hi.
Yeah.
Yeah. Thank you very much for the introduction and the great lecture from Professor Li Biao, who make a brief introduction of the systematic teaching process, which happened in the last dozen of years. Professor Li Biao actually set up a digital chain from the undergraduate to graduate study, and from the generative design perspective, especially subdivided into the rule-based and the database different scenarios to implement different kind of algorithms, including the cluster data analysis, and including the rule-based design methodology to implement this kind of methodology to not only the installation scenarios, but also the city urban planning scenarios. I think the most impressive is about the urban scale research, not only in the rural area of China, but also he leading a group of students in Roma. I think that is a very interesting research based on the city fabric and the urban fabric rules, which can generate the new era. Great systematic teaching and design methodology. I have one question. Firstly, goes to Professor Li. I think the generative design is the key methodology Professor Li Biao actually set up in his teaching, and not only his teaching, but also the practice methodology. From the very early version, cellular automata, which is like 元爆自动机, very fundamental rules, very simple rules, which can generate very complexity forms, and later goes to different kind of shape grammar, and that is based on sometime on the Voronoi pattern subdivision, and sometimes goes to more complicated rules, goes to like the rural area housing tectonic system, not only the roof system, but also the structure system, and facade system is all based on some kind of rules. And later goes to the city data. I think the cluster data is a leap forward, which can help to set up a database, and also training the database, analysis database, and also you need to clean the database based on a lot of work. So my question goes to, because this morning we also make a discussion on this about the intelligence, because the generative design is like a black box thinking simulation process. Could you give us some brief conclusion on your methodology in the past dozens of years, from the, I think it's cellular automata era to some like artificial intelligence era? Is there any difference in the generative design methodology through your research? So my question go to maybe a review, a brief conclusion in generative design.
You asked me the question?
Yes, yes.
Okay. So I think on one hand, we need to have a deep understanding of what architecture design needs. I mean, not only on one part, but on the whole, from the whole global side. We need to know about what's architecture need. Not only how to say, for example, now we have so many technique for digital fabrication. But on the other hand, if from the angle of engineering side, they think it's not real digital fabrication. I mean, as an architect, we need to think about such kind of technique in a global or in a bigger, how to say, with a big angle of view. And on the other hand, we should think about the how to say, the technique of algorithm. Every year, such kind of algorithms or method are make progress of we can absorb many how to say algorithms from other fields. For example, from graphic, from how to say from computer field. I just delete the ending size involved integer program and the linear program, and many before I had just delete ending size because it's too much. So it's about use the, how to say, use as we do, the integer program is just a concept from mathematics, a math. And then we tried tried to use it in architecture design, use the code. It's very powerful. It's very, and many cases of many facts of architecture design are involved such kind of method. So, and now during the past months, we try to use how to say, combine many different kinds of algorithms together, and for you know, it's not so easy to combine the codes from different kind of person. So it's not easy. It's a huge work. We just combined the algorithm because everybody have a different habit of coding. So we just want to combine together. Because we finished many how to say package, for example, Java package or a Python package, and then assemble them together, and then let's see maybe it will be powerful. We want to try such kind of tool for the real estate cases. We want to have collaboration and to the design institute and so on. Let's try it. Let's see. So I think there is a low end for exploring methodology or method for digital in a digital way. I don't know whether it's okay.
Good. I think Professor Li Biao has mentioned about the computation tools, especially the scripting could be a new instrument, a new platform, conclusion or make development by the certain team can give us a really important plugin toolbox. And based on years of development, this kind of plugin toolbox will be the key invention from the architect, future architect, or the research groups. So we're looking forward, Southeast University can announce your future plugin or digital tools in the near future. And at the same time, we want to announce this year we'll have a award on scripting from DigitalFUTURES. So we want to encourage the future architect, young generation, and also research groups, focus more on the scripting development. That is, could be part of the teaching topic and research topic from different teams. So we want to encourage future generation involve more into the scripting. I think the Southeast University play a leading role, a very important roles in the scripting teaching engagement into the education system. So it's great opportunity to have this lecture here. Thanks a lot to Professor Li Biao. Thank you.
Thank you.
Okay, I want to share my screen to the section 2. So the session 2 is, the topic is machine seeing and machine learning. I'm the session chair. Based on the schedule, I just briefly introduce how many, it's 1, 2, 3, 4, 5 papers in this session. So the first one will be, the author is from RMIT, Roland Snook and Da-Sung Wang. And the topic would be artificial students of generative design and approach and based on reinforcement and learning. The second one is about embedded GAN, a method to embed images in GAN latent space, and which is written by Zhijia Chen, Wei Xinhuang, and Ziniu Luo from Tsinghua University. So the third paper is real-time defect recognition and optimization, decision-making for structured timber joints. This one was written by Luo Dan and Jose Guetta, Paul Sichu Sean Tan from University of Queensland, Australia. And the fourth one is, the topic is exploration of campus layout based on generative adversarial network, discussing the significance of small amount sample learning for architecture. The author is Yubo Liu, Yihua Luo, Qiaoming Deng, and Xuanxin Zhou from South China University of Technology. So, and the fifth one is Cybergen approach of eco-interaction design based on the machine intelligence and embodied experience. The authors are Gu Yi and Ayla D. Carlo from UCL. So the first paper I want to give the screen to Mr. Da-Sung Wang from MIT, who will briefly introduce their paper. The topic is about the artificial agency, which exploring the operation of machine learning in generative design and digital fabrication. So welcome, Da-Sung Wang, Wang Da-Sung, please.
Thank you, thank you.
You can
Thanks,
share.
Professor Philip. Okay, I'm trying to share my screen.
Yes, please.
Yep. Can you see my screen, please?
Yes, no problem.
Okay. Hello, everyone. Great honor to present in this year's Digital Future conference for my first time. Thank you for the invitation and offering the opportunity. My name is Da-Sung Wang. I'm currently doing PhD research at RMIT under supervision by Dr. Roland Snooks from Architecture School and Dr. Fabio Zambetta from Computer Science School. The presentation is titled as Artificial Intuitions of Generative Design, an approach based on reinforcement learning. The presentation has particular focus on the operation of machine learning in generative design process. Several chapters are structured to demonstrate the design approach, including critical reflections to demonstrate the design approach to critical reflections on generative design and machine learning as introductions and background, and random walk-based design experiment as methodology and some further discussions and conclusions. Architectural design has been fundamentally impacted over the past 3 decades by the integration of emerging technologies and perceptual theory, which have contributed to the proliferation of generative design methodology. Among these, the rapid maturity of artificial intelligence, the massive increase in computational power, and further development of complexity theory provides a new perspective to reflect on future directions of generative design, architectural design. These several images are listed as both emerging generative research and their practical applications of architecture projects in different scales across the world. While these generative design approaches are capable of compelling and sophisticated design outcomes, a series of limitations still exist as obstacles towards its further development. For instance, some parametric-based approaches relies on the linear relationship between parameters and the system, which leads to the outcomes that are limited to their predefined conditions. While some behavioral-based approaches privilege micro-interactions over macro-awareness, establishing a global ignorance that limits the integration of overall design intentions. In addition, some real-world materialization and structured performance within nonlinear generative design process still remains to be problematic. Based on these reflections, the research speculates on a generative process driven by machine learning, which is capable of gradually developing typical and specific intuitions towards a series of design intentions. In natural process of evolution, intuitions emerges from intelligent creatures' inheritance of long-term accumulation of knowledge. Similarly, the approach posited in the research is tended to form a higher level of design intelligence within generative design by undertaking a self-training, learning, and incrementally evolving process. The proposed intuitive generative approach is inspired by the development of a machine learning technique. There are significantly increasing number of researches has been conducted on the application of machine learning in architecture and urbanism field, as shown in this year's Digital Future conference. However, I would like to bring up some of my speculations of three different types of machine learning and their in regard to their potential impact on existing 3D generative design process. To begin with, supervised learning is essentially an algorithm that trains a predictive model with labeled datasets. In terms of its potential application on existing generative design process, firstly, supervised learning relies on massive datasets, labeled datasets, with which the collecting and labeling process is probably considered as an inefficient process. Secondly, the feedback from the two sets of the artificial neural network is normally a non-sequential procedural regardless of the information passed during the generating process, which might be opposed to the ambition of existing generative design. Additionally, the digital representation of 3D geometry is still a problem with supervised learning, especially on the further development of 3D GAN. Comparatively, unsupervised learning is based on training a clustering or association model with non-labeled datasets. Generally, unsupervised learning doesn't have a very clear training objective, so fundamentally, the approach of applying it with generative design is still under exploration. However, reinforcement learning is closely associated with the field of optimal control, in which an agent seeks an optimal policy by interacting with its environment through a feedback between observation states and quantified rewards. I will talk about reinforcement learning more in the next several slides. There are several key elements in reinforcement learning algorithms, including observation states, agent actions, reward, and policy. Due to that, there are some detailed paragraphs demonstrating the mechanism of RL in the research paper, so I will directly skip to my reflections on it. Theoretically, reinforcement learning seems to have strong correlation with an enormous potential impact on existing generative design process. As a reason, firstly, reinforcement learning operates in a heuristic mode with no direct human knowledge, which is opposed to the labeling process of supervised learning. Secondly, reinforcement learning operates on a sequential decision tree rather than the simultaneous process of massive datasets, which is suitable to be implemented with the evolving generative controlling process. In addition, reinforcement learning seems to be less problematic with 3D environment, as there are multiple technical approaches to implement with, such as the GEM toolkits by OpenAI and ML agent toolkits within Unity platform. As the fundamental method, the intuitive design approach aims to integrate reinforcement learning with existing generative process, in which RL is acting as a brain to further control the computational system instead of creating an entirely new procedure. I would like to further explain it with a design experiment initially developed since 2018. Although the design experiment is based on a simple random walk system, it comprehensively shows both theoretical and technical method of applying RL within generative process. As shown in this diagram, the goal of this example is to train a random walk with a series of basic architecture intuitions initially inspired by Le Corbusier's domino system, and further developed with some more abstract and complex design intentions. With the implementation of RL, it is expected that the opposing character of random walk's stochastic mechanism and the domino system's formality character can be integrated with a synthetic design process. Reinforcement learning algorithm relies on the definition of 3 key elements: actions, observations, and rewards. Within the training framework, the RL action can be based on the underlying generative system or customized method to further control the generating process. It normally depends on the character of the system itself. In this case, the definition of action is that an agent takes random decision to move towards 6 directions within a predefined 3D voxel grid, and the walking trail is recorded as a generated form. The definition of observation states describe the current condition within the generative process, which normally consists of two types of information: the overall digital representation of the form and a series of reward-oriented values. In this case, the form is converted into a matrix of integer representing a Boolean whether the voxel is occupied or not. As the most critical part of the RL training process, the reward definition is normally an evaluation structure based on design intentions. In this case, several reward functions are set up based on an extraction of the domino system, such as some tower topology, structural logic, spatial connectivity, and spatial creations. I will skip the technical details of this as they are well explained in the paper. The random walk design experiment operates with a customized deep Q-learning algorithm in Python and TensorFlow environment. Totally, there are 10,000 training episodes have been undertaken. What I present in this slide are some training samples that are recorded every 100 episodes. Overall, the training result is quite successful. The character of form generated through its process evolved unexpectedly over time, creating a clear sequence of design intentions. We can see that from the initial several episodes, the system doesn't generate any effective intuitions. However, in the followings, it starts to understand the predefined intention as tower type. Throughout the training process, the response to structural logic, spatial connectivity, and spatial creation are slowly improved, becoming more and more obvious in the final episodes. Despite that all the rewards operates simultaneously, the process generates a multi-stage character that achieves one significant reward prior to addressing the others through a gradual process of improvement. One of preferred generated outcome has been selected and further developed into structures and platforms with a set of algorithmic operations as shown in the render. As some reflections, there are some obvious limitations in the random walk design experiment, which result from using a single walker to generate form within a low-rise grid. However, it still shows concrete effects and a significant flexibility to be integrated with other existing generative design processes in different domains of research. Based on the random walk case, a number of research directions are emerging from the application of RL on generative design and digital fabrications. This is one of a design experiments I'm working on in regard to integrate RL with complex behavior-based generative approach, typically a mesh growth system. This case aims to train the system to make sequential decisions of undertaking complex generative behaviors to eventually augment the typical simulation and selection process. In this case, a number of techniques of defining the RL actions, observations, and rewards with complex generative system are under development. Those techniques are expected to be demonstrated in the following publications. As conclusion, the proposed reinforcement learning-based design approach integrates heuristic design intuitions within existing generative process, which enhance it by establishing a greater level of sophistication and design capacity. The research also aims to indicate potential ways of applying this emerging tool to existing design methodologies, as well as anticipating the future correlation of designers and computational intelligence. So that's it for my presentation. Thank you all for your attention.
Okay, it's a really good presentation. I think we got really familiar with Roland's methodology. Years ago, it's from like a swarm intelligence, which is a totally bottom-up rule-based design methodology. But this time we see a totally different methodology based on the reinforced learning. Actually, that is a different information, totally different generative process. That is the interesting part you mentioned about the action, observation, and the reward. So my question goes directly to the detail. I find some weight in the, you make decision about the reward. Can you give us some introduction on how you set up the weight proportion, or how to make decision on different kind of weight in the design process?
So in terms of the weight, actually, I think reinforcement learning itself is a multi-objective kind of optimal algorithm that normally deal with multiple rewards at the same time. So when I trying to set up a multiple reward, I think a key thing is to set up a hierarchy structure with the reward. So for example, we have several rewards that is predefined. And so when the agent achieve two of them at the same time, so it will get an additional reward based on that. So actually this is a similar, this is a very related field called hierarchical reinforcement learning, which I think is very
question goes to if the weight system kind of optimization process, is there any relation from the weight decision making with some structure optimization some integration, collaboration with certain kind of tools, not maybe just reinforced learning? Is there any other input, protocol input from other software in this process?
I think I didn't quite get the question. So
yeah, I mean, the weight process is like different resolution, different density of the action of components. So is there any objective or design motivation which can totally make decision by the structure, for example, the structure performance, which can actually influence the weight of the density of your components? So I mean, is there any input to the parameters to make decision about the weight of your system?
Yeah, I think so. I actually very recently I'm working on some project that is using some structured performance, like for example some FEM structure analysis as a reward to train a model with some structured performance, for example. I think that's also a very interesting and very practical way of applying RL. So I think that's really associated with some workflow that's using RL with some other structure analyzing softwares. So I think, but there are definitely some ways of doing that, like creating an API between two softwares and sync the data real time. So I think that's a very interesting topic at the moment.
Okay, thank you. Thanks for your presentation.
Thanks.
Song Wang, thank you. So let's welcome the second paper, Embedded GN, mastered to embed images in GN latent space. So author today here is Zhijia Chen from Tsinghua University. So please, Chen Zhijia, you can share your screen.
Okay, can you see my screen?
Not yet.
I'm sorry.
Maybe we should wait. Okay, it's coming.
Okay, thank you. Thank you for the introduction. And I'm Zhijia Chen from Tsinghua University. And today I'm going to talk about the.
Sorry, could you maybe it's right now it's not sharing the screen. It's
okay.
sharing the screen. It's not sharing the presentation. Could you change the sharing screens by a different model?
Okay.
现在就是看到的是没有播放的状态。
哦，好的。
所以在共享屏幕里你选一下。
哦，共享屏幕里选一下，好的。
你点共享屏幕的右边一个，然后你可以选。
或者我先停止，或者。
Right now it's okay. Good. Keep on.
Could you see the full screen of the slides or?
Yeah, right now it's you quit, but the last one is good.
So can you see the second slide now?
Play the PPT right now， 就是播放吧，现在。
我已经播放了，所以可能还是我看一下，要不我重新共享一下。
重新共享一下 ，OK。
Could you see my screen now?
Very slow.
Could you see the slides?
Not yet.
But slow. 现在屏幕有在放幻灯片吗 ？Okay, thank you, thank you. I'm sorry about the delays, and let's start from the GAN latent works. And proposed in 2014, and GAN is widely used to generate images. And GAN latent works allows us to use a pre-trained generative network to generate images according to our control or according to our need. And also the advantage is that there's no need to retrain the model. So this is how the GAN latent walks work. Firstly, we have to input latent code to the GAN generative network, and then we get an image. And if we modify the original latent code, we got a new one named latent code 2. If we input the latent code 2 to the generative network, and then we get an image 2. So this is how it works. Like it is like we walk from the image 1 to the image 2. And if we repeat this process, we can have an image sequence. And that's how we use latent walk to generate image facing our need. And here is a classic example of GAN latent walks from the DC GAN. From the example, we can see that the author start a walk from a face facing, looking at the left, and then he used a latent walk to generate images facing to the right. And so it is a typical latent walk example. However, every GAN latent walks must start from a randomly generated image. So we can't even start from an image in the training data set. That's a problem of GAN. And all the related work shows that researchers have used CNNs and ACT to search and regenerate images from a pre-trained generative network, like the X one. The X is a target image, and the GEX is the generative image. However, we can see that there is still a gap between the generated image and the target images. And also, there's a model named GLOW can fix this problem. It can generate images from the data set. However, it had a huge computing cost, and also it is not even a typical GAN model. So our goal is to embed selected images in GAN generation distribution so that we can embed an image to the generated network, and then we can start a latent walk from the selected image. And also, we want that the network will hardly affect the parameters of the other part of the generated network, so that we can still perform latent walks at the same time. So firstly, we had to figure out why GAN just can't generate images from the training data set. Explanation is that as if we see GAN as a mapping between latent codes and images, there are feature information loss due to the latent codes and read look and other activation functions. And so that the discriminative network can hardly learn low probability sample features, just show like what's shown in the curve. The GAN generated network data distribution is much more narrow than the data set. So our solution is that if we just want to embed an image, there's no need to modify the architecture. Maybe we can just fine-tune the parameters of the generated network so that we can embed some image in the data distribution. So also we can have the advantage of low computation cost and short training time. So we try to figure out a way to fine-tune the network and embed an image. And experiments shows that the generated network will be distorted if random codes are assigned. So the key point is to find an appropriate latent code for every selected image. And that's why we decide embed GAN. Embed GAN consists of a generated network and an embedded network. The generated network is only to generate image, and actually it is a pre-trained model from the DC GAN, which contains CNN layers and batch node layers. And also we designed the embedded network. The embedded network E, its main function is to search the appropriate latent code for every selected image, and it consists of CNN layers and full connected layers. So here's how it works. Firstly, we input a real data or a selected image to the embedded network, and to the embedded network E. Then we got a latent code Z. We input the Z to the generating network, and then we get the output image, a picture fake. We calculate the difference between the picture fake and the fake picture and the real picture. And according to the difference, we optimize the embedded network and the generating network. So our optimization goal is to minimize the difference between the two between the two pictures, sorry. And the training process is like the generating network. We choose the generating network from a pre-trained DC GAN, which can generate interior design images from a good website. And then we select 64, we randomly select 64 real interior design images to embed in the generating network. And as shown in the figure A, here are the 64 selected images. And at the beginning, we can see that the generated network can hardly generate pictures similar to the target images. And however, after 150 inputs, the generated network now can generate images very close to the target images. That's our result. The embedded GAN that generate images close to the target. And if we have a look at the below figures, here are the images generated from a fixed noise from the generating network. And after the training process, it can still generate normal interior design pictures from the generating network, which means that embedded GAN can still generate rich interior images beside the selected images. So here we give an example. We select randomly a picture from the good website, like this left one, like this right one, sorry, and we perform latent walks. We perform latent walks by the heuristic searches on GAN latent space, which means we actually train two classification network, and one is to classify the materials in the interior design. And here shows the latent walk. We can walk from the selected images, and then we make the generating network to regenerate images in the certain feature direction. And we also try country styles classification to do the latent walks. And also we can get, you can see that from the sequence, the image shows the interior design is more like a Chinese style, which means that with embedded GAN, when we use latent walks, we can regenerate the selected real images into a certain feature direction. We also evaluate the performance of the embedded GAN, and for two aspects. Firstly, we want to figure out the difference between the regenerated images and the original ones to know that if we really embed the images into the generating network. And MSE and SSIM shows that the embedded GAN really generated images very close, get very close to the selected one. And on the other hand, we average the quality of the random generated images. We put the embedded generating network and the original generating network. Yes?
Yes, one more minute.
Okay.
Yeah, time.
Oh, okay, thank you. So we tested our generating network by the same discriminated network, and we found that the embedded GAN has a larger loss function. However, under the condition of generating design intent, the loss of the image quality is acceptable. So to sum up, we propose a framework include an embedded network and a generative network. And we embed we reach the goal to embed any selected images into a retrained GAN. And we take both computation cost and image quality into account. The quality of the generative network has declined to some extent, but still in an acceptable range. So we propose a method to fine-tune again, and it can be a tool to explore the intention of design. And here's all about the embedded GAN, and thank you for listening.
Good, good. So one quick question. When you're training your database, normally the embedded images, how many embedded images you give to the database?
64.
64.
As a batch. Yeah, a batch.
Yeah. So I want to, could you tell us the difference? Because this kind of GN is a little bit similar to style GAN. The style GAN is like two images, like one to integrate the two images together. But the embedded latent space GN is like more like embedded some image into a database and to do kind of implementation. So could you give us some description on the difference between these two GAN methodology?
Thank you for the question. And for the style GAN, actually we can choose what kind of materials or what kind of information we want to add to the data. They just know for the multiple layers, every layers add some details on the image, but we don't know what exactly it adds to the image. However, in the embedded GAN, we can choose some selected, any selected images. We can embed it to the generative network so that we can start our latent work from any selected images. And I think that's the difference. Because we can choose it. Yeah. Thank you.
Thank you so much. We should keep. Yeah, thank you. So the next paper, the topic is real-time defect recognition and optimized decision-making for structured timber joints. So is Rodan here? Yeah. Rodan, please present the paper. Yeah.
Thank
you. Share the screen?
Yep, I'm coming. One moment. Let me share my screen. Is everything looking all right?
Yes, we're waiting. It's in several seconds. Okay, it's coming out.
Okay, it's coming here. Okay, so the name of the paper I'm going to present is called Real-Time Defect Recognition and Optimized Decision-Making for Structured Timber Joint. And this is a paper, so I'm currently a lecturer in School of Architecture in School of Queensland. And this is a collaborative between me and Joseph Geddes, who is a senior lecturer at the School of Engineering, and Sean from University of Pennsylvania. And this is a industrial sponsored project, so it may involve more practical. It's developed to tackle a practical problem that the industry currently face. So in the timber mill, parallel to the production of the structurally graded timber, owing to, as we see, the timber as a natural material and the uneven growth patterns, there are over 50% of the timber sometimes are become this kind of undergrade timber because of the defects and the structure failure that fail the structure grading test. And currently, there are a few methods to salvage those timbers. So one common strategy to recover those unusable undergraded timber piece, or to recut and remove those defected area and rejointed the, let's say, the good part of the timber together with structure finger joint, so that they can reconnect them to this very standard full-length structure timber piece. And so this paper is trying to use real-time decision-making, like machine learning algorithm and some image processing to automate this process. And currently, this is like a preparational work for industrial applications. So we did build a simulation platform to show how the system works and what is its capacity and in terms of accuracy and efficiency. So this is the interface that we developed just as a demo project to show how the system works. So the entire system mainly have composed of two parts, and the one is to detect the defect and process the timber image, and the second part is to connect the salvaged irregular pieces to the maximum efficiency and to reduce the waste. So the first part for defect detection in the timber processing, there are 4 main steps which echoes that what it's going to be in when applied in the industry. So the first step is to have this kind of image denoising process from the raw image inputs, because the one idea of this process, this system is that you can connect this one to the existing fabrication process just by adding an external camera that watch the pipeline of production without additional cost, which the cost of changing to the hardware is relatively low because it's only adding an additional camera. But of course, there should be some image processing part that deal with the raw image collected from the image. Also, the second step is to remove the background and undistorted image. This one was to prepare the image for image processing. And the step 4 is with the clean the image, and we use them to calculate the probability map to locate where the defects are. And the step 4 is, of course, to cut the image, or in reality, it's like a cut the timber based on the probability distribution of the defects along the real timber. So because this is a simulation process, so indeed we used those images was actually provided by Hein Timber. So it turned out that they do have a structure grading process, and during the structure grading process, they would automatically scan and collect the scanned image of each individual piece of the timber, so that this quality of the image was a lot better than we have expected. The only elements that to clean during the image preparation is to remove the noise at the edge. So we developed the algorithm to find those kind of spikes of noise and how to clean them to have this more clear trimmed edge. And the second aspect is to undistort the timber. So the undistortion of the timber may mainly come from 2 aspects. One is the movements. For example, sometimes during the scan process, the timber shifts position so that there is distortion in the image. And of course, there are another alternate possibility is that the piece of timber is bended by itself. So in this case, we were able to detect the degree of distortion. So each of them, this piece was 4.8 meters long, and this one, all the image review here were distorted to 1/6 of the length in the longer axis, just for better representing to fitting the image of the timber on screen. But so this one is actually, in reality, it's stretched a lot longer by 6 times on the horizontal axis. So that we were able to detect the curvature on the edge, and that we would decide either to remove the curved part, or if it's a mildly curved, then mainly due to the problem during scanning, we would undistort the image, and by shifting the distorted back the areas to align them along the axis, the flat axis. So in the third step, so now we have this kind of more, not say perfect, but more coherent piece of timber image as you see on the top. The step 4 is to calculate a probability map to locate where the defects are. But there are a few issues about the probability map because they're like currently in the timber industry, they would have like a person that has a marker that sit there and just mark out where the defects are. Like, so this is a very subjective manual process. So initially we used API called the Weka segmentation. So that was like a system that they could indirectly ask the workers to manually mark them out, and they would analyze on where like they visually believe the defects are, and we would generate the probability map based on the inputs from the workers. So if you see like the image B are like the workers who sort of manually sketch and label the defects are. There are 3 colors. The red color are the zone of defect, and the green color are non-defect timbers, and the purple or just background in the original image. In this case, I noticed a lot of us are using the neural networks, but in this case, we didn't really use neural network, but we rather use another machine learning system like the decision tree. So the algorithm we used in this case is a random forest classifier. And the one benefit of this one is that like we can have this kind of quality of segmentation just by 1 or 2 pieces of training data. So basically you only ask the worker to mark like 3 pieces of timber, and we can already get a very high results accuracy on the result. And this is possible because like the defects on the timber, like more or less, at least in this batch, follows a very clear pattern, and it was not that computationally heavy to be separated from the non-defective timber. So on the right in the image CDE are the probability map we generated for when inputting the image A. So the image C is a probability map for the good timber, and the image D is a probability map for the defect, and image E is a probability map for the background. We were thinking of using this one for removing the background, but it was not really used in the end. So based on the, and of course we were able to cut the timbers based on the probability map. And sorry, I think I'm missing one slide here, but basically is that it will read this image D in the probability map, and we do have a algorithm to identify where the, let's say, because we can only cut it against the axis, like let's say cut on the shorter directions. So basically we will just calculate, for example, in each section and the slice of the timber, if there were over 5% of timber that have a defect probability larger than 75%, then these slides should be removed. And we only remove defect slides that are wider than 5 centimeters, and we only keep the good pieces that are longer than 20 centimeters, which was like an industrial criteria. It doesn't make sense for us to remove like very short defects, thin defects, and nor like connecting segments that are maybe only 5 centimeters wide. So these are like some threshold we use during the removing of the defects. So after that step, we would end up with a lot of smaller pieces that are of arbitrary length. So they can varies between 20 centimeters to a full length, which is like 480, like 4.8 meters. each of them are like very varied in length that we have no way to control. But now the challenge is that how do we connect those smaller pieces to a full length? In this case, we use a standard full length, it's 800 millimeters, but we did adapt this system so that it can be, can have like arbitrary target length. So if we were looking for a more customized set of panels, it was able to fabricate and utilize those smaller pieces to connect to any arbitrary target length. So the problem during this process is that it's not like we're going to have a static stack. So it's not like we're going to have 3,000 pieces laying in the stack and try to sort it out. So because the timber pieces are coming like one by one, so we're having a stack that are constantly joining and constantly having new pieces coming in. Sorry, one more. Sorry, my kid is like screaming next door. So this is a challenge of this kind of dynamic on-the-fly decision making. So in this case, we tried different options. So one options we use is like the original one is called exhaustive recursion, and the having a exhaustive recursion is to have like check the combination of all possibilities, but this one was very computational demanding. So basically you would crash your computer with like 13 to 15 pieces in the dynamic stockpile. And so we use another like backtrack logic that would more like from like ends up that would immediately increase the efficiency of the system and was able to make decision within seconds when the new stockpile comes in. And this has proven to be very efficient. So in this case, this is like one of the processing of a randomly selected 10 piece of defect timbers, and on the right we will see the jointed timber piece. So there are like 7 full-length pieces that jointed from the smaller segments, and we would say the target length is 400, and the most of them was able to meet the 400 exact with the combination of the smaller pieces, and there are only one piece was not able to meet the target length and having a little bit of leftover that need to be cut out. So this algorithm we developed for the on-fly like decision making on which piece to connect to each other is very efficient in terms of salvaging the smaller pieces. So we were able to meet the target length with smaller pieces without any much of a redundancy to. And on the left is a condition of our dynamic stockpile. So those on the stockpiles or those smaller segments that has not yet be connected together. And here is a chart on the change. So we can see until this is at the first 20 iterations, and we can see the dynamic stockpiles are very, very low. Yeah.
1 minute.
Yeah, and I'll just quickly show this one. So this is recording of the simulation so that we were able to see like input of the each piece and what's happening in the background, how was it cut. Sorry, I need to fast forward this a little bit. So that's like you can get another piece and getting another piece so that you can see, we can see that there are complete components that are stacked on the right and there are like smaller segments in the middle. So here are a few features of the interface that we were able to change the pre-trained classifier. So we still can calibrate a few nuance of the parameters and generate classifiers of different quality. And there are options to view like the completed pieces that we have connected. And this one I'll just quickly glance through. So those were some of the future developments. So one issue we noticed is that we relies on the workers, and the workers they relies on their experience, which are not very accurate in terms of identified defects. So we use those kind of MOE testing, like module of electricity mechanical value from the mechanical grading to further calibrate and recognize where the defects are based on the scanning and the module of electricity test collected from the industrial grading machine. And here are just some of the future works that we're doing, just quickly going through. So this is the work that are sponsored by Future Timber Hub and our industry partner Hein Timber, and ideally should be connected to their fabrication process in the future. Thank you.
Good. It's a really interesting research. I think it's to the timber industry, it's extremely important to make material performance pre-defection before the laminate process. So first question goes to in the industry actually, because I visit in German and the Swiss some timber CNC factory. And they actually have certain kind of tools in this kind of defecting process by different kind of software, and also have some optimization and show the efficiency, how efficiency we can integrate different kind of cutting panel and to laminate them in big pieces. So could you give us some special introduction on the difference about your updated version? Have any comparison with some German version or European version of such kind of similar technology? Could you give us some introduction on that?
So I think a lot of the German technology and at least in the industry, they are more relying on the mechanical grading tests. That's what I showed in the last part. But the issue with that one is that it's very effective in, let's say, structured tests. So you can just pop in a piece of timber and it will give you all the criteria or parameters on how structurally sustainable or how efficient that is. But the one thing, at least from our industry partner, the feedback is that that system is very, let's say, closed sourced. So it's very difficult to connect that system to their other machines. So for example, like the one that is cutting things and or the one that is joining things. So that test was a lot only for evaluation. And but in fact, how to joining things. So currently the joining process is only sequentially. So they just join the first piece to the second piece that's coming and the third piece that coming and the chop off whatever is remaining. And the defect detection process currently is just experienced worker with a marker to mark them. But of course, after a lot of them were jointed together, they do have very dedicated structure grading system to test each one of them. And so they would have a feedback on how efficient the system is. But the problem is that information gathered in that system is very difficult to communicate to the fabrication process. And they were thinking if they were able to use the image recognition, so they can just basically add a camera to the fabrication system, and it will be sufficient to get the information they need to calibrate and automate the fabrication system. And also they have mentioned this application is it's just like the first step of collaboration, but they have mentioned this one is more useful in maybe other aspects, for example, in lamination. So basically for lamination, they would want team laminate the different panels, but they don't want, let's say, defects to stack upon defects. they would want some like better piece to the better, more stronger areas to stack on top of a defect, so they have like more even distribution of the structure quality. But currently that part is only like by human visually trying to make the decision, or they would just randomly laminate them and get rid of the bad pieces if some of them later fail the structure grading test. So they were thinking just by adding a little bit of like this kind of visual computer vision and the machine learning aspect, it could help them a lot in the fabrication process.
Okay, let's keep the time. Thank you. And
thank you.
Wait to the panel discussion. And I would like to invite the next paper, exploration of campus layout based on the generative adversarial network, discussing the significance of small amount sample learning for architecture. So let's invite Qiaoming Deng to make the presentation from South China University of Technology, please. Yeah, you should turn on your microphone. Right now, cannot hear you.
Oh, no, it's okay.
Okay, okay.
Okay. Can you see my screen? Okay. Good afternoon, everyone. My name is Qiaoming from South China University of Technology, located in Guangzhou, China. It's an honor to have opportunity to present our research here. It's about exploration of campus layout based on generative adversarial network, discussing the significance of small amount sample learning for architecture. The research was done by Professor Liu, Lecturer Zhou, undergraduate Yihua, and me. As we know, in recent years, the tide of artificial intelligence is turning again. Machine learning is becoming an inevitable opportunity and challenge in almost every discipline, of course, including architecture. Some scholars have also tried to make exploration in the field of architecture in combination with machine learning. Among them, layout design has always been a research hotspot in field of AI, such as document layout, game map layout, and interior furniture layout. In the field of architecture layout, Paul proposed a method of auto-generating residential building layout based on Bayesian networks. And Lubin proposed a method to complete the missing facade layout with a statistical model and a planning algorithm. And this is a previous study by our team. We try to expand the existing 15 samples to 140 samples in the form of artificial data augmentation and explore the generation of specific architectural forms through the neural network method. In recent years, the development of deep learning has provided new ideas and methods for architectural layout. Professor Huang and Dr. Zheng use generative adversarial network for the recognition and the generation of apartment floor plans. And Stanislas Chu's network nested gains to generate a furnished floor plan from the puzzle. Use about more than 700 floor plans as samples. And Professor Wu proposed the CNN-based method to generate floor plans for residential building with given boundaries. And they select more than 80,000 floor plans to construct a database. And David tries against to generate floor plans with the style of Le Corbusier and discusses the effectiveness of different augmentation method when dealing with small amount sets, like rotating and mirroring. In the above work, we found two ways to collect and filter data samples as data sets. One is to use thousands of samples for training, for filter the samples in a statistical manner and to obtain a universal loss, such as Professor Wu's research. And the other way is to use a small amount of sample data sets for training to filter the samples that meet the training standards and only to master the laws of its particularity, such as David's research. So in our research, we adopted the latter method and construct specific sample data sets through artificial selection according to the value orientation and aesthetic tendencies of specific architects, and use a small amount of sample for deep learning training. Our research expected goal is generating a reasonable campus layout under the condition of the given campus boundary and surrounding roads. According to the character of campus layout, the value orientation of specific architects, we have selected 302 primary school samples and 85 university samples. Below the picture are the specific rules for primary school and for university. We selected the PIX-to-PIX model. The generator uses the UNIT framework and the discriminator uses the Pascal framework. By inputting a picture of the actual campus boundary and the surrounding roads, the outputting corresponding pictures of the campus layout. This is the labeling rule of training data, and each color represents an element. The left is input and the right is output. The bottom is labeling blue rule. The color selection in the image is related to the RGB value range of the color to avoid recognition errors. For the primary school, the experimental results shows that the model has learned the laws of layout. The left of the page shows the selected results from the test sets. Compared with the real layout, the number 2 and 65 has a more reasonable relationship between the teaching building, the gym, and the stadium, leaving a transition road in the middle. And the number 301 pays more attention to the north and the south orientation of the teaching building than the original sample. And yes, there are also some poor layouts. For example, the 2 and 75 fails to generate a complete teaching building groups. And number 2 and 94, the campus interest is not reasonable enough at the intersection of roads. But the main building chooses north and south orientation instead of parallel of the surrounding road. And the right of the page is an interactive website for generating primary school. According to the surrounding road, like grade, shape, and the land ridge, rectangle, polygon, you can freely draw in the input box. And after a few seconds in the output box, can help designer auto-generate school planning layout scheme based on the site condition. For the university, due to the complexity of the campus layout, we split the training process into 2 steps. The first step is to train a model that generates the mean functional zoning of the campus based on the campus boundary, surrounding roads, and the surrounding functional distribution. The second step is to train another model, which is based on each functional zoning of the campus and the generates the internal architectural layout of them. In this way, a complete campus layout is achieved. The left of the page are selected results. Top is the first step. The final effect reached expect from the perspective of zoning, functional zoning. The generated layout is highly consistent with the original plan, forming obvious layout pattern of the loop traffic system and the central area, and also forming a continuous campus walkway from the entrance area to the central area. And the button is the second step. The final result is also relatively successful. The output results not only get the loss of orientation of building layout and stable building spacing, but also coordinate the relationship between the building's public space and the water in the central area. Unexpectedly, the layout of some buildings also reflects the overall style of lightness and flexibility, which is pursued by the design company. The inspiration of this study is that when combining the field of architectural design and AI, we should pay more attention to the particularity and the difference in architecture. Find out our own road, not just follow the way of computer science. In the field of architectural design, the design issues we are considered with are not only related to the universal laws, but also related to the value orientation and aesthetic tendencies of specific architects. The particularity and the difference of these projects result in the richness of architectural works. So this character of architectural design makes it possible for the training of a small amount of sample data size to achieve a good effect. Okay, that's the end of my presentation. And for more information about the training process and the data, please follow up with our WeChat link. And thanks for listening, and thanks for CDRF conference. Thank you.
Okay, thanks a lot to Professor Deng. I think you make a fabulous presentation, which based on the GN algorithm, especially focused on the scenario of the campus design. So I have one question about the database you set up. You're talking about 302 primary school and 85 universities as a database to training the GN. So my question goes to the number for the campus data. Do you think it's enough to train the pix-to-pix algorithm to design a campus? Do you think the database is big enough?
Yes. Yes. I think why we choose the pix-to-pix it's not pix-to-pix HD because I think the goal is different from computer science. Sometimes very similar with original sample. I think it's not best for us. So how to evaluate the learning model, which model is better, I think we have to our own road and our own way. Yeah. So I think 85 samples to train the learning model is okay for us. Yeah.
Okay, thank you. Thank you very much. Please waiting for the panel discussion. And then the last one in this session, I would like to introduce Cyberging approach of eco-interaction design based on the machine intelligence and embodied experience. Let's welcome Yi Guyi, who is from Shanghai Tongji Urban Planning Design Group. So welcome.
Hello. Yeah, now I'm trying to share my screen.
Could you turn on your microphone? Right now, I cannot hear you anymore.
Yes, but I didn't find the way to share my screen.
Actually, it's in button with a, yes, it's coming.
Right now, can you see the slide?
It's white slide right now.
No. Sorry, and how about now?
No, it's not coming out.
Oh, I'm sorry.
Could you share your screen?
下面有一个共享屏幕，你看到吗？那个按钮。
哦，我知道，我知道。
On the bottom.
Because I'm using the iPad, so I don't know how to share the content in another app.
Can you share your presentation slide in the chat room? So I'll play it for you if you can't play it on the spot.
Could you send your PPT to like Yao Jiawei and other members here? Probably they will help you to present. your PPT.
Okay.
小嘉伟，你可以问他要一下，你帮他放一下吗？你需要移开这个窗口，现在这个窗口挡住你了，你要把这个窗口在你屏幕上移开，然后你再放就可以了。
嗯。
你的这个窗口挡住了你那个文件的窗口。The real files are actually behind this. 如果这样，我们要不然就先做 panel discussion， 你放在下个 section 里面，下面一个 section 里。
好的 ，OK。
Okay, I would like to invite all the speakers in this session. Shall we make a short discussion, panel discussion here? Please turn on your video. Let's invite is Das. Yeah.
Yeah, sure.
And Chen Zhijia. Is Chen Zhijia here? Professor Deng. Is Professor Deng here? 邓乔明，邓教授在吗？ Okay, maybe we could start to make some panel discussion. I think it's a great panel, and all the presenters give a super good presentation, and most of you especially focus on the GN, some artificial intelligence tools, and implement them in different kind of scenarios. Actually, that is really popular this year, not only in this conference, but also the other conference as well. So my question firstly goes to the design and thinking process, because if we go to GitHub, we can find this kind of algorithm, fundamental algorithm is there. And actually, it's a cross-discipline scenarios right now. We implement this kind of very basic algorithm to implement them in architecture discipline. So I can find out some very similar approach, because the algorithm logic is actually similar. So do you think this kind of thinking design approach should in the future will control the design thinking from the designers? Do you have any feedback on this kind of working flow or this kind of very popular research methodology right now? Could you give us some feedback on that? What's the advantage and disadvantage of this kind of artificial intelligence tools?
Perhaps I may start up with some of my opinions on that. I think so far machine learning is still a very emerging tool. I think even though machine learning has a very long history since 1950s, but it starts to have some really practical achievements in recent years. I think there is always developing process of how those tools that is implemented in another field of research. Like for example, like cellular automaton or some multi-agent based algorithms are developed quite early, like in 1987 or something like that, or earlier than that. But with the development, a lot of designers trying to use it in very different ways and with their very specific design intentions. So in very different ways. I think for machine learning is a very typical type of application algorithms. So I think there are what we should focus of applying machine learning to our design is always focusing on how they can integrate it with the existing design process. So that's kind of one method. The other method could be how machine learning, so what is the main character of machine learning itself, and how this character could be implemented with architecture on some typical architecture problems, with also some things that cannot be easily solved by traditional generative or architecture design process. So I think they are some of my points on this.
Okay. Any other feedback?
So maybe I can quickly cut into the conversation because I was Roland's student back in 2010. So I have been like following his work for a while. And what is very interesting because this kind of swarm and the bottom-up theory that are both is like an architecture design theory, but it also coincide with kind of like social structure, social organization theories, this kind of like bottom-up self-organization and etc. But like one issue with, or at least something I perceive with this one is that it always come up with these very complicated systems that are almost like a machine learning that were almost non-interpretable by like humans. So it's like the complexity is beyond our interpretations unless we start to look at the rules at the bottom. And it does require a certain mindset change in how do we perceive complexity and how do we evaluate a system that are not as intuitive as like other method of design.
Yeah, I think that's a very interesting point that, for example, like some of my work using reinforcement learning with some generative design process, typically on some multi-agent system. So I think the initial intention of this research is around like multi-agent system is a bottom-up system. So, but the machine learning is a top-down system. So we have a goal from the designer's mind at the first place. So I think the research, the very interesting part of the research is how to bring the bottom-up generative process with a top-down machine learning control and hybrid the two of them to form a higher level of design capacity. So maybe that's a little bit off the topic, but I think that's a very interesting point.
Okay, yeah, I think which goes to keep on this question, it goes to the design from designer's perspective. The authorship actually is building the, is that still the human-based design process, or this kind of GitHub library actually give us a brand future, which is really influence the creativity of designers. Do you have any argument on that about the plugin tools or the algorithm, how this kind of aspects will influence the designer's creative process? Is there any new authorship we should define in the near future on that?
So, sorry, I'll start first. So I think this is a tricky question because personally, I believe those kind of, or the technology itself is a tool. And as architects, like our skill set sort of restrict us on, let's say, developing like whole new algorithm from the start. But a lot of time we would be like take the arsenal of the algorithm that were developed by computer scientists or mathematicians in other scenarios and fit them into architecture scenario. So I think our strength is on the interpretation of them and how do we find like values in this let's say either algorithm or code that would further our architecture research, that would further our, let's say, fabrication or the industry further. So I do think there is a value in this kind of interpretation and how to link them to like what architecture need, what build space need, and what, let's say, our experience need, instead of, let's say, the just trying to create everything from scratch. Yeah.
Yeah, I agreed. And there's a saying that if we see architecture design as a kind of searching to a solution area, and then Professor John Jarrow once had a saying that he thinks the most creative design are beyond the solution area, and that's because machine learning is always we give the machine some data and then it learn the pattern behind the data, and the output is based on the data, and it's hard to produce something out of the data, and it can only learn some regularity from the data. So maybe the core of design or the core of creativity is still relied on human beings, I suppose.
Any feedback from Professor Liu?
Yeah. When we work together with our partner from computer science, we have argue about what can we call what we did, because he wants us to say you are a CAD, but we don't think so. We think this is designed by computer, but not CAD. But the scientists from computer science, they said, no, computer could not design. That was, all the scientists have this kind of view. And this made me think a lot. I think machine learning, in my interest, I think I'm very interested in the relationship to the architectural education. So we train the model, we teach the students, and you can see the design master like Le Corbusier and some others, they don't have, they didn't get into any school, didn't get a tropical trend of architectural education. So maybe how I think it really depends on the model and the technology of machine learning improving. But I think based on the basic role, it's a role didn't support something new, some new ideas. It supports some reasonable, I think it's something like scientists. So I think we can, as for now, we can only try some design, some common design, some design just like the common architects training by the common school. And I don't expect the machine learning can train a design master and get a very totally new idea. I think that should depend on another kind of model. And you know, many architects were so afraid of that, even afraid of now. They are worried about their place will be taken. And so I don't think whether it's a good thing for such a kind of model can make a critic. As I cannot say that it's okay.
Okay, thank you. I think it's a great moment for the paradigm shift right now because this year in the CDRF conference, 40% of papers have some special relation to artificial intelligence. That is a new trend which is flowing right now globally. I think it's something we need to change our attitude, how to regard the future, how to think about the future. I think it's something about the cyber. Maybe all the human being is a cyber future right now because the tools becomes part of our thinking methodology, which can engage embedded into the creative process of the human body. So including different kind of toolbox, including different kind of algorithm. But the most important thing, I think, in the future is how we can implement, deploy this kind of different kind of tools in the architecture scenarios. That need creativity. That need different kind of logical or experience or practical process, different feedback, and different kind of communication, like this kind of conference. So I'm looking forward for your emerging generation right now. You play a very good roles. From your paper, we can find it's a brand future for you guys. So thanks a lot for this session. Because of we need to follow the schedule, I need to give the session chair to Professor Liu Yibo. Professor Liu Yibo is chair of architecture department in SUT and South China University of Technology. And we have still the session 3, which is also a very intense schedule. So let's welcome Professor Liu Yibo to host the next session. So thank you, all the speakers here. Thank you so much.
Thank you, Professor Yuan. Thank you, Professor Liu.
Thank you, Professor Yuan. Thank you, Professor Liu.
Oops.
Can you see the screen?
See you, but not nothing on the screen.
Oh,
Could you share your screen?
I have tried. Okay, what about now?
Okay. Okay.
Okay. Hello, everyone. Good morning, good evening, good afternoon, the same way. And I'm Professor Liu Yibo from South China University, Guangzhou, China. And our university located in the heart of the Pure Real Data and with a beautiful name, Flower City. And I'm so honored to be the session chair of this section. Let's begin with a small question I often think about. That is, what will happen to the traditional architecture knowledge in the digital time? And will it be useful? Useful is, I think, all will think they will not. But shall the traditional knowledge take a separate part, opted to the digital architecture knowledge? And what's the relationship between them? Enemy or friends? So this is, I always think about that. That is, the question is due to my personal experience. I'm a traditional architect and a teacher, so I have many friends from both fields, and I think they were in this kind of situation. Look at each other like something like an enemy. The traditional architects think the digital architect as a very smart talent, but without any humanistic care. They are all day doing something strange, dazzling, but cannot be mass constructed. And the digital architect, they look at the traditional architect as someone with old fashion and even wood-headed, don't know the future is coming. So they play separated, just like our today. And so I often think about that. Could these two parts of knowledge, digital or non-digital, promote with each other? So my partner, Professor Deng, just introduced our study, and I have shown some new steps just in this year. We try to use machine learning to study about the traditional private garden in South China. Here is Shizilin, just 100 kilometers from Tongji University. And the owner of this garden is the I.M. Pace family. I.M. Pace spent his childhood happy hour here and formed his basic aspect about space, architecture, and the landscape. From the photo, you can see the water, the artificial mountain, plants, and the main space, and the pavilion for spare time. Our study also focuses on the layout according to the shape of the boundary and some influential element on the boundary or in the boundary, just as the entrance, shape of the water, and something else. So the first step, we must find some database. So this is the process of about select, and I think this is the progress need some traditional architecture knowledge, need some understanding of Chinese private garden. Only in this way you can select the suitable case as the database. And the second step, we must make the label. And I think I'm very interested in how to make the label. First, because the really data map, really site map of the traditional garden, there were so many data. I think study about this kind of set map is mission impossible. So my way of small amount case study is just something about how to make the label, how to tell the computer what you should pay attention to, and we should find the basic element in the space and the relationship of them each other. So the first we choose the boundary, the entrance, building, central park, and landscape, and even the routine corridor. But the result is not so good. It can not study very clear. So this makes us go back to our traditional architecture knowledge. What we know about the garden? What is the most important thing? So after thinking and reading, we changed the label to also the shape, the corridor, but the corridor also located just close to the boundary, but not so closely. They have some that kind of small charming space. That is it's very interesting in the traditional Chinese garden. And the water and the artificial mountain. And even the building, we separated into two parts. this thing at first I don't get this idea about the garden. The garden is not for the owner's family, and their bedroom, their even their living room, they are not located in the central park, and don't need the view. The most important is this building something like a guest hall, something like a showroom, and he must be located close to the entrance, but not so close, and has a relationship of the water, main space, mountain, and this is the place the owner and enjoy the time with their friends, with their guests, and then they go on the corridor. So there was some other building along the corridor, big or small, but they are not as important as this one. This is our understanding about that. So we change the color and make the new label, and then after so many tests, we can get some better result. And this is a test we have just a very strange shape, but the computer also can make the results like that: entrance, main guest hall, water, mountain, and corridor, and charming small space, something like that. And I use this case to say that this I said what I said just now, that is very interested in the relationship of the machine learning and the architecture education. And I think in this case, we cannot say that the computer can design such a Chinese traditional garden. I don't think so. I think this is just a kind of training. But during this progress, we know much, get more understanding about what is the most important of the Chinese traditional garden, private garden, and this is something that I think can either expand the area of the machine learning use field, and also can promote the traditional architecture knowledge. And yes, this is all I want to say. And then we come to the our this session. This session we have 7 presenters from Denmark, Japan, mainland China, Germany, Australia, and Taiwan, China. The topic we have including machine learning from fabrication, deep learning for quantitative analysis, building energy performance, adaptive fabrication for bamboo structure, carbon fiber infused 3D printer tectonics, fabrication with robot wire cutter, and digital interactive fabrication. I counted together 5 fabrications with different materials and different tools, and 3 machine learnings in different fields, including 1 machine learning of fabrication. So let's welcome the first paper, machine learning for fabrication of granite membranes. And the speaker should be...
I'm here. Hi, everybody.
Oh.
Can you hear me?
Sorry, I cannot see you. And are you...
My name is Yulia, and I have a camera and a sound.
Ah, Yulia. Okay, okay. Welcome, and please share your screen.
I think first you need to stop your screen sharing. It doesn't allow me.
Okay. Sorry about that.
No worries.
Can you also hear me?
Yes.
Yeah, I can hear it.
I'm Sebastian Getz.
So we will be presenting together. Hello, my name is Yulia, and together with Sebastian, we're presenting our paper, Machine Learning for Fabrication of Graded Knitted Membranes. We are researchers from CETA, Center for IT and Architecture, which is part of Royal Danish Academy of Fine Arts in Copenhagen in Denmark. And we're very excited to take part in the conference in such a new format and share our findings and discoveries with the audience. I begin with the context. So new interfaces between design and fabrication have fundamentally changed the way we design. And now we're shifting from designing artifacts to designing material systems. And the ability to interface digital fabrication at the material scale directly allow us to steer the design of material behavior in respect to performance criteria. In contrast to composites, functionally graded materials are singular multi-materials that vary their consistency gradually over their volume. And due to their optimized material composition, they're better responding to given conditions and particular set of design and environmental constraints. Although the integration of graded material properties into design provides great advantages, but often cause a lot of challenges. So currently, how it's solved is through simulation model validation loop that depends on detailed parametric and simulation models to steer the material composition and require understanding of this performance criteria, which is often not straightforward for some material systems, and demand deep understanding of fabrication processes often obtained only with long-lasting professional training. As well, it's rely on extensive physical testing for validation and calibration of digital tools. So the integration of machine learning to this process into this design systems allows to break the reduction use of this design to fabrication through simulation loop and provide with a more adaptable method with higher degree of design topological versatility. Here, the model is trained to build the links between design and fabrication data directly by detecting and automating simpler parts of the process and of the steering processes. This leads to a more intuitive material specification without the necessity to know all the details of the production. So the following case study we will be presenting will examine the training of fabrication model, its validation through physical prototyping, and application on topologically different situation that would otherwise be not possible with traditional parametric interfaces. So our study takes a point of departure in is a peer research project, which can be described as textile system of arches pulled into shape by the system of cable nets. The installation is very site-specific, and therefore it required a bespoke variation of each membrane through functional grading of the textile. So to increase the structural performance of the arches, because all knitting fabrics are produced two-dimensionally, we varied the knit pattern to enlarge the depths of the tension columns. So here in this project, the design model was developed with the parametric setup to interpret a series of outlines, as you can see on the diagram, star-like for different stitch patterns, specifying the material grading automatically. These were then translated into encoded pixel images and directly used for fabrication. Here you can see the close-up of grading of these membranes, where a star-like boundary applied around the cone areas, allowing for greater extensibility when tensioned. However, from our own experience, we know that functionally graded structures increase the design complexity, and the lack of integrated simulation tools means that the prediction of knitted material outcome, its shape, size, and performance are mainly evaluated and tuned through physical prototyping. So the challenges of inflexible parametric setups and difficulty evaluating the performative effect of the patterns, and as well as the cumbersome process of CNC knit specification relying on deep knowledge of knitting technologies, we wanted not to have this all and find new workflows when designing with graded fabrics. So even though some research have been done investigating a more user-friendly design to manufacture interfaces that would allow users without any knitting experience to design with graded fabrics, the integration of simulation to design models remains difficult. And this challenge lies in knitting intricate loop structure and their interaction at multiple scales. So if quite precise yarn-to-yarn modeling methods exist in textile engineering field, these are only applicable on sample scale due to computational capacity limits, and also the abstraction of knit behavior through digital models is still not fully understood.
Machine learning offers an alternative approach for specifying graded knitted membranes. Here, the specification and simulation of detailed knit surfaces and the challenging encoding of knit parameters in parametric models is replaced by a process of learning the relations between fabricated surfaces and their corresponding design data. Our approach uses image-based machine learning algorithms to generate CNC fabrication data. Image data is practical. The image data is practically interfaced to the process, as CNC knitting instructions are image-based. Project we will present, called KnitVault, builds on an earlier probe called Ombre, in which the machine learning approach was first tested. Ombre investigates the specification of a light filtering textile constructed from two yarn types, a reflective monofilament and an absorbent elastomer. In Ombre, the different yarns and their interaction affect and change translucency of the knitted textile. This means that shifting between the two yarns creates complex nonlinear correlations between light and shadow that are not readily intuited by the designer. To explore the correlation between the shadow and the material specification, Ombre uses image-based sensing in the form of photography under an artificial sun to record the shadow effects of the textiles. This data is then used to determine the textile's light filtering performances and map these to the corresponding fabrication bitmap patterns. A generative adversarial network is used to train the model to build the link between the shadow effect and the corresponding fabrication bitmap pattern. The machine learning technique allows us to construct relations between sets of data when these relations cannot be described in a straightforward manner. The study proved the usefulness of image-based machine learning methods to train design to fabrication models directly.
So as the study Sebastian presented focused mainly on simple performance criteria of light filtering effects, the further question of transferring this method that we developed earlier into other performance criteria provoked the development of the project into KnitVault, the picture you see on the slide. Here, the machine learning method extended to work on the three-dimensional textile configurations, and the aim was to study the functional grading of knitted textiles to control the three-dimensional deformation under the stress. Model was trained on a set of pre-designed flat knitted textiles with varying patterns and fixed topology at the central node. All these textiles were knitted on industrial knitting machine with the same tension settings across the production from a single Dyneema yarn, employing three different knit stitch types to control the depth. This way, pattern geometry is the only changing parameter, and panels were then tensioned to a testing suspended frame and loaded in the center, creating a three-dimensional cone-like shape with the different depths, as you can see in the picture below. So the pattern shapes were drawn manually, following the intention to create diversity in the patterns. After tensioning and loading, the shape is documented with a 3D laser scanner, resulting in detailed point clouds to get the real-world geometrical performance.
The used neural network is able to learn a generalized related behavior of knit on the specific load and their corresponding fabrication files. For the teaching input, we use height maps of the 3D scans of the samples under stress, and for the teaching output, we use the pixel-based knit fabrication files. In order to have sufficient data for the teaching, we employ data augmentation to the initial image pairs. Using this method, we create 8,000 image pairs out of the 7 initial samples. After the training, we test the network's prediction capacity on the 7 samples, which were part of the dataset, and on an 8th new sample. The relatively ambiguous success rate of the training stems from the partially contradicting training pairs like sample B, D, and I, similar stretching depths but different knitting patterns.
And in order to verify these results of the trained model, we produced and loaded the 8th unseen sample with the same machine setting as for the previously shown designs. So the loading of the trained ML sample, which is to the right, which was relatively far from what we predicted, 25 centimeters versus 18. That was performed in a D design, that's to the left. that use was the target. So when looking at the percent of stitch types between D and ML samples, they vary, and we conclude that the relation of stitches and their visual distribution in the surface affect the expandability of the textile under the load. Also, the same conflation of inputs and outputs during the training can be the reason of this depth difference. So then we try to kind of explain what's going on and find samples which are more similar in material composition to our machine learned sample. So for eye, for example, which is visually similar, it's more like an oval-like but mirrored geometry. The depth is not aligned with our ML sample result, and the closest in depth outcome is E, the one to the most right. However, it's still challenging to explain why, as their stitch ratio varies as well as the pattern typology, so they look very different, and the graph shows a different proportion. So this all, again, makes us to conclude that none of the identified parameters, such as the relation between the stitch ratios, pattern configuration, oval cross, free shape, etc., alone are determining the stretch of the material. So, however, the machine learning sample did achieve the predicted cone geometry and with the generated centric topology, even though with the 6 centimeters tolerance, which makes us again to say that looking into machine learning actually makes sense to try to look into it and try to fine tune this method, as the material system is quite unclear in explanation.
The second experiment we conducted is to test the neural network's prediction capacity by giving it a height map outside the training scope, here multi-cone images. The results show that, in fact, the network was able to predict outside of the training scope, which implies that neural networks can be more flexible opposed to relatively rigid parametric models. While the results of the first test of predicting the fabrication file from a desired stretching depth remains ambiguous, the success of the method's adaptability across different topologies is promising for future digital workflows. Generally, the project shows the possibility of bypassing domain-specific limitations of parametric models. Nevertheless, the used dataset for the training was small and ambiguous, and therefore the training results of the neural network are equally indistinct. The small dataset was heavily augmented in order to provide enough data for the training. This approach is not a good practice for machine learning, but is symptomatic for the real-world problems of machine learning in architectural applications, where big datasets are not always available. The question is, how much data will be needed to train neural networks in architectural contexts to help to inform design decisions? The second test of the adaptability of the method to different topologies showed the possibility of transferring from one problem domain to another. Further probes have to be made to determine how far away from the training data a neural network can be used to predict the outcome. The general approach of skipping the simulation model validation loop by training neural networks directly on the fabrication data can have useful implications for other design to production workflows where a nonlinear relation between design intent and fabrication data exists. For example, CNC milling usually includes cumbersome procedures of manual labor when 3D models are translated to G-code. Nonetheless, there is a relationship between model and G-code which potentially can be learned by a neural network. Sharing fabrication data and design models of different fabrication machines, robots, CNC machines, 3D printers, for example, can potentially help to overcome the limitations of small data sets and too much data augmentation. Finally, the presented image-based approach can be extended to either parallel image-based approaches, for example, optimizing for different problems simultaneously, or voxel-based, or voxel-based training, or maybe even time-based voxel neural networks. Thank you.
We're done.
Okay. Thank you, Julian, and thank you, Scott. Thank you for the splendid presentation. Julian Scott is come from the Royal Danish Academy of Fine Arts, Denmark. And Professor Thomason, he said that the CITA is Center of Information Technology and Architecture in 2005. They're interested. I think the presentation showed their keep interested to combine the craft into the technology. And sorry, due to time, I cannot say something more because we still have one speaker for the last session. There's something wrong with his iPad, so we must welcome the next speaker, Yi Guyi from Tongji University. Yi Guyi, please.
Yes. So is it working now?
Yeah.
Can you see my screen?
Yeah.
Okay. Oh, cool. Okay, finally. Sorry for the inconvenience and thank you for your understanding. My name is Guyi Yi, and now I'm very excited to share our paper entitled Cyborgian Approach of Eco-Interaction Design based on Machine Intelligence and Embodied Experience. The proliferation of digital technology has swelled the amount of time people spend in cyberspace and weakened our sensibility of the physical world. Imagining a future where humans totally give up mobile phones and embrace nature is neither realistic nor reasonable. What we should aim to explore is the opportunities and capabilities of digital technology in terms of fighting against its own negative effects, cyber addiction, and working as a catalyst that re-embeds human into outdoor world. This is a review paper that introduces how cyborgian approach behaves and its objectives to achieve. One is to improve the quality of environment by enhancing our understanding of non-human creatures. The other is to encourage a proper level of human participation without disturbing ecobalance. The term cyborgian or cyborg is a combination of cybernetics and organism, a hybrid of part clock and part swarm. It advocates cross-species communication, control, and symbiosis. In a broad sense, everyone holding a smartphone is a cyborg, because the external apparatus has become the cyber extension of our organic cooperative. Embodied cognition is a psychological theory that emphasizes the indispensability of human body in the process of cognition. In other words, the body is our general medium for having a world. This could be a theoretical foundation for designers, as a designer and a cognitive scientist seem like a pair. Both are trying to decode how humans interact with the world. On the basis of these two theories, here comes the question. Since the cooperative is the main source of knowing the world, when our body is augmented by machine intelligence, how would human cognitive abilities and experiences be improved? And how would this be beneficial for the construction of an interactive environment? To encourage human-nature interaction, one way is to make plants more sensible, intelligent, and interactive. Cyborgian approach would be instrumental, as it influences the way plants sense, think, and actuate. Rather than augmenting the way plants sense, it augments the way how we understand and benefit from their gifted sensing abilities for interactive purpose. On the basis of big data flowing in cyber network, cyber approach augments plants' intelligence, including communication, learning, and memory, thus improving capability of cross-species interaction. Cyborgian approach guides the growth and movement of plants by controlling input stimulus, and even guides the process of evolution to a certain extent towards the objective of the most appropriate level of interactivity. To encourage human-nature interaction, The other way is to improve bodily interaction experience. Cyber system plays valuable roles under the frame of experience hierarchy and assessment metrics. At the most basic and rational level, cyber system enables human and nature to communicate in a common language, the binary machine language. Digital technologies allowed us to Hello? Sorry.
Yeah.
Digital technologies allowed us to explore the reality beyond human limits, to see the familiar world from an alien perspective, to achieve a better sense of sensational attraction. Besides this, the ultimate goal of eco-interaction is to build up an emotional bonding with nature, which could last longer and deeper than just rational or sensational memories. Cyber approach would be advantageous in human-nature bonding process. Its application and efficacy are investigated from 4 aspects as follows. Maneuverability, including fluency and freedom. Fluency means operating smoothly with a clear logic. Freedom refers to the range and types of interactions users can play with. The development of human-machine interface is a process with increasing fluency, yet the freedom of gesture control of current somatosensory devices requires further training. Immersibility is related to sensational experience and mental status. Accordingly, immersive quality can be improved by enhancing multisensory experiences, as well as balancing the relationship between challenge and skill based on concentration analysis and personal feedbacks. As for joviality, machines nowadays are capable of sensing and recognizing emotions, which are no longer just the output of byproduct of interactions. Emotions participate in feedback loops and become input parameters that affect final outputs. This means an interactive system can adjust its levels according to users' emotional conditions in order to ensure constantly positive feelings. Attractivity derives from beauty and creativity, which can be enhanced by cyborg approach. For instance, in the project Bioresponsive Garden, microelectronics realize the unusual combination of plants and dance, where creativity emerged. And in many projects by TeamLab, the attractiveness emerges from the non-repeatable organic aesthetics empowered by machine intelligence. In short, cyber approach allows us to better understand the physical world, to improve bodily experience, and to add more joy and attractiveness to the interaction with nature by making use of its sensing and computational capabilities. As a matter of fact, most eco-interaction projects nowadays are installed indoors. What are the constraints of outdoor eco-interactions, and what are the opportunities provided by cyber technologies? One of the biggest technical obstacles of outdoor interactions is the complex environment compared with indoor ones. Personal wearable devices increase the feasibility of multisensory enhancements in outdoor scenarios, which would indulge humans more in a destructive environment. Another challenge of outdoor eco-interaction is to minimize the impact on voiceless ecological entities. Cyber approach would be helpful because the living conditions of plants can be always monitored and guaranteed by their cyber apparatus, and our cyber extensions work as a medium for harmless virtual interactions that bring about genuine feelings. Additionally, distributed wearable devices enable mass customized multi-user interactions, which encourage not only physical but also social activities in natural environments. In summary, a cyborg approach supplemented by multisensory enhancement technology would work as a powerful toolkit to the challenges of outdoor interactions with enhanced immersibility, customized experience, and minimal impact on the ecology. Finally, based on the researches above, a cyborg eco-interaction design model is proposed. What distinguishes this model from the others is that it concerns more about the user experiences at all levels for all ecological entities. Environmental data and plants' living conditions that are monitored by ubiquitous sensors have a decisive impact on the system. The behaviors as well as mental experiences of human users are recognized by wearable devices and stationary sensors. These data are evaluated from the 4 aspects mentioned before. The results may trigger self-tuning mechanisms of this intelligent system, which would redefine its back-end algorithms, customize its interaction levels in order to better serve the users. When bottom-up self-adaptation is not efficient enough to enhance user experiences, then human designers are required to get involved in order to modify the interaction design in a top-down way. This is what Kevin Kelly called control of control. The cyborg eco-interaction design model this paper proposed may be far from satisfactory, but it is expected to broach the subject for further concerns and investigations. Opportunities always come along with threats. Advancing technology is facilitating our life while challenging our relationship with nature. Insightful designers should be keenly aware of the pros and cons of technology, trying to come up with a new paradigm to rehabilitate this relationship, which would then be more than a design paradigm, but even become a new lifestyle in the upcoming digital future. Thank you for listening, and thank you for offering such an excellent chance for me to give a presentation here on my birthday. Thank you.
Okay. Happy birthday.
Thank you.
Thanks for Jiayi, and it's a very, I think it's a very attractive presentation. He says no more techniques, but he spent much time about to study about what the human need and the relationship with nature and something else that is very attractive to me. And sorry for due to time, we keep all the questions to the panel discussion, and then we have to come to the next speaker. Is that Zhang Jiaxin. The next paper title is a large-scale measurement and quantitative analysis measurement of facade color in urban streets using deep learning. It come from the Osaka University, Japan. Is that Zhang Jiaxin speaker?
Sorry, can you hear my voice? Sorry, can you hear my voice?
Yes.
And can you see my screen? Can you see my screen? Oh, okay. Thank you. Thank you so much. And sorry. Thank you so much, dear professors, audience, and the CDFR conference committee. And good afternoon, morning, and evening, everyone. And my name is Zhang Jiaxin from Osaka University, Yabuchi Lab. And it's a great honor for me to introduce my paper, a large-scale measurement and quantitative analysis method of facade color in the urban street using deep learning. And color is people's first version impression of the city, which can influence spatial perception in the human-made environments through different color compositions. And the city managers issue lots of plans and regulations for urban color planning, like Figure 1 shows. And most of those plans regard building color controlling as the most critical implementation program, because buildings are larger and more complicated than the products created by human beings. And currently, urban planners have built a workflow of facade color investigation, first collecting building pictures and geography coordinates by using digital cameras and GPS devices, and then referring to the Monsieur color system to get color information. And finally, the result can show the facade color distribution and dominant color in the city or spatial area. And however, this workflow is limited to the manual collection at a small quality. And thanks to the street view image and deep learning technology, we can get a large number of street view from online map services like Google Map and Baidu Map and Tencent Map. Meanwhile, we can automatically classify the street facade using semantic segmentation method. And the literature review includes 3 steps. And the first part is about urban color planning with a definition of color system. The planning of urban color requires a quantitative definition of color system, and then the work can carry out on repeatable. And there are lots of practice, and I won't go into the details. And those methods can provide status data for sustainable development of cities and give design suggestion to urban planners. And however, the city information model gradually become the future urban development direction. And the fine management of urban color information is a significant aspect of a digital city. And then it's about facade color measurements. And the traditional facade color measurement are mainly based on manual collection. And those methods have played a role in promoting urban color planning in the past. And however, due to the consumption of time and labor in field investigation, and many researchers conduct a small-scale experiment. And with the development of the semantic segmentation algorithms and urban data sets, replaced it by the cityscapes, and it's no longer difficult to use deep science to achieve different future dictations of so many elements of the building facade. And the third part is quantitative analysis of version quality in urban space. The combination of street view data and machine learning in street version measurements can solve the problem in large scale with high refinement, and is used in many aspects, such as identification of the neighborhood safety through street view pictures, and the extraction of green street visibility, and the application of measuring visual quality in street space, and so on. And 2 considerations, including in my research, are the classical theory of urban visual design and existing deep learning algorithms. So specifically, the first one is the frequency with elements mentioned in related urban virtual series, and whether those factors are easily translated into practice. And the second consideration is whether existing related algorithms can measure those factors. And to our experiment methods, and our research is conducted within the main districts of Nanjing City, which is about 156 square kilometers. And the workflow can be briefly summarized as 3 steps. The first step is street view image collection, and the second is facade segmentation and data clean, and the third is color calculation and analysis. And the street pictures in this study were extracted from the Baidu Street View platform, and the urban road network information is selected from the OpenStreetMap, and we can get the sampling point in QGIS, and then downloaded 2 pictures, both left and right side of the street for each sampling point. And then the next step is building facade segmentation and data clean. We use the PSP net to segment the building facade from street view images. And the examples are shown in Figure 6. And then the proportion of a building facade can be measured, as Formula 1 shows. However, there is a low proportion of building in some street view images, like Figure 6C shows. And in order to improve accuracy of the experiment, we set a regulation if the building proportion is below 20%, accounting for the total pictures, and we need to clean up those photos. And then it's about facade color calculation, and using the architecturally standard color card with 258 colors, like Figure 7 shows, and as a reference, and we merge the raw color data to standard color, and the merge method is to calculate the HSV value of the street view color and replace them with the closed standard color by calculating the Euclidean distance, and as Figure 8 and Formula 2 show. And then we count the proportion of the facade colors. And to the result, finally, we get around 59,000 sampling points with geography coordinate. However, about 55,000 sampling points in Baidu Map API with corresponding street view images. However, around 4,000 sampling points without data. So after cleaning up the low proportion building perception, we finally got around 77,000 valid data in 110,000 total images. Table 1 shows the dominant color statistics of street view pictures at each sampling point, and information is including the hue, saturation, and value, and the geography coordinates of the facade, the latitude and longitudes. And by calculating and getting the quantitative color information of building facade at the city scale, we can not only do a large scale analysis, but also can make a granular analysis for specific area. So let's say the figure 9a shows the distribution of the dominant color of the street network in central city of Nanjing. And the red line indicates valid data, and the black line indicated that there is no image or the building proportion is very low. And we can find that the dominant colors are mainly gray, with dark gray accounting for 33.5% of the total, and the greenish gray accounting for 22.3%, and moderate khaki accounting for about 20% of the total. And the most proportion of historical style area, the dominant color is low saturation, like the figure 9b shows. And in the specific historical conservation area, like the Confused Temple and the East Zhonghua Gate and the Spiral Campus, and the dominant color is light, and like the figure 9 shows. And also, it can be verified with the city plans, like the land use plan and the historical city preservation plans. And also, we can compare to our daily experience. And in addition, we can also get relationship analysis of building information like age and price from the real estate companies database like Yahoo Real Estate and Lianjia and Fangtiansha and so on. And then to our conclusion and discussion, this study proposed a framework for measurement and analysis of facade color in the urban street, including using open platforms to collect data and quantitatively analysis. Compared with the previous studies, this method used open source data to realize the refined measurement, which can got the street colors information at different scales. And in addition, we can check the consistency of urban colors, and it also helps to coordinate with other elements to achieve integrated design. And in conclusion, this study is fundamental research for the decision-making and the database construction of urban color planning, and which plays an important role in perception measurement and data-driven design in urban space. And in my future work, and in the technical level, the color calibration of street view images can improve the accuracy of the calculation results. And to the potential application, and it can be combined with the machine learning to identify the degree of functional mixing of streetscape and to calculate the color composition with different functional blocks. And last but most importantly, how to use it to design a better version environment is a different problem in future work. And yes, there's reference. And finally, I would like to thanks to my supervisor, Mr. Fukuda Tomohiro, and Professor Yabuki Nobuyoshi, and my friend, Dr. Wang Bowen. And that's all. Thanks for your listening.
Okay, thank you, Zhang Jiayi. Sorry, did I make a mistake? You are not from Osaka University. Now you are in.
Yes, I'm from Osaka University.
Oh, sorry.
You don't.
That's not no fault. And thankful Jiaxin for such a very attractive presentation about the data-driven measure of the city color planning, and I'm very interested in how can we use this measure in the future. And but still no time for question, and now we come to the next paper, optimization and prediction of design variables driven by building energy performance, a case study of office building in Wuhan. And is that Li Jingyi? Okay. And I think also I say the Professor Chen Hong. Is that?
Oh yeah, Chen Hong.
Is that?
Now he is in. Yeah, now he is in Japan now.
He's not here. Okay, and Li Jingyi is from the Huazhong University of Science and Technology. Okay, please share the screen.
Okay, but now I'm not the 联席主持人. I cannot share the
really
the screen. Yeah.
Maybe
now. Oh yeah, now I think I can share the screen now. Okay. Okay, sorry. Hello everyone. No, sorry. Okay. Okay. Can you see my screen?
Yes.
Yeah?
Okay.
Okay. Hello everyone. My name is Li Jingyi, and I'm come from Huazhong University of Science and Technology. Now I will give you my the presentation about my presentation about how to use the RBFANN's model and MEGA optimization to optimize the building based on the consideration about the building energy consumption. And now I think in my research, I used the two different algorithms together. One is the multi-island genetic algorithm MEGA, and another is RBF, artificial neural network, RBFANNs together. And because the RBFANNs model have some error between the prediction value and the simulation value. So I use the RMSE to test which one is the best, because I did 4 different RBFANNs model, and I compare to the reference case, the RBFANN's elite case save at least 37% of energy, and I Hello.
Okay, I can hear you.
Okay. Can you see my screen?
No, please share.
No.
Share the screen again. And,
Okay. Because I think right now.
Yeah, we can wait a little moment. It begin to share.
Okay. I don't know why. Because this is the Zoom said it is connecting. Okay. Can I continue?
Still not seen. I don't know why. Okay, I think it comes.
Okay. So compared to the reference case, the MEGA elite case will save at least 44% of energy, and RBFANN's elite case will save at least 37% of energy. And I don't want to just focus on the best solution of the design variables, but I want to consider about the good one, not the best one. So I use the K-means Chester Center to local the design variables in the 2 different optimization process. Then I summarize the benchmark of 14 design variables and give. And I think I can suggest one guidance for the Wuhan office building design. Okay, now I think everyone knows Wuhan. Wuhan is one big Chinese city which have 10 million people, and we all know Wuhan is a typical hot summer and cold winter city. So it means the cooling system and the heating system of the office building is very high, and also the office building will use 10 or 20 times energy than the residential building. So I think Wuhan office building energy saving is very important. And so this is why I choose Wuhan as my research case. And my research objective is to reduce the total energy consumption of building. And lighting of the Chinese standard of energy efficiency for public. this is my screen, and building is just now, and I want to
there is something wrong with the voice.
I want to the problem I research for level surrounding building. But I in my next step I will input the surrounding building. The total is 1,000 square meter and 5 floors. Okay, I have variables in my to be considered about the curious studies of the horizontal and list of the 14 variables. And I use the to simulate so I need to find the material list of this
Sorry, Jingyi, there is something wrong with your voice. I think we cannot hear very clearly. Could you, how can we keep the voice?
Otherwise,
I think maybe there's due to the internet, it's not your. Okay, please try again.
To reconnect the internet and okay, sorry. Okay. Hello.
Okay, I can hear you. It's very clear.
Hello. Hello. Hello, everyone.
Still not very good advice. Maybe this due to your device. The Jingyi, can you hear me? Jingyi, can you hear me?
刘老师，金一他说能不能放到最后去
？Okay, I get his message. I will put his paper at the list of the session, and now we come to next paper. Working with uncertainties, adaptive fabrication workflow of bamboo structure. The paper is come from University of Stuttgart, Germany, and the presenter will be Zhang 张如晴,钟如晴.
And 钟如晴, yeah.
Okay.
Hello.
And your partner's name is
七月.
Yeah. 七月, okay.
Yeah,
welcome.
Okay.
Just begin, please. You can share your screen.
Yeah, can you see the screen now?
Yeah, you can see.
Okay. So let's begin. So hello everyone, thanks for the invitation. I'm Ru Qing and together with Yue. And it's our great honor to be here and present our research project working with uncertainties in adaptive fabrication workflow for bamboo structures. So aim of this project is to investigate an adaptive fabrication workflow for natural bamboo structures, which can compensate for cumulative deviations between built and designed form in real time with vision-based sensing. With such workflow, we aim to effectively increase the efficiency, accuracy, and the reliability of bamboo constructions. We would like to first introduce these three aspects of the research context: natural material in construction, the challenges of its deviation in fabrication, as well as the adaptive fabrication workflow. So global average temperature has increased by more than 1 degree Celsius since pre-industrial times. Recent research shows that bio-based material can be a solution. Bamboo is one of the good candidates. It grows fast and has remarkable mechanical properties. Though there is engineered bamboo product available now, real bamboo still has some advantages. It maintains evolutionary optimized geometry and fiber layout. Meanwhile, it doesn't require extra energy and chemicals to produce. However, its geometrical dimension and mechanical property is far less stable than its engineered counterpart. As a result, its application is still highly dependent on craftsmen's experience. Efficiency, accuracy, and reliability cannot be ensured. Natural geometry of bamboo brings material-related uncertainties. Manual operation results in fabrication-related uncertainties as well. Both lead to deviation of the fabricated structure from the design state. Therefore, the application of bamboo is usually limited in non-accuracy dependent scenarios such as small-scale residential projects, pavilions, as well as low-cost scaffoldings. Apart from that, inaccuracy results in difficulties of interfacing with accuracy-dependent building layers, which consist of prefabricated components. The unpredictable deviations make it difficult for natural bamboo structures to achieve target points with required accuracy. So, working with those uncertainties, our fabrication system needs to sense and adapt. We would like to introduce two state-of-the-art projects in terms of sensing and adaptation. In the project of Sombra Verde's 3D printed bamboo structure, the bamboo cross-section is scanned and the data are used for generating the geometry of the 3D printed bamboo node. The project mesh mode from ETH showcases the potential of applying adaptive strategies based on sensory feedbacks to achieve global accuracy of the structure. Facing the challenges of bamboo constructions, we propose a method which is an integration of sensing, adaptation, and actuation processes. It is composed of multiple iterations of adding bamboo elements onto the existing structure. Each iteration begins by retrieving digital information about the connection areas. The respective connection areas within the built structure and the new bamboo elements are scanned with an RGBD camera. So after comparing the sensory result with the computational model, the pose of next element is optimized for compensating the existing error. According to that, the geometries of related connectors are generated and fabricated. Finally, the bamboo element is assembled onto the existing structure, and the loop starts again. Then Yue will introduce the technical development part.
So for the sensing, we started with a relatively low-cost RGBD camera as our sensor. The sensor is mounted on a tripod for scanning both the material and the in-progress structure. A circle grid board is used as a reference object to align the scan point cloud with the digital model. The sensor can capture RGB images as well as depth images, which we use for estimating the cylinder parameters representing the bamboo. They are given by a radius, a point on its axis and a vector along the axis direction. The bamboo part of the points are segmented by checking the distance from the point to the design cylinder axis. And then the data are used for the least square cylinder fitting process to determine the cylinder parameters. Here are some of the results of the scan point cloud of both the material and the in-progress structure aligned with the digital model. Since the connection system we use for the first two experiments requires drilling on the bamboo pole, we also developed the method for detecting the positions of drilled holes. And the adaptation process is formulated as an optimization problem. The goal is to move the next bamboo pole to such a location where it is able to connect with the existing deviated structure indicated as P1 on this diagram, while keeping future connection areas as originally designed, indicated as P2 here. In our experiments, the transformation is optimized with the evolutionary solver Galapagos. After the optimal pose of next element is figured out, it needs to be connected onto the existing structure. According to the research of Hong et al., bamboos are usually connected by Mortise tendon joint as well as lashing joint in traditional applications. In modern bamboo buildings, bolting and steel member joints are more frequently used. Many other possibilities, such as 3D printed joint, are under investigation in research projects. In our experiments with 3D printed customized connection pieces for different nodes, the node can be also fabricated with subtractive method like 5-axis milling to increase their performance and minimize the fabrication time. The connection piece can work with a wide range of angles between two bamboo poles, and with the drilled holes on the bamboo, human worker has full information for the assembly. In our case, the drilling is done with a very simple low-cost machine. The bamboo pole can be turned into the desired orientation, while a guiding block can move along the bamboo axis to the design position, with which we can manually drill on the design positions of the bamboo pole. So to test such method, we carry out two experiments, one for testing the effectiveness of sensing and adaptation method by making a very simple zigzag structure. The other is intended to achieve a three-dimensional tree-like structure while testing the potential of interfacing it with prefabricated building components. In the first experiment, in order to validate the effectiveness of the above-mentioned methods, we choose to build a simple zigzag structure with two groups of material. And each group is used to build the same structure 3 times with 3 different methods. Method A is exactly the proposed workflow. As comparison, in method B and C, in-progress survey and adaptation process is not performed. The material is measured only once before all connectors are fabricated. Method B employs vision-based techniques, while in method C, the bamboos are assumed to be straight and their diameters are measured with a caliper. And here are the results of 6 built zigzag structures. And they are scanned and compared with the design structure. The result of method B and C shows significantly larger deviation of the 4th and 5th elements. And we plot the deviation of the midpoint of the axis. In comparison to an overall accumulating trend of error with method B and C, the errors of method A fluctuate at a relatively low level as the building process continues, which matches the expectation. As the first experiment shows encouraging result, we apply the method for a more complex 3-dimensional structure while testing its accuracy by interfacing it with prefabricated polycarbonate plate. And here is the built result. The final deviation of the bamboo is controlled within 10 millimeters, and through adjusting the geometry of this final connector, the interfacing is successful. And here's the scan point cloud aligned with the design model, and the deviation is again visualized in the left diagram.
Yeah, so I will make the conclusion. To conclude, We have presented a feedback-driven workflow for efficiently surveying and correcting deviations during the construction of natural bamboo structures. This is an important step towards reliable and predictable digital fabrication methods for large-scale bamboo architecture. The current study is limited by the accuracy of the sensor result, manual drilling, and the node valence. Future developments would focus on more precise sensor and algorithms and more performative connection strategy. As an outlook, we believe our study is a starting point towards bamboo usage in even accuracy critical applications. For instance, it may enable bamboo structures to interface with some prefabricated components made of wood, metal, or glass, so that they can be used for building substructures for the roof or facade. It may also enable building bamboo structures in complex shapes like space frames efficiently and reliably. The presented work was conducted within the iTech Master at the University of Stuttgart. We would like to thank all the researchers at the Institute for Computational Design and Construction, Institute for Building Structures and Structural Design, and Institute for Controlling and Engineering of Machine Tools and Manufacturing Units. This work was partially supported by the state of Baden-Württemberg, the European Regional Development Fund, and by the German Research Foundation under German's Excellence Strategy. Here are our references. And thank you for your attention.
Okay, thank you, Qiyu and Zhongru Qing. Thanks for your very impressive presentation. Although I have many questions about what your point, response to the shape changing, but we decided to keep it to the panel discussion. And because of time, we still have Maeso and Patrick for tonight, so we must hurry up for next paper.
Sure.
Okay, the next paper, super composite, carbon fiber infused 3D print tectonics, and the come from RMIT University, Australia. The speaker will be.
Hello.
Okay. Hi, Sam.
I'm here. Hi, how are you? But I think my recording is gonna play, so I won't present online. Yeah, I can hear you. Can you hear me?
Okay, you can begin and share the screen.
The recording I send the recording, so it's gonna be recorded. Yeah, there we go.
Audio. Okay, good.
Yeah, thank you. Hi everyone, thank you for joining me in this presentation today. My name is Hassan Mohammed, and today I'm going to present supercomposite carbon fiber infused 3D printed tectonics by Nick Ball, Roland Snooks, and myself from RMIT Architecture School in Melbourne. The focus of this paper is the application and development of a series of technical innovations that enable the design and realization of complex, intricate architectural forms through a carbon fiber reinforced 3D printed polymer fabrication approach. This infused fiber reinforced plastic, or IFRP, method offers a viable approach to constructing supercomposites that have complex geometries and compressed tectonics. The application of FDM printing to larger scale architectural fabrication requires numerous innovations in terms of hardware, printing techniques, software development, architectural detailing, structural design, and the design of tectonics. This paper outlines some of these developments, including printing topologically complex forms, subdivision of forms into printable parts, non-parallel printing techniques, the infusion of carbon fiber within printed conduits, structural analysis, and jointing systems. The broader context of this research includes and contributes to a wide community of practice, which includes various research streams with different conceptual agendas in context of digital architecture and fabrication. History of polymer composites in architecture dates back to at least 1956, Monsanto House of the Future. Recently, there has been a re-emergence of polymer composites in architectural discourse. This is evident in the work of architects such as Greg Ling. Big area additive manufacturing, or BAM, refers to the fabrication of larger scale components through fused deposition modeling, or FDM techniques. Robotic fiber deposition techniques have been developed notably by the ICD in Stuttgart and also the Digital Building Technology Lab at ETH University in Zurich, which avoid the need for conventional molds. These techniques include fiber winding and direct deposition on the 3D printed surfaces. An alternative approach to avoid molds was developed by Studio Ron Snooks through a sacrificial formwork approach, where concrete structure is cast within 3D printed surfaces. This approach became a precursor to developing a carbon fiber infused 3D printed tectonic strategy to create a negotiated relationship between the inner and outer skin, where form and structure negotiate with one another to enable topologically complex forms. This research is presented in two projects. First project on the right, Cloud Effects, which is completed and exhibited at the 2019 Architectural and Urbanism Biennale in Shenzhen. And second project on the left, Unclear Cloud, is currently under development and scheduled to be exhibited at the National Gallery of Victoria in 2021. Now I'm going to talk a bit about some of the technical innovations achieved in fabrication of cloud effects and refined in the fabrication of our next project, Unclear Cloud. A multi-layer 3D printed mold is used to accommodate both the structure and services within embedded conduits. Structural skeleton at their core, surrounded by a secondary layer to allow for building services and compressive foam insulation. Also, customized tools and jigs are used to place the steel connections in the right alignment for each other. Then epoxy resin bonds the carbon fiber, a steel connection, and polymer sacrificial mold. This lattice-like network is embedded in a translucent outer skin. These two skins laminate to one another periodically to create sufficient structural integrity in the skin at a macro scale. Embedding a structural network into the skin is a technique to achieve a negotiated relationship between the inner and outer skins. This enables an inherent geometrical intricacy in the design process, which is contrast to traditional systems and is needless of post-rationalized structure. This is what we call supercomposite, an approach to transform application of polymer composite material systems to a new architectural tectonic by compressing surface, structure, services, and ornament into a single, irreducible assemblage. Compared to filament printing, there is no material retraction in this process, and the tool path stops. This results in the dragging of excess material between the end point of a tool path and the subsequent start point, creating polymer strings within the printed part. This string causes accumulated defects between layers, affect the surface quality, and result in possible print failure in large prints. Series of minor technical innovations, such as flange connectors, were introduced to reduce the start-stops in printing process, which has major design implications and enables fabrication of non-continuous surfaces. Flange connections also enable positioning vertical seam lines toward the back of the geometry where they can be hidden and less visible. Conventional FDM printing, where each layer is deposited horizontally and perpendicular to the vertical axis of the tool, poses significant limitations to geometrical directionality and freedom. Non-parallel printing leverages the 6-axis of the robot to deposit non-horizontal layers in order to gradually change the layer heights and print plane orientation within the printing process. This enables the fabrication of geometries with more complex surfaces. We use FEA modeling to examine the structure and foresee extreme deflection points and bending moments. Despite advantages, this method considers the carbon fiber as the only structural element. This led to overestimating the required structural strength of the carbon fiber composite, adding to the overall weight. This process has been refined, where we have developed a hybrid analysis that includes both the carbon fiber network and the polymer skin. Initial structural analysis to undertake this network as a discrete segment with same fiber value all over the network, resulting in overlapping fibers in which segments cannot be optimized. We develop a new approach to map the fiber distribution throughout the structure. This fiber mapping optimization strategy navigates the fiber through the network relative to the specific bending moments of each segment. For logistic reasons, this project requires prefabricating parts which are assembled later. Connecting these individual parts creates a substantial challenge and need for robust joints that create a continuity of a structure equal to the strength of the carbon fiber elements. Cloud effect uses a concealed steel fixing plates that create structural continuity across plane joints. There are some technical challenges in this process, such as misaligned connections and interference with outer skin that led development of new subtractive joining system. This new method uses a CNC milling process to create positive and negative polymer inlets. This research has outlined an approach to integrating carbon fiber structure within 3D printed polymer skins. To advance this research, we have developed innovative techniques and approaches in large-scale 3D printing, detailing necessary to infuse carbon fiber and advances in digital tools to fabricate the necessary geometric complexity. The future direction of this work is intended to extend the research beyond proto-architectural demonstrator projects and explore the feasibility of this research and approaches within the design and construction of large-scale architectural projects. This is my presentation for this paper. Thank you for listening to this presentation, and now I'm happy to answer some of your questions after the recording finishes. Thank you.
Okay. Thank you, Mohammed. And Mohammed is a PhD student, and I think he's a famous STAR student, and he has a very cool homepage. And I suggest to some other audience, you can visit his homepage. And sorry, Mohammed, we still have must keep the time to the next speaker, so we will keep all the questions in the panel discussion.
Thank you for having me.
Okay, and now we come to the next paper, freeform volume fabrication using accurate robotic hardware cutter. This paper is the presenter is Paul. Okay? I would like to give some introduction of you. Paul and David was the founding partner of the LLDS with the architecture registration in the UK and Victoria, Australia. Paul studied architecture at the University of Melbourne and the University of East London at the architecture at the AAUK. He has over 15 years of architectural experience in Australia, Malaysia, and the UK, and that's all I know about you. And okay, Paul.
Thank you, Professor Liu. Thank you for your introductions. Good afternoon. My name is Paul Lowe. I'm from the Melbourne School of Design from the University of Melbourne in Australia. So we're very glad to be able to present our paper with you. I'm going to share my screens now. I hope you can see that. Can you see our screen at the moment?
Yes.
Yeah. All right. Should be full screen by now. So we're glad to present our paper titled Freeform Volumetric Fabrication Using Actuated Robotic Hot Wire Cutters. The paper is co-authored with Yihan Hao, Thomas Sears, Jiaqi Mo, and David Leggett of Architecture Research Lab here in Melbourne. Yihan will be joining me later with the presentation and will speak about the robotic workflow for this project. So most of us are fairly familiar with hot wire cutting techniques and efficiency to cut large volumetric geometry, primarily using expanded polyester or EPS. This geometry are either used as a mold for casting concrete or as an end product in itself. And in recent years, researchers has been exploring using collaborative robots to shape non-rule surface geometry which is typically produced from using a single frame hot wire cutting on the left-hand side. And as you can see, both techniques are increasingly used in the industry for fabricating architectural components and molds. The two images also illustrated the current techniques in hot wire cutting. So we have on the left using a flexible nitron wires, and on the right the more rigid cutting rod or sometimes a knife system. So in our research, we actually use both techniques. So the challenge for our research is to design and test a new hot wire cutting end effector that can be mounted onto a robot arm that will be able to produce non-rule surface geometry without the use of a collaborative robot. So in other words, using a single robotic arm, in this instance, in conjunction with what we call an interpolated polynomial curve hot wire cutter, or IPC hot wire cutter. So the research is born out of a design studios that David and I has been running for the last 8 years here at Melbourne School of Design. The last few years, we have been exploring a very simple ideas. We've been asking students to make machines that can make architecture. A very simple brief, which obviously have the ideas to look for high impactful research. So today we will actually look at only one of the projects, which is obviously the IPC hot wire cutter. So the pedagogical models behind the studio is to utilize the flattening knowledge structure in electronics to explore critical making that allow designers to make sense of the affordance in electronic prototyping platforms and the material system to generate novel design. What we're interested is in the affordance of design that such machine can produce or provide for the designer. So instead of the traditional generative methods of ideas to algorithmic design, we're interested in how geometry, algorithms, and material system through prototyping can generate design intentions. So for this project, we started off examining a very simple set of geometric rule set and essentially the idea of a variable surface transformations using a series of polynomial curves to form a network surface. And it's something that we do all the time as a designer, to draw continuous surface, but we want to go back to some of the basic ideas. So the studies allow the design teams to translate the curve into physical systems. And here you can see a series of, here you can see a series of prototypes that explore both rigid and flexible hot wires, as well as blade system. 5 prototypes are being developed by the team before we reach a workable solutions. The hot wire cutting knife is one of the main challenges of this design, and more detail can be read in our full paper when it's been published. So I encourage you to do that. This diagrams shows the various components of the IPC hot wire cutters. Now it operates using 4 steppers motors, and diagrams here you can see the mechanical movement of the system that's being illustrated. Now, through articulating the nichrome wires with 3 movable intersecting points, or nodes, we can begin to produce a non-rule surface geometry as the hot wire cutters went through the volumetric geometries, or EPS, as we would later test it. And so here's Ihan mounting the IPC wire cutters on the Kuka robot here at ARL, and Ihan, you will now expand on the fabrication and data workflow.
Yes. So this diagram shows the parametric system and the mechanism of the design. There are 3 main systems here. First is using Firefly plugin for Grasshopper 3D to translate network surfaces into G-codes for 5 steppers that are associated with IPC hot wire cutter. The global panel controls Arduino Mega 3 with ramps 1.4, allowing 5 step motors move spontaneously. Second, using Kuka PLC, the movement of robotic arm with variable velocity can be precisely scripted and simulated before cutting the EPS. Thirdly, the wires of 3 cutting knives and primary nichrome wire will be powered individually with 12-volt power supply. In this diagram, it shows the key is ensuring the 3 systems work simultaneously. These diagrams mainly explain the actuated movement. A given form is typically sectioned to produce a set of contour curves on XY plane. For example, from wire 01 to wire 104, the profile of the U curves contain the same number of the nodal points as the IPC cutters, in this case 3 only. The number of the U lines decided the number of commands for steppers. AB refers to 2 steppers, which adjust the length of the primary nichrome wire, while XYZ represent each of 3 transforming nodal points driven by 3 cutting knives. The operation time frame is set as 12 seconds per command. However, the displacement required for XYZ, AB to move to the next point are different. That's why we have to create a different feeder rate, FA, FB, FX, FY, FZ, to maintain the same time frame. This diagram illustrates the overall workflow of the technique. Through the evaluation of geometry input, the workflow synchronizes the actuation of the IPC hot wire cutter with the robotic movement to produce a fabricated outcome. The following diagrams will unfold these procedures in detail. The IPC cutter and the robotic arm both provide constraints to the size of the EPS stock, and in this research, an outdoor seat design is performed on 2 1200 mm deep, 400 mm wide, and 1.2 meters tall EPS stock. A typical freeform surface is divided into suitable EPS size. Through evaluating the curvature of the surfaces, the robotic cutting procedure is divided into 3 continuous parts: top, seat, and bottom. The intersection of UV curves form the nodal points of the cutting profile. Driven by the movement of cutting knife's displacement, each U curve is translated into a line of comments for 5 steppers. The total cutting time of 3 continuous parts, T1, T2, and T3, is calculated based on the number of the command lines on the operation period. The cutting time of T1, T2, T3 are used further to calculate robotic velocity. The boundary curve of 3 parts, H1, D, H2, is used to generate the robotic movement in KUKA-PRC. The traveling speed is essential in this research as it needs to synchronize with step motions. Thus, the robotic velocity V3, V4, and V5 for cutting the continuous part are set by dividing the length of the routines H1, D, H2 with same traveling time corresponding to T1, T2, T3. Finally, the synchronized movement of IPC hot wire cutter and the robotic arm is further simulated in SPRATCAM before proceeding to actual cutting.
So as the IPC cutters are essentially planar, when we use it as an end effector with the robot arm, we begin to also explore the fourth axis of freedom in cutting freeform surfaces. Now, this affordance is developed by the design team into an urban project for performing landscape in the city of Melbourne, next to the Centre Market. On the left-hand side, you can see the use of agent-based system to articulate potential circulation paths through the structure, and on the right, a more three-dimensional Boolean operation to transform the cutting logic from the IPC cutters into the design process. The diagrams illustrate the potentials to deploy the technique as an on-site constructions methodology using EPS with resin-infused fiberglass. The color is so here you can see a series of diagrams that shows in more detail the cutting process, the spraying of the fiberglass and the polishing of the fiberglass. So color is used to visually enhance three-dimensionality of the surface as a form of increasing the depth and of course visual abstractions to the structure. And here's a video that shows the development of the end effector leading to the one-to-one prototype.
So here is the simulation of the actuated cutting knives before cutting. Thomas and Jiaqi are assembling the 3D printed bracket that support the cutting knives. We choose aluminium extrusion as frame to support the primary nichrome wire. Here is assembling of 500mm actuator kit. Here is a CNC milled plywood as a joint between the cutting knives and the kit. We test the temperature individually before cutting. The wires go through the front hole of each cutting knives. And it is the complete machine. We start to put machine on the robot arm with a designed connector.
Sorry, I think maybe 1 minute left.
Yeah, here's a simulation of the cutting process. We export the data of the nodal points into G-codes that drive the motors. And we simulate the robotic linear movement and racial movement. And finally is the cutting process. Here is the EPS stock, 1200mm thick, 400mm wide, 1.2 meters high. We add some diagonal movements for cutting the seat. The left is the first attempt. and the right are the second attempt. After cutting, we put the resin on the top, mixed with colors as weatherproof coating. Here is the final sectional model of pavilion design and perform stage.
And that's the final prototype at the 1:1 scale. That's the end of our presentation. Thank you very much.
Thank you.
Okay. Thank you for and okay. Thank you for the presentation and sorry we are so hurried for time and we still have 2 speakers. Now we come to the next paper, developing digital interactive fabrication progress in coexisting environment. And the speaker will be Luo Yu. Yeah. Okay. Luo Yu, yeah, please.
No. I'm not the speaker. I'm the staff of the conference. Is the speaker was Chen Junyan and Chang Chengwen. They are from National Union.
Sorry.
I just played their pre-recorded video.
Okay. Okay, please.
Hello everyone, my name is Qingyan Chen, and this is my today's presentation title, Developing a Digital Interactive Fabrication Tool in Coexisting Environment. It is difficult for makers who doesn't have experience in digital fabrication. They don't know how to operate the complicated machine and system. Therefore, generally, maker will give the blueprint or simulation and communicate with manufacturer to fabricate. In this process, the maker must be waiting until the finished project is complete before found problem. Digital fabrication is based on traditional fabrication. It starts integrate to digital because the digital machines developed. There's 4 types about traditional fabrication. The first is forming, and second is cutting, and third is joining, and fourth is finishing. And it includes different material and method, like metal bending, arc welding, and panel bending. In digital fabrication, through the digital machine and tools to replace human hands to fabricate, like laser cut, 3D print, CNC, and the recent years developed robot arm. And the robot arm is the tool that integrates the virtual and physical object, and it expands multiple possibilities of works. When the robot arm combines the design, manufacturing, and the fabrication tools, maker can through the digital media to communicate with each other and a new interactive fabrication process. Therefore, in this paper, we combine the digital fabrication and the concept of digital twin and implement a coexisting fabrication tool system that's called CoFabs to support an interactive process for designers that allows for real-time modification and manufacturing in the design sequence. In order to close relationship of human and material, DFA prototyping process proposed by Cailin Xie, which enables users to take advantage of fabrication as part of a collaborative process. DFA is a collective prototyping process that will provide a framework to allow many participants to join the process, experiment with the concept, and respond to the adaptation of interactive surface. 3 stages of DFA are design, fabrication, assembly. It makes present the design process more complete. And the mixed reality is the popular device in the digital interface field because it not only combines the virtual and physical information, but also visualization and create a new environment for the user. Let's check the picture. The user can use gesture control to interact with digital model and transform the model. Currently, there is a wireless hand-mounted display called HoloLens. It has a unique capability to integrate virtual 3D content with the real world. Optimization of interactivity with a simple gesture recognition input system allows users to easily manipulate 3D reconstructions and create 3D models in space. Therefore, HoloLens was used in this research as a mixed reality interface device for the system. And then is the robot arms application. The hardwire cutting material has large plasticity through the method of subtraction manufacturing. Users can carry out manufacturing in real time and freely. So we will use the hardwire cutting fabrication process as a research test. In order to allow co-fabs extend rapid prototyping to the other fabrication process, therefore, we divide the fabrication process into 4 steps. The first is the interface settings, and then component setting, and third is fabrication, and the fourth is finish. For verifying the DFA process, and each step is mapped to virtual and physical environment through the concept of digital twins. In order to verify co-fabs, we used FabCard to perform a small test on a unique component and utilizing robot arm hardwire cutting to fabrication in this paper. FabCard is a collaborative project aims towards the implementation of a modular car. It gives designers the ability to modify, customize, and adapt the vehicle to their specific needs at any given time and allows designer to interact on the project in real time. And we provide the 4 works area for user and in design space to fabrication and the correspond co-fabs 4 steps. In the first steps, we set 3 different architectures and tile templates. The template model will import to the second workplace by user selection, and system will compute the space to place by selected size of the tire. Second, we set up the component of engine, seat, transmission, shaft. User can drag to pick up the component and customized Fabcar internal structure by placing the components in the desired position. In the third, through track two-hand positions and generate the line from the middle as cutting tools in virtual. Users can generate the cutting path through click and moving two hands to reduce path unsmooth due to muscle fatigue when hand floating. Each click wants to generate a line as forming initial cutting surface and path. In order to allow the user can modify the model and precisely cutting, we set up the interface to provide their user to edit and modify, like the edit surface, edit curve or clear, and undo curve, undo surface. Then, according to the set cutting surface via the editor to generate the cutting path and the rapid code to control the robot arm perform hot wire cut. In the fourth, we simulate the component assemble sequence and position of the final project in physical environment. Users can via click and drag gesture to preview and assemble the component. In addition, we use color to distinguish car shell and internal structure collision position. It allows the user to check and make sure all the component is the match, and modify the component via the display of collision position. And then we will see the videos to test.
Let's recall about the time.
Now in the lesson learned. In a situation which don't need oral instructions and diagram, user can share fabrication process and working on different projects together. In this process, we will face the interface and interactivity problem. And it can via the user experience research method to solve this problem. And in the coexisting fabrications, imprecise virtual and physical information delays interactive feedback. And we use HoloLens to solve this problem, but it still needs fault tolerance. And virtual and physical information cannot be complete synchronized through the transmission of network signals. And in the future, it can via 5G network to increase the wireless transmission speed to solve this problem. And final, the conclusions. First, under the operating conditions of rapid prototyping and mixed reality, designer via the concept of digital twin to observe the difference between the virtual model and physical finished product. And the designer can build the model in digital space and see the manufacturing process of the robot arm in physical space at the same time to form a remote wireless mixed reality integration system. And the finals, the fabrication of complex space structure can be realized while eliminating the traditional dependence on 2D documents. And thank you for listening.
Okay. Thanks Chen Chunyin and Chang Tengwen's video project. And now we come to the final. Is that John, is that okay?
Yeah, I'm okay now. The final one is me?
Yeah, it's you.
Yeah, but now I'm not the hoster of the meeting, so I cannot share the screen. Okay, now I will share the screen. Okay. Okay. Sorry everyone, because my internet problem, so I need to give you the presentation again. I hope you still have the interesting. I will not introduce myself and only concentrate on the presentation. My presentation is about my research, how to use MIGA, the multi-island genetic algorithm, and RBF ANN model to optimize and predict variables. I guess the consideration of because I use two and because AN's more for the analysis and I also the me alone and so I have to optimize process. The two group of valid cases. And the big we have them support and all viewing is so I think it's very urgent viewing and
金怡啊，这还是不行啊，我们还是没办法听到你的声音的。嗯，金怡啊，sorry about that. We still cannot hear your voice. Maybe it's due to your device. Can you change to another computer or?
As I'm not
is a really a pity, but we still cannot hear you, and you know the yeah. Sorry about that. Okay.
I will record a video.
Yeah, maybe we can just begin our panel discussion, and you can take a video or change to another computer, and if you're okay, you can tell me after the panel discussion. We go back to your presentation. Okay, thank you, and sorry about that.
Okay.
Okay, can you and you share your screen and Jing, could you end your sharing of the screen? And somebody have to end the sharing of the screen? Jing, can you hear me? Jing? Okay. Okay, everyone, it's time for the panel discussion, and sorry for Jing, and I hope all the speakers. What's wrong with it? Okay. I hope all the speakers and turn on your camera and join the panel discussion. And oh yeah, okay. Ting and that and Julia is leaving. Okay.
Yes, I'm here.
Ho Yuhan, would you please? And other speakers, just please come here, turn on the video, turn on the camera. We still have Ho Yuhan, are you here?
Julia, she is gone.
Julia is gone, I know that. And Ho Yuhan, perhaps they don't. And is there? And the other speakers, Mohammed Hassan. Mohammed, are you here? Can you hear me? Just us? Sorry,
I'm here. I'm here. I'm Zhang Jiaxin.
Okay, Jiaxin, and we have 7. We have 8 speakers, and with Luo, Yulia, and the Yi is
sorry, Professor, not me. I'm staff. I just played the video for Chen Junyan. They are the authors for the last paper. So I'm not the author. I'm just the staff of our conference. So I just played the video for them, for their team.
That means they are not here?
Yeah, they are not here. They are not here. Yeah.
Okay.
Actually, 2 of the presenter there actually just play the video, so that's fine. I think we can shall I ask question firstly to special 2 guests, one from CETA, one from ICD, right? Zhong Runqing, right? And SJT.
Here.
Yeah, I think it's a great group here, including the presenter from different teams, especially most of you focus on the robotic or digital fabrication. And in the research process, I find it's extremely important because you focus a lot on the material performance. And actually, like the ICD team, you especially make research on the joints which integrate the plastic printing with the bamboo. Is actually a kind of traditional material, and you can scan the bamboo because all the bamboo pole will have their own material performance, including geometry, including all the details. So the 3D scan can help you to address the geometry system into the computer. And the question goes to, firstly goes to you, I think as to a professional architect or the implementation of the digital tools, how efficiency do you think this kind of working flow can give you the new opportunity to replace the other ways to find this kind of the joint geometry formation process for the joints? Because, for example, we can use polygon glass to position each bar and bundle them by hand. So without this kind of high-end, high-tech toolbox, actually we can do the similar things. So what's the contribution or the critical contribution from your methodology to this kind of traditional material, bamboo, to use this kind of 3D scanning joints to make a new system? This is first question. Secondly, about the structural performance of these joints. Because the 3D printing joints, actually, we need to evaluate them from a structural perspective. If it's a small table, small installation, that's fine. But if you want to construct a real macro scale structure, actually the joints will be evaluated by different kind of structure performance simulation tools. Do you testing this kind of a special compression, tension, or bending performance of your joints, including the integration joints to integrate this kind of plastic with bamboo together? So that's two questions.
Yeah. Okay. Thanks for the questions. I think the first one is mainly about the effectiveness of our workflow, and the current the status is that our vision-based sensing and adaptation process is actually quite effective, and it takes like around less than a second to generate all the results, and the bottleneck we think should be like the connection method we are using now, which is the 3D printing, which takes a lot of time to produce a joint, and that joint is also not structurally very performative. So in our research, we think in order to make it more effective, the future research would be very like intensively focusing on the connection method, because we also just see the 3D printed node as like an initial method to test our vision and adaptation processes, and the 3D printed node works actually very well for that purpose, but for the real structural purpose, maybe it's not sufficient. So yeah, we also mentioned that our future work would be really focusing on to improve the performance of the joints in terms of both the fabrication time as well as the structural performance.
Yeah, just for some additional information, that we also considered like a bunch of joints like lashing and such as clamping, and like in our further researches. And as for the efficiency of the like augmented assembly, we also like consider that as a part, maybe that could be an aspect of our like kind of future research. But it's also very valid that to give some digital information in that joint to indicate the worker, like, okay, I get the joint, and then I know how that angle is because it's defined for me. I don't need to like to adjust the angle based on the digital information, like maybe a little bit here, a little bit there, and then these information are totally included. And
welcome back.
I think that's for the questions.
And then maybe in addition, that I would like to talk about, I would like to compare our method with the AR-based mixed reality-based method. And first, I would like to say that our method is actually not any high-tech methods. The sensor we use is actually quite cheap in comparison to our like AR headsets or HoloLens. And the second point is that to position a building element, to position a stick in space, according to some AR mixed reality instructions, is actually not, maybe not as intuitive as we think about, because there are a lot of degrees of freedom to control. You need to like rotate and always adjusting the thing. But if you got a connection piece, a joint, which defines part of the position and orientation of that element in space, it will be much easier or much more intuitive for the like workers, for human workers to do that, to perform the assembly.
Yeah, and then maybe we can combine these two together and to give like a more strong way to indicate the worker to do the assembly, to do the fabrication.
Okay, thank you.
Okay, And maybe because of it's the time for dinner and there were not so many speakers here, and I keep a question about from the beginning, and because the recent year is 100 years of the modernism, and Filippo, he said there's another modernism, that is digital modernism. So I would let's discuss some about digital modernism. You know, the the real modernist group and Le Corbusier's dream, I think it's not really come true even today, because their dream is to build the developing part in the factory and directly to the user, prefabricated. And this dream, I think, even 100 years up to today, is not come true. But in the beginning of last century, they don't think so. They think it really will come soon. And so I'm very interested about the digital modernism. Will the future come soon, or later, or sometime even 100 years? So I would like someone to get some feedback about what do you think something will put the stone on the road of the future, and what will stop or slow the digital digital modernism come to the reality. And I really want to get some messages from you. Who would like to say something about that?
Maybe I can say something.
Okay.
I don't know much about the framework of digital modernism. Like where I see possibilities in the future is to use technology and AI.
Welcome back.
Or like as a symbiosis with natural fabrication in a way. So like similar like the bamboo or something. So to use, you know, like all these digital tools, like go back at the same time to more like environmentally friendly construction techniques. So also going back to a kind of tectonics, which is closer to humans. So I think that is maybe like a kind of dream or looking towards the future, like to combine those things. So like just because it's technology and robotics, it doesn't need to be synthetic and you know, artificial. You know, I think there can be like a nice crossover between biology and like algorithmic exploration and so on. I don't know if that actually like answered the question, but like that's the kind of way like how I see a hope that the future is developing.
Okay, and did someone others? Do you have some thinking about that? Someone curious? Okay, please.
Sorry. Because as an architecture student, we actually have a lot of opportunity to learn the grasshopper, the current technology things. But for me, I always feel like there's a gap between the things you want to achieve with the technology. Because I feel like you have to gain a lot of skills and have a lot of technical support in order to realize what you want to achieve. That's the first thing. I feel like it's just the basic is about technology, but it takes times and take resources to learn that technology. So I feel like in the future, if students could have the more resources to get access to the basic skills, then we can jump that gap and to actually do the things we want to do. I think that's the first thing as a student point of view. And secondly, I always feel like the machine is still a bit far from the human feelings. It's quite cold, it's very rational, it's straightforward, it's based on the math. But we as architects have to do something that would create some emotional reactions. the phenomenons, the feelings. So I feel like how we could use machine to do that kind of job. So I still feel like there's no clear answer for us. Even I think the Frank Gehry, he has a great team, but sometimes I feel like some kind of form is very iconic, it's very shocking, but doesn't really raise some emotional reactions with the buildings. Yeah. So that's my concerns about how digital technology could facilitate architect in the future.
And Mohammed, would you like to say something about that?
I think it was mentioned before, but what I see is there's a big gap between technology architects, the architecture that happens now, and environment. I think that's a hot topic, and I think that's a big challenge for not just architects, for entire globe, entire Earth, everyone living on Earth. And I think this is going to be a real challenge in the future, in the present, and especially for architects to deal with it, with the skills that we have, with the progress that we have made, especially during the last 10 years. So there's lots of topics in that, but I think that's the biggest challenge that architects have to deal with now.
Okay. And I still have a follow-up question. That is, when we look back to the modernists, we have Le Corbusier, have Gropius. They have their theory. They have their, I think they come to make their idea come to the truth. They will be mass constructed, and they form their aesthetics and the minimalism. And finally, I think in the 1950s, when the Texas Rangers, they put out the teaching methodology of modernism. That is totally whole modernism. But for digital modernism, do we still lack of something such as theory, such as thought, and some? Do you think so? And or do you have some other opinion? If we look to you.
I think I can say something on that. Whatever you name it, it's a digital modernism or not. But I think the next week is fantastic because we really organize a special event. It's a 8 days, full days event with different kind of sequence of talks, including Peter Eisenman, including Nader Tarani, and different expertise, theorists, and professional designers. And all of them will participate to talk something about the theory in digital. I think the theory is there, and including Anthony Picon, who focus more on the authorship in the digital age, including Maria Capel, who set up a speech with Roland Snook and Jules Raskin, and talk about the customization and the second digital turn. And I think we have someone from Roland Snook's team. What you're doing is really interesting, and including from Ho Yuhan, what you're doing is, which is similar focus more on the customization process of the future. I think as the new digital age, maybe customization is a special character, which give us more opportunity in the very fast and efficient ways to do something quite different and quite customized. But that is not the purpose. I think in the back we name as a special paradigm shift give us is we can very efficiently produce different kind of customization facade structure or the performance-based elements in the future buildings. And the meaning for that is not for the aesthetics. It's not for the good lookings or the special, unique experience. But I think it could be for some very special motivation, because we name it as a post-humanism age or era. Just like the coronavirus, that's why we organize this special event, because after the coronavirus, we should be thinking on why we make construction and how we make construction to have a new relationship between the human being and the planet. So it's kind of Benjamin Bratton, a philosopher who also will engage into the discussion. He actually talked about the terraforming the planet. We need to reorganize the resources in a more intelligent way, to design in a more intelligent way, to find a new sustainable future, which is totally based on the new relationship between the buildings, object, and the human itself. So actually, that is something should be customized. The better performance of the behavior, the better performance between the building and the architecture, the better performance between the environment and the building itself. So it's all based different kind of feedback, different kind of real time corresponding between the element of human being, the element of the environment, element of materials. Is kind of a totally new protocol-based design process and thinking process. So we can name it a cyber future. We can name it like a post-humanism future. So that is something totally a paradigm shift. It's not just about the modernism, which is more than that, because which is based on the different kind of philosophy, theory, design methodology, different tools, different kind of design working flow, different kind of generation, different knowledge system. So I think DigitalFUTURES right now, what we're doing is set up a kind of platform, which is a new knowledge platform. Try to attract more young generation. You can start your research and set up your friendship by the knowledge, because we're sharing different kind of toolbox, right? Like PhD student, grad student, when you're studying different kind of schools, you help your professor and you make research on different kind of toolbox. That is like an extension of human skills. That's a kind of collaboration between human and machine. So the machine intelligence, which is a topic for this CDRF conference this year, is not only on the robotics is kind of physical machine, but also the machine like computer, like this kind of computation tools. And that could be also the machine that can totally help us to redefine our future. So that is something I think very meaningful. We learn a lot from your presentation. It's a great appreciate you can sharing what you have right now to a different global culture. And we're looking forward, because the book will coming out next month, at the end of October, the proceeding of CDRF, and the topic this year is machine intelligence. So thanks a lot for your contribution, and thanks a lot for your time to participate to the presentation. And thanks a lot to the session chair, Professor Liu Yibo, to stay with us this afternoon. So thank you so much. I think maybe probably we have one hour, because around 7:30, 1 hour and 50 minutes later.
Yeah, we still have Patrick.
Yeah, opening event for the workshop. We already invite Ma Yansong from MAD and also Patrick Schuma from Jaha. Both of them will give 2 lectures, and then we'll have a dialogue to each other. So I think a great opportunity. Welcome. You join us in next event. And thank you for everyone here. Thanks for your contribution.
And thanks everyone. And one more thing, that we still have one speaker, and now he has his video, but I think due to the time, like he's played the video here, and the speakers, you can do all up to your time, because they were so close and the time within that. So if you have time, please keep here to which the the video.
Okay. He want to present, maybe I think it's still welcome. A student from Huazhong University, right?
Yeah, Huazhong. Li Jingyi. Li Jingyi, are you ready? Sorry, I could not upload video. Okay. The video could not be uploaded, and maybe sometime.
Right now is really in a very serious, tough situation. Not only the pandemic of coronavirus, but also the internet as well. So that's a pity.
Okay.
Thanks a lot.
Thank you.
Luis.
Thank you
to Professor.
I'm glad to be with you this afternoon. Okay.
Okay. See you guys. Bye bye.
See you.
Thank you.
Bye.